Check. Test. Yes, I hear that. Well, as long as the hush has fallen over the room, uh, it's 9, so we should get going. Um, I'm Paul Green, and I run the program. And it's good to see everybody here, and I'm sure a bunch more people will filter in shortly. If this is your first Einstein Fellows Symposium, could you raise your hand? Nice. Well, welcome to the program and to the symposium. Um, this is like your first hazing, sort of. So I guess I was going to go into a little description of the program, but 95% of the audience is fellows, so I don't guess I need to do that. But as you'll see, it covers a really wide spectrum of topics, from cosmology to high energy astrophysics to gravity to simulations of all kinds of beautiful phenomena. So as you know, this is required of all fellows, but at the same time, it should be fun, I hope, and a chance for everybody to get to know each other and talk about science and possibly collaborate or whatever, but just enjoy everything that's being produced by all this amazing effort going on. I was just about to point out Katie Wyman when she went up the stairs. There she is. Katie is, she works most closely with me, keeping things organized, our database, and she works closely with the programmers that put all of our software together, that keeps track of everybody's details and applications and awards, and she is, together with Evan Tingle, basically running this symposium. So Katie's the person to see if you want to get us your presentation before your session, which would be nice, because that makes things run more smoothly. If you need to use your laptop for some reason, you can, but you might lose a minute or two out of your presentation time as a result. So coffee breaks or lunch or whatever is a good time to meet up with Katie and give her a flash stick, or you could just send an email to fellows at CFA also. Later on, I hope to get the chance to introduce Carol Jengalewski, who is the grants administrator. I think she'll be showing up, so hopefully I'll be able to introduce her later. She's the person who keeps track of all the money and the many details having to do with administering your fellowship awards through your host institution. So that's about it for details. You know that there is dinner tonight between 6:15 and 6:30 at the New Bar restaurant, which is really nice. It's about a 15-minute walk down Concord Ave towards Harvard Square. We should be done here by about 5:30, so that should be enough time for everybody to get there. Don't forget, your annual reports are due Sunday, if you haven't done that. I know I've gotten a bunch of them already, but they're due. Lunch will be provided both today and tomorrow right here, so we'll try to kick people out who aren't fellows, and then we can eat right here. And that's about it. So next is my pleasure to introduce my boss, Belinda Wilkes, who is the director of the Chandra X-ray Center. Belinda works scientifically a lot on multi-wavelength observations of quasars, particularly radio loud types, and she has obviously served on many committees, NASA and NRC and the AAS head committees, high energy astrophysics. and she attended St. Andrews and Cambridge University, which means she's fluent in English, and squash and tennis as well. So I'll let her say hi.
Thanks, Paul. Is this really working? Okay. Doesn't feel like it is. Okay, good morning, everyone. It's my great pleasure to welcome you here to Cambridge this morning for what is the most enjoyable meeting we hold each year, which is to hear about the science and the new results of our talented young Einstein Fellows, of whom most, all, I hope, are in the room. But before we start, I'd like to give you my thought for the year, and that is to encourage you as the brightest and best young members and potential future leaders of our field, to make yourselves aware of the big picture, to think about the future of the field both with your own research in mind, but beyond that to the field as a whole. We are in a golden age of high-energy astrophysics at the moment, with a number of different facilities facilitating a large variety of science, but this will not last forever. From the Chandra X-ray viewpoint, it will last for a while, I'm glad to tell you. We completed last year a 25-year lifetime engineering study of the spacecraft systems, and this found no showstoppers to 10 plus more years of Chandra operations, so we're planning on the long term. The aging of the spacecraft is being very well managed. We're developing contingency plans for predictable and unexpected events as far as we can, and most of the components are operating with no major problems. So we are now in the midst of hiring new scientists to ensure that our workforce is consistent with this timescale. We encourage you to think in these terms when planning your science projects that might need Chandra observations. And also, please let us know if you have suggestions that we should consider as we make our plans for the future program. In terms of high-energy astrophysics in general, now is the time to look towards the 2020 Decadal Survey and to plan concepts to compete for the next large mission New Start. As many of you will know, in January, Paul Hertz, who's NASA's Astrophysics Division head, released a white paper requesting community input to identify 3 or 4 missions for which NASA will support mission studies in advance of the Decadal Survey. Paul's budget projections indicate about $5 billion per decade for new missions. This could support, as an example, 1 large $3 billion mission and 2 below $1 billion probes. Although such a division of funds is by no means a foregone conclusion, it's just to give you an idea of what it could support. Some of you likely attended the special head meeting in Chicago in June. A large number of mission concepts were discussed there, many aimed at probe class concepts, which, as I said, were less than $1 billion, and covering the full range of our science. In addition, the community, via the FISPAG, endorsed the X-ray Surveyor mission concept. The X-ray Surveyor would be a true successor to Chandra with comparable spatial resolution. This is unlike ESA's Athena, which, while being very large and very powerful, is aimed at about a 5 arc-second spatial resolution as opposed to half an arc-second. X-ray Surveyor would also have between 30 and 100 times the sensitivity of Chandra. So despite the growth of our community through recent missions such as Chandra, New Star, Fermi, we remain in the minority and we face stiff competition from the mainstream. This was highlighted this past summer by the Aura launch of the HDST, or High Definition Space Telescope mission concept. HDST will facilitate amazing science, as I'm sure all of us could, with a budget which, by a number of accounts, would likely require the next 3 decades of NASA's large mission budget. It would also narrow our view to the UV optical waveband and about less than 1% of the continent of the universe for the conceivable future. We need to ask ourselves, as a community, is this, a major step backward from our current multi-wavelength view, the best way forward for our field? To answer this question in the larger community, in advance of the decadal, we need to advocate for our science, to make an extra effort to go out into the community, attend meetings, give seminars, and talk about your science, our science. both current and future, not only for the sake of our own careers, but also to make clear to the whole astronomical community why and in what ways X-ray, gamma ray, gravitational wave observations, whatever it is we are doing, are key in our quest to understand the formation and evolution of our universe and its contents. Only then will a decadal survey be able to make a well-represented and correct, hopefully correct for our subject, decision. So with this in mind, and with all of you here today, I will now ask the chair of our first session, Andrea Presswich, to open the day's science program. Thank you.
Okay. I don't have anything special to say, so we'll just jump straight into the first talk. Talks are 15 minutes plus 5 questions. Is that right? I will give speakers a hand wave or a card at the end when you've got 5 minutes left, and jump on you if you would exceed your time. So we'll start with Anna Pernaka, and she's going to talk about resolving the high-energy universe with strong gravitational lensing.
The frustration of gamma-ray astronomy is poor angular resolution. With 0.1 degree, we cannot resolve even nearby sources like M87. With improved angular resolution of Chandra instrument down to 0.5 arcseconds, we have learned that extragalactic jets have very complex structures. But what we would like to have at high energies, and in gamma rays in particular, is angular resolution of a Hubble Space Telescope. I will tell you how to resolve the origin of gamma ray flares with angular resolution of the Hubble Space Telescope using cosmic lenses. Extragalactic jets are the largest particle accelerators in the universe. They transport energy from the regions very close to supermassive black hole to hundreds of kiloparsecs into intergalactic space. They also produce radiation from radio up to very high energy gamma rays. And they're also known to display very fast variability. And it is assumed that this variability is produced somewhere very close to supermassive black hole. One of the nearest examples of extragalactic jets is M87. This image shows X-ray observation with Chandra of M87. In 2004, we observed increased emission by a factor of 50 with Chandra instrument from M87. Thanks to improved angular resolution of Chandra instrument, we've been able to resolve M87, and we have learned that this increased emission by a factor of 50 wasn't originating from the region close to the core, but from HST1 node. The separation between the core and the HST1 node corresponds to about 60 parsecs. And at the same time, when X-ray emission reached its maximum, we all from HST1, we also observed TV flare with Cherenkov telescopes. But even though the flares were simultaneous, we cannot tell whether the emission was originating from the core or from HST1, because there is ambiguity in the origin of gamma ray flares. So this image shows XS map of gamma ray photons around position of M87 obtained with Cherenkov telescopes, together with radio contours. The angular resolution of Cherenkov telescopes corresponds to about 0.1 degree. The point-sprint function for M87 corresponds to about 30 kiloparsecs. So to resolve the emitting region of M87, for which the distance is 60 parsecs, we would have to improve angular resolution at gamma rays by a factor of 1,000. The future instrument will provide improvement in angular resolution by a factor of few, at best. We could resolve M87 because it's a nearby source, but we cannot resolve the emission at the highest energies. An example of M87 makes us further wonder how frequent the emission originates from the regions along the jet far away from the core. And this is very important because we use these variable sources when they are gravitationally lensed to measure time delays, and we use these gravitationally time delays to obtain Hubble constant. The multiple emitting regions can introduce systematic errors to measurements of the Hubble constant using gravitationally lensed time delays. Also, we don't know how those jets look like at higher energies. And what is the special origin of gamma ray flares? We assume that those gamma ray flares originate somewhere very close to supermassive black hole, and we have to find out where the emission really originates because it's very important for our understanding of particle acceleration. We've been able to resolve M87 because it's a nearby source, but we cannot resolve emission from more distant sources or at higher energies. Or can we? What if M87 would be gravitationally lensed? The massive galaxy close to the line of sight would curve the spacetime. Curved spacetime tells the light how to move. In such configuration, the multiple images of the source would be created, and there is a time delay and magnification ratio between the multiple images. And those time delays and magnification ratio depends on the position of the emitting regions in the source plane. Therefore, when we can measure those time delays, we can find out from where the emission originates. So here is the idea and all the elements. The extragalactic jets are huge. They can be even hundreds of kiloparsecs. But those from which we see the largest variability are those which have a jet pointed under a small angle toward the observer. So when the jet is pointed toward us under an angle of few degrees, the size of the jet is about few kiloparsecs. Also, the Einstein radius of the lens, where the lens is the massive galaxy, is about few kiloparsecs, which means that we can fit entire jet into the lens plane. Then, depending from where the emission originates, the emission will pass the lens plane at different distances. And we will have a different time delays depending from which emitting region along the jet emission, where the emission was produced. Then we can resolve emitting regions. We can resolve mirage images with radio and optical observations. Also, optical observation give us the redshift of the source and redshift of the lens. We can use the resolved images together with distances to reconstruct the mass distribution of the lens. Now, imagine that we have a gamma ray flare from this object. We cannot resolve gamma ray emission. We cannot resolve mirage images at gamma rays. But we can resolve the flares. And the massive galaxy will produce multiple images of the same flare. And the variability timescale of these flares are of the order of hours to days, which is much shorter as compared to the time delays, which are of the order from weeks to months. Therefore, even the light curve at gamma rays is the sum of multiple images. We can resolve the ecoflares, and we can measure the time delays between ecoflares and the magnification ratio. And when we have magnification ratio and time delays, we can find out from where along the jet the flare originated. But M87 is not gravitationally lensed, at least not when observed from our galaxy. Now, let me take you on a journey with the spaceship of imagination to the place where M87 is located at redshift equals 1, and between us and M87 there is a massive galaxy which split the emission of M87 into Einstein ring of diameter of about 2.2 kiloparsecs. At redshifts equals 1, the distance between the core and HST1 of about 60 parsecs will correspond to about 0.01 arc seconds, which is about 3% of Einstein radius. Small, it's large enough to produce significant differences in the time delay and magnification ratio depending if emission, the variable flare, originated from the core or from HST1. In this example, the difference in the time delay would be about 2 days, and the difference in magnification ratio corresponds to about 0.2. We can measure time delays with much greater precision than 2 days. Fermi telescope has a horrible angular resolution, but it's a unique instrument in terms of temporal resolution. It pictures the entire gamma ray sky within a few hours and produces uninterrupted light curves of all gamma ray blazars since 2008. And among these blazars are also gravitationally lensed ones. One of these objects which is gravitationally lensed is PKS 1830. This image shows the radio emission of PKS 1830, where we can resolve the multiple images of the core, and the pseudo-ring-like structure is made of extended emission of the jet. The radio time delay for this object is 26 days. Also, this object is very bright gamma ray emitter. So here you can see gamma ray sky around the position of PKS 1830, where this distance corresponds to about 5 degrees. And we've been also able to measure time delay during the low state of this object at gamma rays. And the time delay during the low state for this object is about 27 days, which is compatible with the radio measurements. But then we are interested from what is the time delay during the flares and where the flares originated. So here is the light curve of PKS 1830 as produced with a Fermi-led telescope at gamma rays. So indeed, we have 4 series of flares. And now our ability to resolve the gamma ray emission depends on how well we can measure those time delays. So we have used 3 different methods to measure these time delays: the autocorrelation function, the double power spectrum, and the maximum peak method. We evaluated the weaknesses and strengths of those methods using Monte Carlo simulations. And as a result, we have found that flare 1 has a time delay of about 23 days, flare 2 has a time delay of about 19 days, and flare 3 and flare 4 don't have detectable time delays, which means that the time delay must be greater than 50 days. So we have a time delays. Now we need to know what our lens is. What is the mass distribution of the lens? And we can reconstruct mass distribution of the lens because we have resolved radio images of this blazar. Resolved radio images allowed us to build time delays maps where you can see what time delay we expected as a function of the position in the source plane. Also, using the radio images with resolved the position of the core, we can localize where the core is located in the source plane, and also we have a projection of the jet. Then using time delay map, we can localize along the jet and within the core where the gamma rays originated. And we have those time delays, so we could find out that flare number 1 and flare number 2, as well as the time delay, which the emission during the low state, is consistent with the position of the core within 100 parsecs. Then for flare 3 and for flare 4, the time delay must be greater than 50 days, which means that the distance between the core and flare 3 and 4 must be larger than 1.5 kiloparsecs, which suggests that the gamma ray flares can originate from multiple regions along the jets. Gravitational lensing is a powerful tool to resolve high-energy universe. Using cosmic lenses, we've been able to turn the temporal resolution of the Fermi-led telescope into spatial resolution, and we enhance angular resolution by a factor of 10,000. And cosmic lenses allow us to resolve the origin of gamma ray flares, and we have found that the gamma ray flares can originate from different places along the jet. So this is one of the brightest gamma ray blazars, but already I'm working on the second one. So we have a few at gamma rays. And then, of course, if we go lower wave energies, we have more and more systems.
Does the spectrum of gamma rays change between flares 1, 2, and flares 3, 4? Or is it easy to see?
So they,
Can you repeat the question?
because the question is that if the spectrum, the gamma rays, change from flare 1 to flare 2. So there are some small changes between flares, because even if you look at the flare 1 and flare 2, they are composed from multiple flares. So even within flare 1, you would find changes and differences in the spectrum.
When you're calculating the delay from the flare observed at another wavelength, what are you assuming is the same about the flare at low energies and high energies to calculate the delay? Are you assuming it's in the same spot? Are you assuming that it has the same time evolution in gamma rays?
So when you measure time delays at different energies, you don't make any assumption. You just have a light curve at given energy, and you don't make any assumption about where the origin of the emission is. You take the light curve and you measure time delays, and when the time delays differ, then you may wonder, what's the difference in the origin, of the spatial origin?
Gravitational lenses cannot change the frequency, so you...
Exactly, they are independent on the frequency. So if you observe the difference in the time delay, it must, the origination of such a change must come from the displacement of the emitting regions.
Did the three methods really agree, and which one was one a standout as a better way of doing it?
So autocorrelation function, which is widely used, isn't the best method because we have evaluated with Monte Carlo simulations. And the strength of the double power spectrum is the signal processing. That when indeed you can measure the time delays with great significance. And then you can, because sometimes your flares last for like 100 days and have a good statistic. So you can use methods based on the Fourier transform, but sometimes you have a single flare. So you cannot construct the light curve, long light curve. And in such a case, we developed the maximum peak method. So depending on what your signal is, different method works better or worse.
Yeah. So it didn't look like the light curves were incredibly rich. There's, a certain cadence that you have to work with. So I'm curious about substructure in flares. How much of that is there, and what kind of use can you make of it?
So probably you ask about flare 2, last two flares. So indeed, if you look at the flare 1 and flare 2, there is a lot of structures. So you can use autocorrelation and double power spectrum to estimate what the time delay in the such a light curve is. But then, if you look to flare 3 and flare number 4, where we are unable to find the time delays, we use different method. For example, here you have isolated flare, which means that you cannot apply autocorrelation. So that's why for such kind of flares, we develop different methods. The maximum peak method, where such a light curve, when you have a single flare, it's kind of perfect situation when you want to look for eco flares directly. So you can measure what is the ratio between the flare, emission of the beam of the flare, and the consecutive beams. And then you can compare those ratios as a function of time delay with expectations from the lens modeling. So for this kind of flares, we use different methods, and they are also very powerful.
One more question?
This actually just answered my question.
Okay. So let's thank Anna again. The role of general relativity in the tidal effects of few body stellar interactions.
Okay, hello, I'm Johan Samsing, and I will tell you about something completely different. It is a role of GR and tidal effects in few-body interactions. And what I mean about few-body interactions could be, for example, the single stars that are coming very close to each other. It could be binary stars, it could be binary single stars. And it is some interactions that plays a very big role in dense stellar systems. And what I will be talking about here is especially the role in globular clusters. So I actually started as a fellow last year, but I had some problems with my visa, so I started very, very late. So I moved to Princeton from Denmark last winter here. It basically looked like this at Peyton Hall. Maybe some of you have been there. I was then lucky to find the house. It's the picture from a little bit later that year. And I got a daughter here just 2 months ago, so I'm very excited about that. Anyway, so my main problem, like the main project that I'm gonna look at is like what is the role in GR and tidal effects in these few-body interactions. And the tools I have to study this is a new code that I've been working on the last couple of months. It's the full parallel code, in-body code with dynamical GR and non-linear tidal effects. And the first couple of goals that I have is to figure out first what happens if I have a few-body interaction and then I have tides. Like what is actually happening? Can I quantify that in a cross-section, for example? Collisions between stars, something that happens if you have finite size objects, you can calculate a cross-section for that. Can I like identify something similar when I have GR and tidal effects and calculate cross-sections? And what are the observable outcomes of this? So first, a very short introduction to this. So this is a global cluster, and the density of stars is 1 million times higher than in our solar neighborhood. So stars are not just moving around in a smooth potential and never see each other. They actually have many different dynamical interactions going on here. So I made a few examples here. You can have a binary single interaction that I showed here. You can also have binary interactions. You can have cosi triple. Some of the other Einstein fellows was looking at this a couple of last years. You can have closed passages between neutron stars or normal stars. So this is something that happens all the time in these globular clusters. And all of these plays a very big role in both what you observe and how the globular cluster evolves as a whole. So for example, the binary single interaction, the binaries are kind of the heat source preventing the globular cluster from collapsing by kicking out stars when you have a triple interaction. Binary can create cosis. Cosis can create mergers or compact binaries. It's very interesting for gravitational wave signals and so forth. And you have passages between these compact objects. So these dynamical interactions directly propagate to the different binary populations that you see from globular clusters, and the signals can be supernova, GRBs, and of course gravitational waves. These interactions plays a big role there. So let's see what happens if you include GR. I looked a little bit on that before, so I don't want to talk too much about it. But basically, you start to form black holes. You also, in your binary single interactions, you can start to find, you can form compact binaries that are spiraling in due to gravitational wave radiation. And I found that gravitational wave signal is dominated by a very high eccentric part of the in-spiral. And we found that is probably have the highest cross-section or highest rate for these high eccentric in-spirals compared to the single. You have also precession effects, which other Einstein fellows were looking at in the cosi troubles. Now let's try to add tides into this picture. Things just get a mess here. So all the stars are not spherical anymore. They start to stretch. There's nothing conserved anymore. Stars are being eaten by black holes. They merge. You have blue stragglers. You have all things going on here. So it's a huge mess. So we wanted to try to make a sense out of this, and what can we observe in this mess, and what can we then learn from the globular cluster and these dense stellar systems. So the way that you do it is to break it into channels. You're saying, okay, I want to look at the single or the binary single channel. I'm going to show you a few examples of my work on especially the binary single channel here. So this is a triple interaction between a binary and a single. So you can see it's very complicated. So you need fully dynamical GR and some limit and tides as well. So for that, I've made a new code here, and I will not tell any details. People can come and ask me, but the thing that I assume about the stars is that there are similar ellipses. And from that, I can calculate completely their evolution. People have been looking at this in the two-body studies. Nobody have done in like anybody before. First, Carter, Luminet, Ley, Ratio, Shapiro did a lot of papers in this model here, and could channel also 91. But now we have n-body code, and I put in the GR with the post-Newtonian prescription. It's basically just adding some modified terms to my equation of motion. Okay, so with this kind of code here, I can calculate these very complicated interactions here in just a few seconds with full tides and GR. And there's absolutely no way that you can do it with hydro. But of course, there is some limitations. I cannot disrupt the stars, but I can calculate the more weaker field limit. But you can see there's a lot of things going on already here. So I'm going to show a little example here. And I was not sure if I could show a movie here. So it's going to be a little bit manual here. So it is a tidal capture neutral star and a main sequence star here. So it's coming in here. And then going into an orbit here. You can see here. That just takes a fraction of a second to calculate these things here. I can also do interactions between main sequence stars. This is like a highly compact interaction here. But I don't need so compact systems to actually see something, right? So you can see in this binary single interaction that the system is approximately divided into a binary and then a bound single. You can see it here. How does this work? Okay. I have a binary here and a bound single. Then it comes back, bounces one more. I have a binary and bound single. And then it goes like this for many, many times until it reaches some final state, an exchange or collision and so forth. So the key to understand what happens if I include tidal effects is to understand what happens basically to these isolated binaries here, because the system spends most of its time at that state. So let me show you a few examples of binaries evolving with tidal effects. People think about tidal effects as just something that carries energy out of the system. You spiral in and then you have a binary. But if you solve all the equations of motion, you find that there is also coupling between the orbit and the tidal energy of the stars. And you don't have to put much tidal energy into the stars before the orbit is changing very, very much. The binding energy of the star is like huge compared to the binding energy of just normal binaries. And so here I have, it's a little bit hard to see, I have a star here, another star here, it's coming in, and it evolves around the star here many, many times. The gray one here is the semi-major axis of the system. It's just like jumping around here. It's a function of time. This line here is how long time the system has before the single one here is coming back. Okay? So at some point it's coming in here, and then the single is coming back, disturbing the binary here, and then the system further evolves as if it has like a reduced energy. You can see it's kind of a little bit random. Sometimes it could also be that this could be over here, and then the system would evolve with lower energy. And since the system has a lower energy, you increase basically the number of mergers in the system. Just one of the things happening. Another example where let the binary run for a longer time is this one here. You can see goes very, very crazy here, and this is the three axes, the principal axis of the star. I just want to show you the other one again. So here, for example, you can see that the semi-major axis is changing quite a lot, but the stars are not changed very much. It's just the radius is going from 1 to 1.1. So it's not that I'm disrupting the stars or anything. You can like, James? No. The viscosity timescales is normally much, much longer. And viscosity is very hard. There might be other ways that you can dissipate away the energy, which is shorter than the normal Kilder-Helmholtz timescale. But I can put in the viscosity, but that's a detail. Okay, so what is happening? So I want to share some few results here. So the idea is basically, in this case, to have a binary, send in a single, and I do this millions of times. And then I'm going to record what is happening when I have tides, and what is happening when I don't have tides. what I found is that when I have tides, I create like these tidal inspirals doing my triple interactions. Okay, so here, for example, I have a binary in here. There's a single star coming in here. I have an interaction, and then a temporary binary is formed. Instead of just devolving out here and going back, as I saw some of the other curves, it actually spirals in. The semi-major axis becomes smaller and smaller between the two stars, and then I form a compact binary, and then actually end up merging. I have other here. It's a crazy interaction here. I have the binary here completely. You can see very clear the orbit tidal coupling here. It's not just going in, but it's like, and here, this one here is going in, almost merging, but then it survives because you have the coupling, goes out again on a wider orbit, and actually ends with an exchanged interaction. Also merge here and here and here, and these two here is simulations where I did not put in tides. So here you have like these intermediate state binaries, these temporary binaries just go in and back, in, back. But here it goes out and then merge. It's just a fraction of these that does this. Okay, so that is just a little picture of this here. So I have a perturber coming in here, the interaction, and then I create an inspiral here, tidal inspiral, and this is the two stars just before, like 3 or 4 orbits before that they actually merge. So they're not stretched very much. When I then reach to a limit where they're coming very close, then you can use the hydro to predict the signal from these tidal inspirals. Okay, so I just want to make a short comment on that these here looks very much like if you put in GR effects. I did not talk much about that. You don't need that when you have stars. But if you have, for example, 3 neutron stars that are interacting and you put in GR, you find something very similar. I have here like the center of mass just moving along the screen here, so it's more easy to see. I have the complex triple interaction here, and then a temporary binary here is formed, and the 2 neutron stars are spiraling in due to gravitational wave radiation. I have note that like gravitational waves is only energy sink, right? So that is why it looks so smooth. There's no coupling between the modes and the orbit. Very smooth here, and this kind of signal here is sure to be very interesting because it spirals in with a very high eccentricity, and that have a very rich signal when you ask the LIGO people. That was very interesting. So the thing that we learned from this was that the cross section for these inspirals to happen increases with the semi-major axis of my target binary, which was counterintuitive at the point that we looked at it. It means basically that these high eccentric inspirals are dominated by widely separated binaries. So, of course, a natural question is it the same with these tidal inspirals? And that led me to the final slide here, where I just give you a hint of what is actually going on. So I was actually able to put this into a larger framework a couple of weeks ago, where I could calculate actually by hand the cross-section for these inspirals to happen for a general sync term. So I will show you here the interaction here, where I basically have a binary coming in, a single. This is the region where it goes completely crazy, and then I have an inspiral coming out and a single coming out. If I consider the case where the sync term could be gravitational waves, tides, whatever model you have, goes as a power law as 1 over the pericenter to some beta power, where the pericenter is here. So you have I'm just here talking about 2 objects that are coming. I don't talk about triple interactions with this one here, but the whole is for triple interactions. So you just have to understand how much energy do I lose in a single passage at some pericenter distance. For gravitational waves, that power is 7.5. You can very easily calculate that. For tides, it's closer to 3, because it's tidal field. Then I found a way to calculate the probability for creating these inspirals, giving a binary single interaction, is proportional to the semi-major axis, so 1 over the beta minus 1. And then I can convert that into a cross-section as A, semi-major axis of my target binary, 1 over beta. And if I put in the gravitational wave term, which is 7.5, then I can calculate the cross-section for these chaotic triple interactions for creating these inspirals here, and these dashed lines here are that power law there. But this is this is completely general. So I can also put in tidal effects, for example, and say, okay, what happens if the power law is like 3 instead? Then you can see it will still increase with semi-major axis. In fact, you can see that for any beta, the cross-section for generating inspirals from any kind of sync term will always increase with semi-major axis. So you're not dominated by something that's already like nearly touching each other. It's actually your cross-section for creating these things are dominated by widely separated binaries. And these inspirals, no matter how you look at it, the cross-section will always dominate over collisions. Like when you, unless that the binary is nearly touching from the start. But when you start to just move them a little bit away from each other, then these inspirals here will greatly dominate over solid sphere collisions. So people normally, there's tons of codes out there, in-body codes with just like the sticky star approximation, solid spheres, and then you calculate collisions. But if you actually take this into account, then you have a huge population of dynamically assembled inspiraling binaries from whatever sync term that you put in here that where the cross-section is highly dominating. Yeah, that is the bigger picture I'm trying to put together right now. And there's tons of different systems that you can look at. This is just for equal mass binary, like for equal mass objects. The globular cluster fully rich with different kind of objects, and that is where my in-body code is coming in. This is just some understanding of what's going on. Okay, thank you.
So, any questions for you?
Yeah.
How did you, since you just wrote this code, how did you test it? Like, are there any?
There is actually several ways to test it. Yeah. Okay. So in the weak field limit, then this model here is fully equivalent to the normal Prison-Tolkowski. So the Prison-Tolkowski, maybe you're not like people in here have been working, like spent their life on that, but it is basically you decompose the star into spherical harmonics, and then you can calculate by leader theory. You can calculate by hand basically what is the energy that goes into tides for different multipoles. And this one here, I'm just looking at the I'm perturbing the stars as 3x3 matrix. So I only keep track of the quadrupole. And in the weak field limit is identical to this one here. So I've been comparing with that. I've been comparing with the two-body interactions that Dongley, Ratio, Shapiro did a long time ago with Newton stars. Like all these different curves, you can calculate how much angular momentum that goes into the stars. When I have the triple interactions, I can look for energy conservations and tons of other things. And I can basically see everything sums up. And I can also calculate what is the different evolutions by hand, and that actually also matches these things. So I believe that's fine. Yeah. Yeah. Nick?
So that binary single channel performing eccentric compact object inspirals seems really interesting. Have you estimated the relative rate between that channel and other dynamical formation mechanisms that give you circular inspirals, like two-body gravitational wave capture?
Well, so that is the thing I did. Yeah, with that GR thing, I was comparing it with like the normal channel that you will think that produces high eccentric inspirals is single captures, and it all scales with what is the number of binaries that I have in my globular cluster, right? If you put in something that you think is realistic, then you would find that this mechanism here is a factor of 5 higher, something like that. So all the things you basically find is that like things are at the same magnitude, things, right? It's the same forces that you are playing around with, so it all scales with the binary fraction. But if you put in something that you think is realistic, then you will find this binary single interaction to be the dominating. Huge uncertainties, but the cross sections should be just fine. You can just multiply with them. Yeah. Yeah.
So just the last expression you had with the A1 over beta for the cross section.
Yeah.
If you go to higher order modes, beta will tend to get larger. So wouldn't that suggest if you account for the higher order modes that it might be a little bit more evenly distributed?
Yeah, in fact, you can. I could. It will take me a little time, but I can assure that, like, basically, no matter which function that you put in there, the cross section will always increase with semi-major axis. It's just harder for me to write out the exact expressions if it's not a power law.
It'll be very weak. Right?
It will be very weak, yeah. And it's probably not, physically okay. Like, it's hard to estimate exactly what is the big scale tidal interaction dissipation of the. But if you have something that looks like this, then it will increase with them, and then we can talk about it, but it will be for any function actually. Yeah.
When you simulate the flows encounter a couple of stars
Yeah.
with the tides,
Yeah.
Do you have to take into account the spin of the stars?
Well, I could put it in as an initial condition, but it's basically something that comes out automatically. There is a torque acting on this star, which is just looking somewhere at some point. And so there's like the gravitational fields like torquing this thing around. Same time the wave is like going around the surface. So basically these things should be self-consistently solved when I solve the equations. Okay. Oh, there's one more. Yeah.
My impression is that a lot of the binaries, let's say in globular clusters, are tight or become interacting. Let's say X-ray binaries or something because of evolution of the stars.
Yeah, that's also true. Yeah.
AGB stars, they blow off winds and the binary coalesces.
Yeah.
But I'm not sure how. Clearly, you're not looking at that here.
No, I am not looking at it here.
And
so
how important is that factor in globular clusters?
Compared to this way of forming binaries, I'm not exactly sure. It depends on which kind of the population that you're looking at. Well, this is highly sensitive to the mass ratios, for example, so you tend to replace lighter members. So it depends on which kind of mass ratio you're looking at, and it's I cannot put numbers on it, but it is something like that. That's the goal of like estimating the. Yeah. Okay.
Okay. So our next speaker is. And he's going to talk about a review of the bar geometry.
All right. Yep, no problem. All right. Good morning, everybody. My name's Mario Manuel. I'm a third-year Einstein Fellow, so this will be my last year giving a talk here at the Symposium. I think I'd like to start off by saying that it has been a great honor and a privilege to be here as an Einstein Fellow, coming from a community slightly outside of astrophysics originally, and being able to come and see this every year and being more a part of the astrophysics community at other conferences and talking with people about laboratory astrophysics, specifically high energy density laboratory astrophysics, has just been really cool. And so it's been great for the last few years. The Einstein Fellowship has been probably a really big highlight for my career thus far. Let's just say that. So this is the same title slide that I think I've given for the last two talks as well. Because HED laboratory astrophysics is something a lot of people aren't familiar with. So I like to start out with putting up a list of things that people in my field work on that are related to different astrophysical systems. And let's see, the first one I've got up here is collimation and propagation dynamics in magnetized flows. This is something that I've worked mostly on for the last couple years. It's been looking at magnetized supersonic flows as it pertains to young stellar objects. I decided not to talk about that today instead, and talk about something that looking at this field has sort of brought me into, and that's down here at the bottom, relativistic electron-positron plasmas. There's a lot of groups at Michigan and Lawrence Livermore National Labs that are doing things in radiative effects on hydrodynamic systems. I started working with folks doing collisionless shock work, again in supersonic flows, and all of this sort of culminated in me trying to get into doing relativistic plasma physics and how that pertains to certain astrophysical objects. And so I've modified my slide here to look at relativistic laboratory astrophysics and talk about some of the recent results that have happened from another group in Europe that came out this year that has really, I think, opened up a new way to look at this in the lab. So I have here a plot from an old 2003 report that looks at temperature and density parameter space to kind of show where all of these different objects lie in parameter space. And what I'm going to talk about mostly today is gamma ray bursts up here in low density, high temperature ranges, and how I think these types of systems we can now form in the lab and study the details of how these systems interact. So the bullet point, the main topic I hope that you can take away from the talk is given right at the top of this slide. Relativistic plasmas is an emerging field in laboratory astrophysics. It's been something that I've talked with folks here over the last couple of years about, and the question is, well, can you make a relativistic plasma in the lab and actually study it? And my answer has always been like, well, we're working on it, right? So the reason that this is interesting is, well, if you saw the first talk, it was great. She talked a lot about gamma ray flares and things like that. A lot of the energetic events in our universe involve relativistic plasmas. And so can we study this type of physics in the lab? So the way to actually make this plausible is that the plasma must be near neutral, quasi-neutral, so that you have no net currents that are flowing around. Everything's based on the neutrality of the plasma. And it needs to exhibit collective behavior so that it's relevant to the astrophysical system. And what I'm going to talk about today is using intense lasers to produce these types of systems and how that gives us sort of a unique window into looking at relativistic plasma physics in the lab under controlled, tunable conditions. So I've snagged a generic cartoon from NASA Goddard that sort of gives the general picture of how gamma ray bursts are supposed to work. I am not an expert in this, but what I've started recently looking at this in the last couple months and applying for new jobs and trying to promote relativistic plasmas as something that's new and exciting to look at. So the general picture as I see it is you have some sort of relativistic energy source. In this case, from this cartoon, it's a black hole engine that's creating some sort of relativistic energy flow. This is transported outwards away from the compact object. And in the general picture, you tend to have these sort of short burst emissions that have sort of this faster shell or slower shell. Then inside the outflow, these different emissions can interact with each other within the flow itself to produce the prompt emission that people see in gamma ray bursts. And then as that flow continues to go outwards, it eventually interacts with the background ISM or whatever it happens to be that's out there. And this produces sort of a broadband spectrum that has an extended emission over days, multiple days, tens of days. So I said, well, what can we, in that general picture, what can we actually look at in the lab? So we won't be simulating any compact objects in the lab. That's not going to happen. What I will try and do is look at what's going on in terms of the relativistic plasma outflow. So the first part of that is energy transport here. We need to create a relativistic fireball that is propagating outward at relativistic velocities. Then to look at the prompt emission portion of the GRB is from the general model is you have these interacting shells of the different fireballs running into each other within the outflow itself. And then finally, for the extended emission, you have this fireball that's now interacting with some sort of homogeneous background plasma or something like that. And so can we look at these different things in the lab is really what I'm trying to address. So the laboratory fireball needs to behave as a plasma in order to be relevant to the astrophysical situation. So if I take my little cartoon rectangular fireball and say, all right, let's let this be an electron-positron plasma. So I can write down what the plasma frequency is of this. It's depending on the sum of the densities of electrons and positrons, and it's corrected for by the Lorentz factor for the mass. So I can put some scales on this and say, all right, well, it has some transverse dimension, L fireball we call it, and the longitudinal dimension is going to be c tau. So the tau here is sort of the time scale that these shells are emitted at. That will determine sort of the width of the fireball. And then our two conditions here is that it needs to be quasi-neutral. So the number of electrons is about the same as the number of positrons. And it needs to behave collectively. So the systems are inherently collisionless because these things are moving at relativistic speeds. They're not actually running into each other. The way that you get collective behavior in the plasma is by having essentially this transverse dimension larger than the collisionless skin depth. So through electrostatic wave interactions, the particles are actually interacting with each other without having any actual Coulomb collisions. So you can rewrite this, this condition, assuming that this one is correct, basically as an inequality which is dependent on the total number of electrons and positrons in the fireball, and the Lorentz factor of the fireball, and the time, the temporal emission of that. And basically this quantity is greater than 1. The time, I've written it in terms of 10 to the minus 15 seconds, which is a really small number for all of you folks, I think. It's even small for a lot of the work that I do, but for the types of lasers that we need to make these types of systems, we're typically talking in the tens of femtoseconds. So a plasma with these characteristics may be created in the laboratory with, as I said, tens of femtoseconds or ultra-short pulse laser systems. The way that we do this is through relativistic pair production. And in order to do that, we need essentially a relativistic electron bunch to begin with. So the way that we produce pair plasmas is through pair production through interactions with heavier nuclei. The two processes that are typically talked about is the Trident process and the Bethe-Heitler process. Each of these requires a relativistic electron to come in and interact with the Coulomb field of a higher Z nucleus. The electron scatters in the Coulomb field. It produces electron-positron pair and a scattered electron. The Bethe-Heitler process is similar, except instead of directly creating the electron-positron pair, it creates a gamma ray first. The gamma ray interacts with the second nucleus to create the electron-positron. So here you can get a nice cascade of different things producing the electron-positron pairs. Because of the way that the cross-sections go with the charge of the nucleus, in the systems in the lab that we create, it's the Bethe-Heitler process that ends up dominating it, because as Z goes up, it's going to create the most pairs. So to do this in the lab, we use, the way I've split it up is sort of a two-phase process. So phase one is you're creating some sort of relativistic electron bunch, and then you convert that relativistic electron bunch into a relativistic electron-positron jet. So phase one, to generate the electron bunch, the way that this has been done previously, there's a number of ways to do this, but one of the sort of nicest ways that gives you a lot of knobs to turn experimentally is through wake field acceleration. And so this uses a short pulse laser, something on the order of 40 femtoseconds or tens of femtoseconds, with very high intensity, 10 to the 20 watts per centimeter squared. This is incident onto a low density gas. Oftentimes this is helium or something like that, and you can dope this with higher Z elements to basically tune your spectrum. So the time scale that this electron bunch comes out at is dependent on the plasma frequency inside of this low density gas. And as you change the dopants in this, you can tune what your electron bunch looks like. So here's some results from a paper from 2010. Here is this gray dot here is essentially the nominal case where you have the short pulse laser interacting with the helium, pure helium gas. And you can see what happens when you add, say, 1% atomic nitrogen. You get this sort of flat top profile. So this is electron energy and essentially number of particles. And so you get this flat top energy profile when you add the nitrogen to it. If you put in 1% argon, you get this sort of monoenergetic profile that's centered around 110 MeV or so. If you add 1% neon, you get this sort of linear profile. So by changing the details of what's inside of this gas for a given laser, you can tune your electron spectrum that's coming out of this system. And sort of typical time scales that this has is about 13 femtoseconds. So wake field acceleration provides an efficient mechanism to create tailored relativistic electron bunches. So that takes care of our phase one. We've got this way of creating different relativistic electron bunches, and now take that to the second part of this is to actually get a electron-positron jet out of it. So that's our second phase here. So this comes into basically putting that electron bunch into a converter block. And what I've plotted here is a radiation length as a function of atomic number. I've outlined where lead is at here because that's what these recent experiments that were done this year, they use lead, so I figure we'll start with that. And so this is radiation length for 10 MeV electrons, and the radiation length for lead is about 5 millimeters. So in order to create a quasi-neutral electron-positron jet, the length of the block needs to basically be 5 times the radiation length. And this comes back to that fact of you have this cascade that's going on as the relativistic electrons are going in and creating gammas and then creating pairs. There needs to be a long enough length where these interactions can occur. And so they did this. This is Sari et al. From Nature Communications, again, from this year. This is a plot from their paper. And so this is the essentially the ratio of positrons as a function of lead thickness. And so what you get is as you increase the length of this block, you're asymptotically approaching this quasi-neutrality limit. Again, that's what we're looking for and trying to do in creating a relativistic plasma in the lab that we could actually do something fun with. And so this was one of the things that really got me more interested in it sort of this summer, was like, all right, somebody has sort of found a way into this regime, and now there are all sorts of cool things that we could probably do in the lab with this. So this technique can create a quasi-neutral relativistic plasma jet that behaves collectively. You have a lot of experimental knobs in terms of the dopant in the gas, or the density of the gas, and changing the length of the converter block or changing the type of the converter block to alter what the relativistic jet looks like in the output. So in this case, it's something on the order of 15 femtoseconds is the emission scale for the experiments that they did here recently. So coming back to what we might be able to do with this, with respect to the GRBs, is first looking at these interacting fireballs. So now if you have a method to create a relativistic fireball, you could then why not create 2 relativistic fireballs and run them into each other? Or change the electron spectrum so you have sort of double-peaked relativistic fireballs that can run into each other. The other thing is instead of looking at the prompt emission, you can look at the extended emission and say, okay, an even easier thing to do is take that fireball and run it into something. So whether you put this into a background plasma or a background gas or whatever that happens to be, that's sort of the easiest next step in this phase. And what would be really interesting and what is still sort of ongoing and what I hope to do in the future is try and measure the gamma ray spectra from these things. So the way that these systems emit gammas is all in about 15 femtoseconds, and it's very high flux, and it's not something that you don't put your single count photon counter out there and count these things. So there's a few different methods to try and look at this, and a lot of that needs to be developed in the next few years. So these are some simulations that were done for this paper. There's another one coming out on arXiv soon. These are from a group at University of Lisbon. This is for that same experiment that they did. They simulated a 50-50 electron-positron jet traversing a uniform electron-ion plasma. So here I think it's the blue is the electron bunch density, the electron density, and the red is the positron density. So you see that the transverse dimension here is a little bit longer than the longitudinal. So you kind of have this pancake relativistic jet that's propagating through. This is a contour at a specific density. And here you can start to see the filaments that are forming. This is a projection of the filaments that are forming when it's running into this background plasma. And so they have this instability growth, and the question is, do the fields that are generated in this type of interaction, in this simulation it's about 40 Tesla, can the synchrotron emission from that be the cause of the gamma ray bursts that we see? And so that's what they're sort of promoting in this study, and I think that this is something that we can do in the lab and actually measure the emission from and answer that question. So there's all sorts of studies that can be done with this type of a laboratory setup, looking at synchrotron emission from self-generated or amplified fields, filament generation and characterization, so instabilities in relativistic plasmas, collisionless shock formation, so you have these two things smashing into each other. How do the shocks form? How are they mediated? How long do you need them to be there? And can you study particle acceleration in those types of systems? All questions that I think can be addressed using relativistic plasmas in the lab. So I'll end again on my summary and again emphasize that I think relativistic plasma is an emerging field in laboratory astrophysics, and it is just coming into the community, and I think there's a lot of new things that can be done. I won't go through all the bullets again, but that's sort of what I've been working on for the last couple months only, in terms of just going, well, I think there's a lot of interesting directions that this work can go into, and so I'm going to pursue that for the next few months while I still have my fellowship.
Is your bunch itself relativistic? What sort of Lorentz factor is it?
So the work that they showed this for the 2015 paper has an average of about 15, but it goes up to, you know, I think it's an exponential spectrum roughly. So depending on where you want to make the cutoff, it goes up into the high tens, not quite 100. But again, I think that again this was the first time that they've been able to show that this is plausible and possible in the lab, and so a lot of it will come down to, I think, tuning the electron bunch to create the jet that you want. So you saw that in one of the cases you could create a monoenergetic electron bunch. Does that actually correlate to an a monoenergetic or nearly monoenergetic relativistic jet in the end? I haven't run any simulations or anything. I can't answer that yet.
This is a very powerful laser, about 4 orders of magnitude in atomic intensity. Doesn't a laser of this power respond to vacuum to create electron positive configuration?
Yeah, that's actually something that people would love to do. And one of the things that they're wanting to keep investigating by upping this intensity. I mean, the intensity that it's actually at, it's focused down to that energy. So it doesn't actually reach the intensity of, say, 10 to the 20 until it's actually hitting the jet. And the hope is that for some of these upcoming systems that are... I'm sorry? How the width? Well, so the spot size, when it's focused down, I think they're down to 10 or 20 microns. Yeah. I wasn't part of the experiments. I'm presenting somebody else's work here, but I don't know exactly what it is. But typically for those types of lasers, that's the kind of spot size you're getting, is around 10 microns. But a lot of the new high intensity lasers that they're building in Europe at the moment, they're trying to get into like 10 to the 21, 10 to the 22, and actually investigate vacuum pair production.
So with the argon add mixture into the gas, you got a monoenergetic spectrum more or less. So you see what energy you get, or does that generally affect the proton?
So I am not an expert in the wake field acceleration. That is work from colleagues of mine, and I don't know the answer. Is the short answer to that. But I think that you can. There's so many variations that you can make to the density, the original density of gas, the atomic percentage that you're putting in. I imagine that there's some way, there is a way to sort of tune that. Because the way that this acceleration mechanism works is basically the gas that the laser is propagating through is underdense, so the laser can technically make it all the way through. But as it ionizes, because of the high intensity, it immediately ionizes it, and it creates a wake, essentially a plasma wake in the back, and the electrons get trapped in this wake and are accelerated over short distances. Now, when you add this other gas in there, the mechanism is called ion trapping, and I don't know exactly what that means, but it changes the way that the electrons are accelerated.
Any other questions? Okay, let's thank Mario again. And our final speaker this morning
I think it's...
and he's going to talk about ETA, the first light instrument for the GMT.
Do we have...
Clicker? We lost a clicker. Mario? Do you have a clicker? Do you have a clicker?
I set it back up there. It should be on the stand.
Oh, here it is. No, it's for the window. Oh, sorry. Thank you. There you go.
What is the laser pointer?
This one's the laser right here.
Okay. I can't see me. Okay.
Hello, I'm Sagi Ben-Ami. This is my second year as an Einstein Fellow, and apparently going to be the last one because I'm moving to a position at the Smithsonian. I'm an instrumentalist, which means that I build instruments. And the instrument that I'm going to present today is an instrument that we are building at the Smithsonian. It's the GMT Consortium Large Earth Finder. And I have an hidden motivation for you guys, and that's since probably most of you, at the time that this will start running, will be young faculty members somewhere, then you are the guys that actually should think of really unique ways to use the instruments that we are building. So it's up to you to actually make good use of what we are coming with. So think about it, because 2022, it's far away ahead, but not that much when you actually think career-wise. So first of all, the Giant Magellan Telescope. The GMT, Giant Magellan Telescope, is one of the 3 next-generation telescopes that are envisioned and I would say partially funded, not fully funded, for the next 10 years or so. It's a segmented telescope, which means that the primary mirror is not a single mirror. It's made of a couple of mirrors, 7 in our case. It's a Gregorian design. Those of you that actually care about those, I can explain that. Yes, afterward, it's made of 6 off-axis 8.4 meter mirrors and 1 center mirror, which is what you see here. This is the design, and this is an envisioned concept. I hope that they won't try to observe anything during the day, but I didn't make the picture. There's an urban legend about the 8.4 meter mirror. Why is that 8.4? I don't really know if that's true, but in general, the mirror lab, the biggest mirror lab in the world today, is in the Arizona University, State University, and it's located below the football stadium there. And the biggest gap that they could fit between the foundation of the stadium was 8.4 meters. So that's why telescopes are basically limited to that size of single mirrors. So everything is related to football in the US. In general, it's an f8.2 design. That's the ratio of the focal length to the diameter. So it's not a very fast telescope, which means that the field of view is 24 arcsecond. It's not very big. It's not a survey telescope. It's not the LSST. And the plate scale is 1 arcsecond per millimeter. So we have very high resolution in terms of angular resolution. Naturally, this thing going to have a very complicated AO system on it. The site itself is Cerro Las Campanas in Chile's Atacama Desert. And I guess that in the next couple of years, I will be visiting Chile quite a lot. What is the instrument that I am going to present? So the acronym GCLEF is for GMT Consortium Large Earth Finder, and I can tell you that it actually changed. The acronym didn't change, but what it means changed during the time. It's a general purpose visible Hess spectrograph that also have the capability to do precision radial velocity measurements. You can see here the optical design, and I will actually go over it in some more details at the end, closer to the end of my talk. It was chosen as the first light instrument for the GMT, and actually it's going to be the only instrument for the first 3 years or so of the telescope. So if you can actually really think about interesting science to do with this instrument, it's actually going to be on the world's biggest telescope for 3 years. So you have a really, really nice resource, and you should think of ways to use it. What are the science cases that we envision? So from the name, it's a large Earth finder. So we are looking for exoplanets. So there's the test mission that actually going to close the gap between what you see here, and I think it's blue, by the way, all optical instrumentalists that I know of are colorblind, which is really, really weird but what can we do? So in blue here you can see the data from Kepler regarding the radius and the magnitude, and as you can see, those are quite faint. Those are really, really hard to follow with modern instruments. They are almost impossible to do spectroscopy on. But with the test mission that is supposed to be launched in 2018, led by our neighbors across the street at MIT, we are actually going to close the gap and try to look, we will find transits closer to Earth at magnitudes of 8 to 12, and those will actually be able to follow up with modern telescope, with the next generation of telescopes. Our limits in the term of radial precision velocity is 10 centimeters, 0.1. And you can see here from the table, so in white here is what we, here, what you see here on top is actually things that we can already find today, already can measure the mass of today with modern instruments. But you can see that we are actually opening a new window into weighting exoplanets with this instrument. So we'll be able to measure, for example, Earth-type planets at a radius both of 0.1 from the host star, but also at a radius of 1 AU from the star. And that's actually really, really interesting, because maybe we can find terrestrial planets at the habitable zone, and this is, the holy grail of all this field. Another very interesting thing is to try and find oxygen O2 lines in transmission at the spectra of exoplanets, and those are mainly between 7600 and 7700 angstrom. And I don't know if there are any optical observers here, but those that are know that this is a very problematic band, because it's exactly in the A band where there are a lot of absorption in the atmosphere. Okay, you can see actually the transmission curve of the atmosphere here. But because if we'll have a high enough resolution and we have a transiting planet, we can actually try to look for the O2 lines as they move in and out of those transition windows. So with high enough resolution and high enough signal to noise that we will be able to collect with a 25.4 meter telescope, we can actually also look for those type of things. And this is really, really interesting, because if we can find a planet that actually has O2 in its atmosphere, then maybe we can find our cousins. I saw the Scientology movie yesterday, so I'm a little bit influenced. I'm looking for Zeno. So it's not only exoplanets. We are, in fact, a general purpose instruments, and the main idea is also to look for other things. We are going to be the only thing on the telescope, on the biggest telescope in the world at the time of when we are deployed. So another interesting thing is near-field cosmology. We will look for hollow stars that have a very low metallicity. The fact that they have very low metallicity means that they were generated from primordial gas, probably either generation 0 or generation 1 after the Big Bang. We can try to understand the enrichment of gas with heavy metals after the first generation of supernovae from population 3 stars, and so on and so forth. And this is actually, in my mind, this is the most interesting thing that we will actually be able to do. And since I was, during my PhD, also working on supernovae, this is another thing that I thought of, flash spectroscopy of supernovae. So we are actually going to operate at the same time of the LSST. And we are even not that far away from the LSST. Both of us are in the Chile Atacama Desert, so to speak. And we can actually receive trigger from the LSST about, look, we found a supernovae 5 minutes old. We didn't see it 5 minutes ago, and now we see it. And we can have a very short deployment time for our instrument, so we can try and slew into the target. Oh, that was echo. Slew into the target and try to see flash spectroscopy right after the explosion, where you have a lot of signature from the CSM and can collect very unique information about the progenitor itself and the environment right before the explosion. It's actually already been done by Galliam et al., but with the LSST we will have a lot of more chances to actually collect that because of field of view and because of the magnitude. So I hope that I convinced you that you can do many, many things with such an instrument, and I hope that you can also think of yourself of more things to do, but let's try to understand how we take those science requirements and actually say, okay, what do we want from the instrument if this is what I want to do? This is the first thing that you say, that you think of when you come to design an instrument. So first of all, if you want to do abundance studies, those are mainly iron lines. Iron lines are closer to the blue end of the visible spectrum, so we want a very high response at the blue end of the spectrum. On the other hand, we also want to do some cosmology. I didn't talk about it, but We also want to do some gamma ray burst science, Lyman alpha breakout, and so on and so forth. So we also want to do very good in the red side. So basically, we want to cover the entire visible waveband or whatever we can get. Okay? We want to do PRV. PRV means that we need to be very, very stable. No, shit, really? We want to be very, very stable. We want to know that the accuracy that we have on the wavelengths will allow us to actually measure 0.1 meter per second, and that means that we really need to have a stable instrument. You'll see how we'll do it. And we also thought about detailed chemical composition behind the local group, and for that we also have a mode of multi-object spectrographs. This is our instrument, so this is our telescope, and in order to achieve that, what we are doing, we have a spectrograph that is actually located in a thermally isolated, non-invariant gravitational environment on the side of the telescope. So we are on this rotating platform, but we don't change in the gravitation vector. We are also in a vacuum environment, and the entire instrument is stabilized to 10 to the minus 3 Kelvin. So we can be sure that whatever goes into the spectrograph is always stable and doesn't move. There are many aspects to that, and I won't be able to get to all of that. Another interesting thing is to cover the entire waveband, 3,500 to 9,500 angstrom. Those of you that know a little bit optics know that this is very, very hard because of the change of the index of refraction in glass with wavelength. Another thing is that we want different resolution elements. For PRV, we want a resolution of 100,000, but on the other end, it will harm our signal to noise if we want to do metallicity measurements. And that's why we want to have different modes to actually feed the spectrograph, and we do it by feeding the spectrograph with core diameters, with fibers of different core diameters. And that's because delta lambda is proportional to the image of the core diameter on the detector. P is the plate scale, by the way. We're going to have 5 different modes, 2 PRV modes. One of them is scrambled and one of them is not. We are going to have a medium resolution with 35,000 resolution. Going to have an high throughput mode with 20,000 and a multi-object mode. I won't go into how we feed the spectrograph, just that, because I have a minute or so. At the end of the fiber input, we actually create a slit. So it works like a slit, but it's a pseudo slit because there's no actual slit there that limits. What we are creating is with image of the fibers, and these two here are the PRV modes, while this one is the medium resolution mode, and you can see the highest core diameter. That's for the high throughput mode, because if we have a larger diameter of the fiber, we collect more light. Okay, so those are the slits. Each time only one mode will be fed according to what the science is that we want to do. If we are doing PRV and we want to be very exact, we will do the scrambled, which is this one. While if we want to do metallicity, then we will go with the MR mode. And we have a rotating platform that chooses what fiber actually is fed by the telescope. Regarding the optical design itself, fibers are going from here. Are creating the slit here. Then light is hitting a collimator and a grating. This is an shell grating. It's actually the biggest shell mosaic ever built. We are working with a company called Richardson Grating, which is not really fun to work with them because they're a little bit problematic, but what can you do? It's a 300 by 400 millimeter mosaic, 3 pieces of gratings. In fact, the alignment of these gratings of the mosaic with one to the other need to be really, really exact, and a very smart engineer that works with that's really did a nice job to actually align that. Another thing is because this grating works as a shell, means that the angle with respect to the beam is very, very high. The beam input on the shell itself creates a cylindrical beam footprint. And for that, we need to correct it at the spectrograph, at the camera, because that creates a lot of aberrations. We solve that with a Mangan mirror, which is a double reflection mirror. It means that it's actually a cylindrical lens glued into a mirror, and that actually is located here and corrects our image. There are many, many different aspects of optical design that goes into that you need to actually think about. Cameras, we designed the cameras in-house. I really don't have any more time, so I really should run over all of it. Whenever you create those, you always think, oh, I'm finishing in 5 minutes, but it's never the case. At the end of the day, what we have is those really, really nice shellograms on 2 different arms. What you see here is the red arm, okay, and this is in the PRV mode. As you can see, we cover for the red arm between 550 to 950 nanometer or so, and this is a focus on that. You can see the 7 fibers that are the PRV mode. And on the other end, we will have the blue arm. We are feeding both arms simultaneously. And for the blue arm, we are covering between 350 and 550 nanometers. And you'll get, again, the same, a similar shellogram, not the same. So with a single instrument, you can get a very high resolution from 350 to 950 simultaneously. Again, we are the first light instrument. So if any of you young scientists will think of something to do, feel free to send me an email. We are still rewriting the science book all the time. And my boss just stepped in like at the last second, which is great because you didn't hear what I say and I could say whatever I want. Okay, but his wife is here, so it's not true. Thank you very much, guys.
People at EASL have been secretly terrified that there's an unspoken of catch-22 with high-resolution optical spectrographs on extremely large telescopes. And that is that the Coude trains, or your fibers, are so incredibly long because the telescopes are so enormous, like the domes are the size
Okay, so our fibers are just 17 meters. It's not that long. Yeah. So it's true that from the VLT, they have like a fiber arm that is very, very long. On the other hand, usually when the fiber arm is very, very long, most of your absorption is in the blue end and not in the red end.
I mean, the problem on the ELT is that the fiber would need to be so incredibly long.
Yeah, they are like 250 meters. Yeah, they are like 250 meters or so, right?
But you're able, yeah, it's ridiculous.
Yeah.
You lose tons of photons at the end of your fiber, and you might as well just have it on.
Yeah. By the way, one of the nice things I think that we have is we will have the capability to actually replace the fibers as time goes on. So if in 10 years someone comes and tells us, look, we have this new amazing fibers that has 100% transmission at all wavelengths and actually multiply the wavelengths by some kind of magic, I don't know what, then we will actually be able to come and take out the fibers and replace them with new ones, and that's it. So
you're able to maintain this stability even though your instrument's sitting on the azimuth disk and rotating with the telescope?
Yeah, in general, so, it won't bump up and down, and we do make all the stability tests that we can make, and we have gone through a full structural analysis to make sure that this is the possibility. That's the hardest thing in the instrument. I don't argue about that, but we are able to do that. And it's true what you say about, 250 meters is not 17, and unfortunately, there is a range that you start losing a lot of photons. Yeah?
Question about the supernova follow-up. I mean, LSSP is going to be collecting 100 supernovae per night. Which ones are you going to actually go after? And does it matter that I can, follow it up within 5 minutes if I'm say using the telescope to do something else at the time?
So first of all, the GMT is going to have a TOO program. So let's say that you submitted for supernovae a TOO program and you have 3 triggers to work with during the year. Whenever you want to trigger, you will get it, but you will think for yourself, what are the triggers that I want to work with, because I have only 3. For example, I have an HST trigger, but I have only 1 per year, so I don't shoot it on everyone. The second thing, I would say, as a supernovist in my past, that I will look at previous image, make sure that I know that this is a supernova, that it's not a circumnuclear event, and that I have good enough limits from telescopes around the world that I can, someone observed the same spot in Africa 5 hours ago and there was nothing there, and now I see it in the LSST, so let's trigger it because it's apparently a very young supernovae that happened in the last 5 hours or so. Okay? There's another program, by the way, that I'm part of, which is a UV ogler on the sky, which is supposed to take a very large field of view and just look at it continuously for the shock breakout from supernovae. If that mission will be simultaneously with this telescope and with our instruments, and I don't know if it will or not, I don't know if it will even be approved, then this is even a better way to do it, because if you get the UV signal from the supernova, then you really know that, okay, this is a shock breaker, this happens in the last hour, or the last day if it's a type 2 supernova. And then there are many different ways that you can think of with future instruments and future telescopes and satellites to actually do TOO programs. Right?
Any last questions?
Are people already working on the other end of the fibers, like multi-object positioners or anything like that?
So we do have a multi-object mode, but we are not working on that. That's an Australian group that is located at ANU in Canberra. They are working on that. I think that when we will start, we actually won't have that option, but only a couple of years afterward. But everything is being worked at, everything is being thought of.
Okay, I'd like to thank Fabio again, and also all of the morning. Starts again at 11.
I just wanted to mention that Carol Bengalewski is here, and she is your
that in your pocket. Yeah, whichever one. And then click that on your lapel.
Is that about right, or da la la la?
Oh, there you go.
Okay.
That's not muted.
That's not muted at all. And this is.
There you go. Someone will key you up.
Thank you.
An email with
Okay, everyone should please take their seats. It's the second session of Einstein Fellowship Symposium. The first speaker is Simon Bird, simulating effects of massive neutrinos on wide-scale structure. Please.
Thank you. All right, so hi everyone. So I'm going to talk about massive neutrinos and measuring their mass. And like the basic point of this talk is to convince you that this is a sensible thing to do, and that I have some method for doing it which actually kind of works. And then next year, I'm going to tell you that we did it and everything's great, right? There we go. Okay. So why should you care about the neutrino mass? So we know the neutrinos are massive, but we don't know what the mass actually is. And there's this quote from Ernest Rutherford about science being either physics or stamp collecting. So in this vein, I would like to have you imagine that Ernest Rutherford has this large stamp collection, which contains the masses of all the fundamental particles, but there is one stamp missing. It is the neutrino mass. His life is miserable until he knows this final value. That is what we're going to do. More concretely, we know the mass difference between the neutrino species because of neutrino oscillations, which won the Nobel Prize a few months ago, weeks maybe. We know the mass difference between two species, so we know that they're massive. We know they have a non-zero mass. We don't know what the total neutrino mass is. This is really quite difficult to measure. And the reason it's quite difficult is just because of this mass scale. So the mass scale of neutrinos is like 0.5 eV. And that is much, much less than the mass scale of the electron, which is 511 keV. So, whenever you're trying to do a particle physics experiment to measure, the energy loss from the neutrino mass, you have to be unbelievably accurate. So the solution to this problem is not to do that. The solution to this problem is to do cosmology instead. So cosmology, we have the advantage that we have a very large number of neutrinos. We can measure neutrino background. There are lots of them everywhere. And so we have a handle on this. What do I mean about neutrino background? So neutrinos are created at Big Bang nucleosynthesis. There's about one neutrino for every photon. They spawn at a ratio of about 10 to the 9 at temperature of 1 MeV. And when they spawn, they're relativistic. So they come up with a very high initial energy. And today, this is their energy. So this is the neutrino mass divided by a factor of about 50. So for a neutrino mass, a total neutrino mass of 0.5 eV, they're maybe 1% of the energy density of the universe. So that's 1/25 of the cold dark matter, 1/25 of the dark matter, and about 1/4 of the baryons. So these things are not an insignificant portion of the universe, but they're also not a particularly large portion of the universe. But how are we going to measure this? So, we can't detect neutrinos directly. We can't detect neutrino background directly because they're too low energy to measure. And we know that there's some part of the dark matter, but we can't distinguish cold dark matter from neutrinos because we can't measure what cold dark matter is either. So the only way to do it is to measure it via their indirect effect on cosmic structure. So unlike the cold dark matter that we all know, neutrinos are hot dark matter. So they do not cluster on small scales. So this is a cold dark matter particle that's kind of sitting there doing nothing. This is a neutrino. The neutrino has some random thermal velocity, which it inherits from when it was created at Big Bang nucleosynthesis. And this imposes some kind of thermal free streaming length. So the idea here is that you're measuring the matter power spectrum on some small scale, some fraction of the cold dark matter, 1/25 of it, is not clustering. And this damps the total clustering of the matter-power spectrum. And you measure this effect, boom, you have neutrino mass. So that's going to be the thing that we're going to be trying to do. Right. So this is still kind of hard, right? 1% of the 1% of the cold dark matter of the mass density of the universe is still a small effect that's hard to measure. The lower mass limit for neutrinos is 0.05 eV, for which we need the matter power at the percent level. So I'm not going to talk about this problem. I'm going to talk about an easier problem, which is how do you even quantify what the effect is to a sub-percent level? How do you even do that? Okay, so this is, here I have done it. The problem is solved. So this is the ratio of the matter power spectrum with neutrinos to without neutrinos, so everything cold dark matter. This is from a neutrino mass of 0.3 eV at redshift 0. And this dashed black line is what you expect from linear perturbation theory, which is the same thing that you use in CMB codes. And you can see that there's this plateau here. So this plateau is the thermal free streaming length neutrino today. So today, they do not cluster on any scale smaller than this. And this slope here is, as you go to larger and larger scales, here they've been not clustering until almost present day. Here they've been not clustering for half of the time of the universe. Here they started clustering, almost initially. These guys here are the results of some n-body simulations, these solid lines, this red and orange line. The point I want you to take away from this plot is that the effect is much larger on smaller scales. So the smaller the scale you go to, the bigger the effect, the better the constraints you get. And if you use any kind of nonlinear probe, you also get a larger effect. And this is because nonlinear growth is faster than linear growth, which kind of accentuates the effect of anything not clustering. Okay, so what have I done to get these pretty lines? So we want to simulate things in the nonlinear regime. We want to simulate nonlinear structure growth. We know how to do this. This is an n-body code. So the obvious way of doing this is to say, okay, we have some dark matter, and we have some dark matter that moves quickly, which is neutrinos. So let's just do n-body. We have one n-body species, which is dark matter, one n-body species with neutrinos, and you can do this. This is what it looks like. This is cold dark matter. You can see there's lots and lots of structure here, clusters, galaxies, everything going on. And this is the neutrinos, and you can see there's not a lot going on. They just kind of blob around. They don't really cluster much. So this is great, but it has some problems. It has two problems. The first is that it only really works for large neutrino masses. And this would be wonderful if the neutrino mass was large, but the universe is naturally intransigent and prefers to pick values that are unhelpful for us. And so this is, the current limits are about 0.2, 0.15. So this is something we're now pushing into a regime where this method doesn't really work at all. The second problem is that you're discretizing your neutrinos. You're taking each neutrino and you're kind of lumping 10 to the 10 of them together to make one n-body particle. And this naturally introduces some kind of inaccuracy, which is the short noise inaccuracy. And the inaccuracy can kind of lead to a spurious clustering signal. So that's a problem. And the third problem is that we have all this machinery to resolve all these very, very small structures in CDM. And if you're looking at neutrinos, there aren't any structures there. So all this machinery, all this very complicated machinery for which we pay a computational cost is not needed because there's nothing happening. These things aren't clustering. So this is kind of wasted effort. Right, so this is, again, some more problems. So this is because this is what I said before about discretization of the neutrino species. Also, at very early times, they're somewhat relativistic and they don't redshift like matter anymore. You can't include the fact that there's splitting between heavy neutrinos and light neutrinos. And this is what I said earlier, actually, that these simulations are just hard. They're unnecessarily difficult. You're making your life difficult by doubling the number of n-body particles you have. So you don't want to do that. So the solution is to imagine, what is it that these neutrinos are actually doing? Because they're moving quickly, they're not driving the clustering. The clustering is all being driven by the cold dark matter. So from the point of view of a neutrino, what you have is you have a static potential, the cold dark matter potential, and the neutrino zips into it, zips out again if it has enough energy. If it doesn't have enough energy, it gets captured. You can describe this with perturbation theory, it turns out. So what we do is we say, okay, let's just take the potential world from the cold dark matter, which we know because we have our n-body code, which is computing clustering. Let's take a perturbation theory integral, find out how the neutrinos cluster in this potential, add that back in, and then we get the total matter power spectrum. So this seems quite reasonable. How does it work? It works extremely well. This is the error for a very large mass neutrino, where the particle method should work pretty good, and the linear theory method you might expect not to work so well. And it works, it works really well actually. It's like a 0.2% accuracy, which is way smaller than the accuracy than the error on the n-body code. If you go to smaller masses, it works even better. Here the error is less than 0.1%, and the dominant effect here is actually discretization noise from the particles. So this is something which is working fantastically. Even better, thank you. Even better, this is public code. So it works in the small mass limit of neutrinos. It has the same cost as cold dark matter. It's public code. So if you're thinking, oh my goodness, I have this experiment, I would like to measure the neutrino mass, this is what you should do. Go to this link, download it, apply your patches to your favorite n-body integrator, and behold, you'll have neutrinos. This is a picture of my collaborator, who is French, and he is a very nice guy too. So if you want to talk to him about it, you should do that. Okay. So hopefully now I've convinced you all that next time you're thinking, gosh, I really want to measure neutrino mass, this is what you're going to use. There are some other methods, but this is the one to do. So quickly before I finish, you might want to apply this to certain experiments. There are some things that are the most promising way of getting neutrino mass out. The first of these is cluster counts. So cluster counts are really quite useful in principle because they probe very small scales where the effect is largest. They're at redshift 0 where the effect is largest. And the cluster count scales like sigma 8 to the 8. So if you change the matter power spectrum by even a few percent, you multiply that by power of the 8, you take that to the power of the 8, the effect is suddenly very large. The only problem is the clusters are kind of complicated, as you all know very well. If they weren't complicated, if we all understood clusters perfectly, we would have a neutrino mass measurement from this right away. So I encourage all of you in the audience who work on clusters, if you've solved the problem, that would be fantastic. The next effect that you might look at is weak lensing. So weak lensing has the advantage that it probes very, very small scales, which gives you way more power. You might also want to look at the Lyman alpha forest. Lyman alpha forest is great because it probes low densities. Low densities mean that there are fewer systematics. And the final one is CMB lensing, which is just powerful because the CMB is generally a good way of measuring things. So all of these things are possible ways of measuring the neutrino mass. If you add them all up and you take, okay, let's say there's a 10% probability of measuring from this one, 10% probability of measuring from this one, 10% probability of measuring this one, and you compute that and you say, okay, how long is going to be the expected time to measure the neutrino mass? It comes out to about 5 years or so. So it's very likely that we're going to measure this soon. We have the methods to do it. We have the experiments coming up. So stay tuned. Thank you.
So some people were claiming that with large-scale structure, not only could you in principle get the total neutrino mass, you could get the 3 mass eigenstates. Do you agree? Is that possible?
It's possible in principle, but it's very, very difficult. So maybe I have a plot. Okay. Let's go back to this guy. Okay. So this guy is assuming a degenerate hierarchy. If you want to get a measurement of the eigenstates, the difference between the inverse hierarchy and the normal. There are 2 states. One has 2 light neutrinos and 1 heavy neutrino. One has 2 heavy neutrinos and 1 light neutrino. The difference between those 2 states is actually maybe 0.1%. So it's very difficult to measure. The way you would get it is that you would measure a limit on the total mass below 0.1 eV. And at that point, there's only 1 state left. If you have two heavy neutrinos and each neutrino has a mass of 0.05 eV, they add up to more than 0.1. So then you get the hierarchy, the eigenstates indirectly. And I think that's the way you're going to do it.
More questions? So I have a question on if you want to compare the cluster counts and the neutrino cosmology, can you use this perturbative theory, or do you need to do something extra to compare the cluster clubs?
You can actually use, do I have a plot? You can use the perturbative theory. Okay, so galaxy clusters kind of work around here. The reason you can use the perturbative theory is because in the middle of galaxy clusters, yes, the neutrinos, it's very overdense, so things are clustering non-linearly. But there's so much else going on that the dark matter starts clustering even substantially more. So it does actually still work. And what you find, where is it? No, okay, I don't have it. What you find is that the effect of neutrinos is actually well described by just taking this thing in and running a simulation with different initial conditions.
So
it works very fine.
Like the red power spectrum as the initial power spectrum for computing nonlinear collapse and follow this.
Yeah, and you follow this method and it works very well, which is maybe surprising, but yeah, it still works. We checked explicitly.
We're like listing different, you have a list of different ways to measure this, and you said like if you add it all up, you expect to measure things within 5 years. Could you tell a little bit more about each of which of them will dominate? What is the problem in this list, and why is it that you cannot only just focus on one, or like, could you tell about where's the power coming from?
I mean, you shouldn't focus on one because ideally you want to measure it from multiple experiments, right? The cluster counts are, to take them first, are very powerful, but there's a lot of stuff going on. You need to understand clusters very well. Weak lensing, in principle, it's a measurement of the dark matter distribution, directly, more or less. But to understand it, you really need to be able to understand how the systematics involved in measuring galaxy shapes. And that's a problem which hasn't actually been solved. So if at the point when people make weak lensing really work and really get compelling measurements of the power spectrum onto the small scales, they will get neutrino mass for free. But that's not something that has fully been realized yet. So I don't, that's something you have to ask a weak lensing expert. The Lyman alpha forest actually is the current best constraints on the neutrino mass. So the constraints here are about 0.12 eV. So in principle, the Lyman alpha forest has almost already measured it, actually. The only problem is that people, the analysis is kind of complicated. The analysis involves its own specific type of n-body simulations, and it's not totally clear how robust that is at the moment. CMB lensing, I know very little about. If they can get it through CMB lensing, they'll get it in the next couple of years because that's when the experiment's coming out. In some sense, if you look at the Planck likelihoods, there's some argument that there is already a neutrino mass signal in there. If you look at the lensing, the constraints on the lensing power from Planck, you will find that it's peaked at a value which is less than 1, which is probably just a systematic. In fact, it's almost certainly just a systematic. But like, if you would take that peak and you would just shrink it in place by a factor of 4, then you would suddenly get neutrino mass.
What is the multiple that you have to be signal?
I don't know that off the top of my head. So I don't know that. It's the lensing multiples work on a different scale. So I don't know the conversion factor. Not sure.
You're talking about high multiples because you want to be able to crystal illusion.
Yeah, probably.
Just wait until the service is having good enough statistics that they're very high multiples.
That's why it's better done with part than
So actual and things like that.
Hello, everyone. My name is Liang Dai from Institute for Advanced Study, and it's a great pleasure for me to visit CFA as a new fellow. And today I'll be talking about a formalism called separate universes, and it is used to understand how galaxy clustering happens on very large scales. So the observation of how galaxies are distributed on ultra-large scales is actually a very interesting thing because it holds secrets to the beginning of the universe. So to date, the understanding is that this large-scale structure formed out of tiny density fluctuations in the very early universe. But how come we have these perturbations in the very first place in a quite homogeneous, isotropic, and flat universe? One elegant explanation is that the universe underwent a period called inflation. That means space itself is being stretched exponentially fast. And then after this period ends, the universe becomes dominated by radiation and non-relativistic matter. It still keeps expanding, but the expansion slows down. What's remarkable in this scenario is that actually during this first accelerating phase, quantum fluctuations in the energy density is unstable, so that this perturbation can grow big and become some macroscopic perturbations. So if you look at some fixed co-moving wavelength of a given perturbation at very early times, the wavelength is smaller than the size of the horizon, so it's in the form of just quantum fluctuation. But once the wavelength gets stretched to superhorizon scales, it becomes amplified, and then the dynamics is frozen until at later times, once the co-moving horizon scale becomes large again, these perturbation modes enters the horizon and start to evolve. And they give you the observed anisotropies in the CMB and also the inhomogeneous distribution of galaxies. So the typical prediction is that these primordial perturbations have Gaussian statistics. But unfortunately, that doesn't tell us much about the underlying physics of inflation. Actually, what is more informative is the departure from Gaussian statistics, because that will tell us new physics beyond the minimal scenario. So there are basically two ways to get this so-called non-Gaussianity. One is that you have strongly interacting dynamics for the inflaton field. The other possibility is that there are other dynamical degrees of freedom that are very important during inflation. And then the target for measuring this, the simplest target would be just measuring a 3-point function for the primordial potential. So these three modes, this is called bispectrum, these three modes should form a triangle because of statistical homogeneity. But there can be many different shapes. If all three wavelengths are comparable to each other, you get equilateral or folded shapes. But you can also have so-called squeeze shapes in which one wavelength is much longer than the other two. And for each shape, you can measure the bispectrum with respect to two powers of power spectrum described by this FNL parameter. So the state-of-the-art of measurement of these parameters provided by the recent Planck satellite measurement of the cosmic microwave background. So this first type of triangle is of more interest because first of all, it is actually the easiest shape to probe using galaxy clustering information. And second thing is that it has simple physical interpretation, which is the short-scale 2-point correlation is being modulated by a long wavelength perturbation. So people realize that if we have sensitivity for FNL of local type to order 1, we'll be able to rule out a large class of non-minimal models. And very fortunately, this level of sensitivity is achievable by forthcoming experiments. So for large-scale structure, we rely on some proxy of the primordial perturbation. So basically, we can measure the distribution of dark matter or distribution of the galaxies. So naively, we just measure the galaxy bispectrum and extract information on primordial non-Gaussianity. But in reality, this will be complicated by a bunch of late-time effects. So one effect here is that once the mode enters horizon, the evolution is described by nonlinear gravitational collapse, so that you generate new bispectrum. And then even if you observe a Gaussian distribution of galaxy at some source redshift, you have so-called projection effects, meaning that the observed position of the galaxies will be different from its true physical position, and that also introduces new contribution to the bispectrum. So these two effects have to be accounted for if we want to extract information on the initial condition. So people have realized that we can measure local type primordial non-Gaussianity using galaxy clustering on very large scales, using so-called scale-dependent galaxy bias. So to understand how it works, we consider long wavelength perturbation and then focus on a small patch whose size is much smaller than the wavelength. Then we can ask what will be the abundance of galaxies within this patch. There are two ingredients. One is that initially there's a power spectrum on small scales. But for Gaussian initial condition, that has nothing to do with the long wavelength mode. So it's the same everywhere. But then these perturbations will grow big and collapse eventually to form objects. And this process is affected by the background perturbation. So intuitively, you can imagine that it depends on the background density and also depends on a possible tidal field, anisotropic tidal field. And therefore, this argument leads you to the conclusion that the galaxy perturbation should be linearly proportional to the underlying matter perturbation. That's the scale-independent bias. However, if we have primordial non-Gaussianity, then this initial perturbation, the initial power does correlate with the long mode. And therefore, the galaxy perturbation will, in addition, trace the primordial potential field and proportional to this FNL parameter. So observationally, you measure the galaxy clustering power spectrum. Without this piece, it will just be a constant offset with respect to the matter power spectrum. But now with this new piece, you get an enhancement on large scales. And the reason is that the potential has a much redder power spectrum with respect to the density due to the Poisson equation. Now here's an interesting question, which is, we have relied on Newtonian argument, but in full general relativity, potential is as important as the density, as large as the density perturbation. So is it possible that in full general relativity, we have an extra piece proportional to the potential and therefore have a enhancement on large scales that mimics primordial non-Gaussianity? To figure out this problem, there's a very useful intuition called a separate universe picture. So basically, we can consider a homogeneous flat universe, but then there's a overdense patch within a finite radius here. So the evolution of this patch will be identical to a different homogeneous universe, but this time with a density larger than the critical density, and with a positive curvature. In fact, for an observable sitting inside this patch, there's no way for him to distinguish between this scenario and the scenario that it is actually an overdense patch in a flat universe. Note that this observation is exact in full general relativity. The size of the patch can be actually arbitrarily large. So this tells us that probably the effect of a very long wavelength perturbation in full general relativity just reduces to a redefinition of the background cosmology. So in order to prove that, we construct the so-called conformal Fermi coordinates. It's a coordinates in which this intuition becomes manifest. So it is related to the well-known Fermi normal coordinates in general relativity. So the construction of the Fermi normal coordinates depends on the equivalence principle, which says that in a free-falling elevator, you don't feel the gravity, and therefore the only local physical effect is due to the double spatial gradient of gravity, of the gravitational potential. So you can construct a local coordinate system that is flat up to quadratic corrections. But in the cosmological context, we want to add a scale factor here to account for the fact that the local space-time is expanding. So in this coordinate system, you can construct this coordinate system and find that all the general relativistic corrections are absorbed into the effective scale factor, expansion rate, and the curvature. And what is left as the correction remains in the Newtonian form. And this is very useful because it tells you that actually there's no relativistic corrections that that galaxy formation can depend on locally. So the advantage of this coordinate system compared to the usual FNC is that it can be extrapolated to superhorizon scales without breaking down. And this is basically because we absorb all these terms into the effective expansion rate. So the condition for this picture to be true is actually very simple. You need all fluids to commove along geodesics, so that which means only gravitational force is important, and you don't have anisotropic stress. And these conditions can be approximately met if you have if your sun horizons are smaller compared to the wavelength of the perturbation, or if the exotic fluid you have behave like dark energy with W equals very close to -1. So you can use this coordinate system to do calculation to see how long wavelength perturbation can evolve, can affect the dynamics of short wavelength perturbations. What you find is that formally they satisfy the same set of equations as in the Newtonian limit. But then this result actually is valid to arbitrary scales as long as you know how to interpret it. So the key is that the density must be interpreted as the density in synchronous gauge, and the gravitational potential is the one in conformal Newtonian gauge. But then up to this mapping, the result is identical to the Newtonian result. So that solves a previous confusion, which is that general relativity, whether or not general relativity can induce effective FNL of local type non-Gaussianity. So previously, people do second-order perturbation calculation and found that the local power spectrum can be modulated by the presence of the long wavelength potential perturbation, and therefore you generate a scale-dependent galaxy bias. But actually, the interpretation was incorrect because here you are not comparing at fixed wavelengths. You are not comparing at fixed wavelengths. And that's simple. That's simple to understand because a long wavelength potential perturbation is part of the metric. So that means because of the long mode, the proper distance is modulated in a position-dependent manner. So once you correct for that, you find that this modulation actually disappears. And therefore, the conclusion is that general relativity does not induce any scale-dependent bias, and it also does not induce any other correlation, any other scale dependence in the correlation of other properties of galaxies, such as halo galaxy shape. So the conclusion of our finding is that, first of all, galaxy clustering is a very promising probe to look for local type non-Gaussianity, and the interesting sensitivity level is of order 1. However, to achieve that requires understanding of galaxy clustering on very large scales using general relativity. So we constructed this conformal Fermi coordinates to show that the local effect of a long wavelength perturbation only depends on the double gradient of the potential, and therefore there's no scale-dependent bias induced by gravity. So if in the future any scale-dependent bias is discovered in galaxy surveys, that can be only the result of two possibilities. One is that we do have primordial non-Gaussianity, and the other is that it is purely projection effects, which is basically the propagation of light from sources to us is perturbed by space-time, by curved space-time. But I will emphasize that these two scenarios are observationally not degenerate, because one depends on the bias of the galaxy population, and the other depends on other quantities such as other selection effects such as magnification bias, evolution bias, and so on. So they are distinguishable. So this opens up a very promising possibility for future large-scale structure survey, that we can actually look for smoking gun of new physics beyond single field inflation scenarios. Thank you very much.
So does the effect that led to FNL minus 5/3 in the wrong units lead to a different effect in the units in these units, or does it just disappear entirely?
It disappears actually entirely, and because the reason, so basically, I explained that you are comparing at the same k, but that same k, so k is the wave number conjugate to some coordinate scale, but that is not necessarily the physical scale. So when you're comparing at the same k here and there, basically it is proportional to the, you're comparing at a slightly different proper wavelength. And therefore the difference is completely captured by the spectrum slope of the linear power spectrum. And then you find that basically the number for this slope gives you exactly this number minus 5/3. So this is basically the statement that in single field inflation scenarios, if you ask locally what would be my power spectrum, initial power spectrum on short scales, that it does not know anything about the existence of the long mode, because this patch and that patch, they behave in exactly the same way up to a time delay.
I remember reading some paper by Matthias that it changed the curvature of the local omega k as well.
So the only difference between this patch and that patch will be a curvature. However, if this mode is on very large scales, the curvature is proportional to the double spatial gradient of the gravitational potential, and that will be very small. And therefore, the bias you get is still scale independent. So you just have basically, actually, the dependence on curvature gives you the usual scale independent bias instead of the scale dependent bias. So it gives you the usual story of linear biasing. This bias parameter is scale independent.
So, have you been looking at what the effect is if you have like a modified GR? So I know there's many ways that you can modify but there is some simple ways to parameterize by some gamma. Like maybe, like the question is there like if you have modified gravity, would you see something like that you would expect to see in the squeezed limit in the non-Gaussianity? And if you can see the difference between these two things by, for example, that the rigid space distortion caused it to just instead of just the
So we haven't looked at modified theories of gravity. So here, our argument, of course, relies on something crucial for general relativity, which is that you have this equivalence principle. So if you can violate this principle, for example, if you have some additional force in modified theories of gravity that knows about this gravitational potential, then I think this conclusion can be violated.
How would you see the difference between the non-Gaussianity and the modified term? Do you have an idea how to see?
The difference between the sorry, which two terms?
The modification to gravity and the non-Gaussianity term in the squeeze limit. How would you be able to see these two different, like the difference?
So that depends on. So basically, they can have exactly I think they can have exactly the same shape, right? But then I think you have additional handles for modified gravity because you should have additional late time effects. So.
Probably also from the rigid space distortion spectrum.
Right. And for example, from weak gravitational lensing, because many modified theories, they predict that the two scalar potentials are different, so that the gravitational lensing will also be different.
Okay, we have to move on. Garrison Kimmel, our next speaker.
Okay, so thank you guys. This is my first year here as a fellow. I'm very honored to be here. I'm also very jet lagged because I got in very late last night. So if my brain shuts off at some point during this talk, please forgive me. So I'm going to talk today about something much, much smaller scale than what we just heard about, which is using local galaxy counts or counts of galaxies in local group to try to constrain the faint end relationship between halo mass and stellar mass. And this is work that I've done with Emma Barbwell, who's an undergraduate at Case Western, and my former PhD advisor, James Bullock, and Mike Bullen-Colchin at Texas. Okay, so the basis for our work is abundance matching. So let me just make sure that everyone understands what abundance matching is. Basically just says that we're going to assume a monotonic relationship between M star and M halo with some amount of scatter about it. To do this, you match up abundances. So you take halo number density from simulations or analytic theory, and you take galaxy number density from observations, and you say, well, these two, this starting at the massive end, this number density of galaxies matches up with this number density of halos. So we're going to say that this galaxy, that this galaxy lives in this halo. And then you just walk up this relation and get to draw a point on your halo mass stellar mass relation at each point that you connect these two lines. Now, if you do that smarter and you take into account some self-consistency checks, you get relationships that look like this. This is from Peter Baruzzi's 2013 paper. The different line colors just indicate different redshifts. What you can basically see is that, of course, you have, as we know, very inefficient star formation, particularly at the faint end. This starts to drop very rapidly. What I want to talk about, though, so let me emphasize, this works very, very well at all of the ranges basically plotted here. This gets us even the radial distributions and abundances of LMCs, which tend to live sort of in this region. So at large scales, this seems to work great. But I want to ask the question, what's happening at small scales? Does this line continue down like this? Does it break off much more rapidly? We don't know. So what I'm going to do, as I said, is use counts in the local group to try to test these extrapolations at the faint end. So an example of how we've done this before, this is again Peter Baruzzi's line, just exactly as he describes it. It becomes dashed where his observational data, which is basically SDSS, runs out. But we think we can constrain it down to basically this gray region with the local group. This is basically the incompleteness of the local group, a few times 10 to the 5. Now, if we just take this line and naively apply it to a set of simulations that look like the local group, look like the Milky Way and M31, specifically the Elvis simulations, which are just a suite of pairs of halos, basically, then we find that even in the complete regime, sort of around 10 to the 6, we're over-predicting our number counts by about a factor of 3. Right? This looks really bad. So we said, well, this looks terrible. Why is this happening? Well, as I said, Peter Baruzzi used SDSS to get this slope here. Basically, you plug in the slope of your stellar mass function and your halo mass function. That gives you a slope of your stellar mass-halo mass relation. We went out and we said, is there an updated faint end slope of the stellar mass function? Turns out there is from GAMMA, the Galaxy Mass Assembly Survey. If you just plug that new relation into Peter's formalism at the faint end, then suddenly you get counts that agree quite well with the Milky Way and M31. This all looks quite nice. However, there's a big caveat here, which is that both of these relations are assuming no scatter. Right? We're assuming a pure one-to-one relationship between stellar mass and halo mass. But we know that at higher masses there's at least some scatter. For example, Peter quotes 0.2 dex in M star at fixed M halo. So we want to ask the question, what is the scatter at the faint end? Can we constrain it with the local group? What are the implications of large scatter, for example, on extant problems in lambda CDM? And furthermore, can the scatter suggested by simulations of small halos of dwarf galaxies actually be correct? Will it correctly predict the local group when applied to abundance matching relations? So just to give you an idea of what I'm talking about, here again is just Peter Baruzzi's line in black. And I've applied a couple other relationships where I've just taken his faint end slope and tweaked it, much like we did before. So the magenta line, I'm going to assume 0 scatter about it. And the cyan line, I'm going to assume 2 decades of scatter. So this is a log normal scatter, and 2 decs here is just one standard deviation. Now, if we again apply these two relationships to the Elvis simulations, then we get the magenta and cyan lines respectively. They look pretty similar, and they both look like they match the Milky Way and M31 counts reasonably well, right? At least in, again, where we think we're complete. But if I take the cyan line and I again apply it to the Elvis simulations, but assume 0 scatter, then all of a sudden I get this dashed line, which, as you can see, way underpredicts the local group. Now, the reason for this is pretty simple. The halo mass function is increasing steeply as you go to the small masses, right? So as you increase your scatter, you're going to have more small halos scattering up into your complete regime than you will large halos scattering down out of your complete regime, right? So basically, a lot of these large galaxies are actually being hosted by very small halos that have just scattered up. Okay, so let's quantify this a little bit. This is our model. We're going to peg to Peter Baruzzi, as I said, at the high mass end, because again, this works very well. But then we're going to let a low mass slope vary freely, so log slope, I should say. That's basically what this green line is. And then we're going to assume a symmetric log normal scatter, and the sigma that I'm going to quote you is 1 standard deviation of that scatter. So we can now vary sigma and alpha. Here I'm showing you what happens as you vary the slope, so you can see everything just gets more or less steep. And then you can also vary the scatter, so here we are increasing the scatter and decreasing the scatter down to 0. Now we've tested a lot of other models, including one-sided scatter, a growing scatter, which I can show you guys if you're interested. These all yield qualitatively similar results. I don't necessarily have quantitative results for all of them, but the basic takeaways are all the same. So here are our results. The color here indicates the goodness of fit, so bluer is a better fit. The x-axis here is the amount of scatter that you assume about that relation, and the y-axis is the faint end log slope that you assume. So basically, you can see that there's a strong degeneracy between the slope and the scatters. You assume more scatter about your median relation. You must also make your slope fall off more steeply, right? This makes sense. As I said, more small halos scattering up than large halos scattering down. Now, this is averaged over some 12,000 realizations per pixel in this plot, basically, because I've done 500 realizations of all of the 24 Elvis pairs. There's a lot of statistical power here. They're qualitatively identical results if we use the local field, but we don't really understand the incompleteness out there as well. So this is just using the satellites of the Milky Way and M31. Okay, so what are some effects of this large scatter, for example, on extant problems in Lambda CDM? Well, one of my favorite problems in Lambda CDM is too big to fail. So let me explain real quickly what too big to fail is. Starting with the missing satellites problem. You guys are probably all familiar with this. You run a simulation of a Milky Way-sized host. You look around and there are thousands of subhalos, thousands of collapsed objects that naively should host galaxies. But you look out at the Milky Way and you see about 10. This is obviously closer to 30 now, but the basic premise is the same. There's a factor of between 100 and 1,000 mismatch between simulations and observations. Now, there's an obvious solution to this. You say, well, only the largest clumps are hosting galaxies, right? There's a lot of physics that can explain why this would happen. For example, maybe all the small clumps had all their gas boiled out of them during reionization. So the question is, does this work? Can you actually put these bright galaxies in the largest clumps that you see around simulated Milky Ways? And the answer is no, or else this wouldn't be a problem, right? So if you plot the constraints on the circular velocity from the Milky Way dwarf spheroidals, taken from basically their velocity dispersion at their half-light radius, and compare them to the circular velocity profiles of ultra-high resolution simulations of Milky Way-like hosts, then you can see that the subhalos of those hosts all have too much mass within sort of the half-light radii of the dwarf spheroidals to host any of the known dwarf spheroidals. Now, there are subhalos that go through these points, but they're all smaller than the subhalos that I've plotted here, which is, again, problematic because we assume the largest subhalos are the ones hosting the galaxies. So what happens to too big to fail when you assume suddenly that there's an enormous amount of scatter in your M-star M-halo relation? Well, this is what you get when you select by the largest mass that the halo ever is. This is basically the canonical picture. You say anything that's big enough to have gas fall into it, cool, and form stars is a halo that should be able to host a Milky Way dwarf spheroidal. You can see we have of order, I think, 9 that are completely unable to host any of the Milky Way dwarfs, and another 6 that are really only compatible with the 2 highest density dwarfs that we have. So there are a lot of problematic systems in this host. If we instead pick just a random realization and pick subhalos by the stellar mass that they've been assigned in this realization, this I think is coming from 2 decades of scatter, then you can see that what we've done is basically had a lot of our large halos, so let me just flash back and forth again. A lot of our large halos that we're living up here suddenly are hosting galaxies that we are incomplete to, right? So we don't think of them as too big to fail because we just haven't found their galaxies yet. We haven't found them yet. And I'll remind you here that the number of halos is roughly equal to the number of galaxies by design because I've set things up. I'm picking at the best fit slope, the best fit log slope, at each scatter. So I've set things up such that we should have the same number of systems in our observations as we do in our simulations. So that means that when I count up all, sorry, I forgot about this plot. So let me just illustrate specifically what's happening here, actually. This is one realization of the Milky Way that has no massive failures in black points. The green points, however, are the same realization but with 0 scatter. As you can see, lots of too big to fail systems, that is, things that are too massive, too dense, but live in the complete regime, which is indicated basically by this blue band, when you have no scatter. But when you turn up your scatter, suddenly you have realizations where lots of your classical dwarf spheroidals are hosted by halos with peak masses between about 10 to the 8 and 10 to the 10, rather than 10 to the 9.5 and 10 to the 11. And most of your massive problematic subhalos have scattered below your completeness regime. So, as I said, we can do this for all of the Elvis systems. Here is just counting up over all the realizations, all the scatters. Basically what I've done is each scatter For every host, I say what slope best fits for you at that scatter. Let's go ahead and pick out subhalos that live above the completeness limit and ask how many of them are massive failures in the sense of having too much mass within their center. Now at zero scatter, we average about 8, right? So this is the average number of massive failures, and down the bottom panel is the fraction of realizations with no massive failures. We'd like this to be 100. We average about 8, which is a major problem because, again, the number of halos and number of galaxies should be the same, and the number of galaxies in our sample is about 9, right? Which means every single halo, on average, just about every single halo that we assign to host a dwarf spheroidal of the Milky Way is not actually kinematically able to host that dwarf spheroidal. Doesn't work. When you turn your scatter up to about 2 decs, which is very, very large, but hey, you can. When you turn your scatter up to about 2 decs, the problem goes down by about a factor of 2/3. And more importantly, we now get of order 5%, or if you just bump all the Vmaxes for all your subhalos down in accordance with stripping out their baryons, of order 25% of your systems with no massive failures whatsoever. This is promising, right? This helps us out a lot. Now, question is the scatter actually this large? Is there any observational evidence for that? Well, we can't go out and measure M halo. We don't have velocities, for example, of stars at the virial radius, particularly for subhalos. So we need to look for indirect evidence of this. So one example might be very faint galaxies that are unquenched. So a lot of simulations recently, this is work from Coral Wheeler, have found that galaxies that are hosted by halos less than about 10 to the 9 are able to form stars, but they're shut off by reionization. So they're all quenched around redshift 2 or so. However, if something that is of order 10 to the 4 in stars is living in a halo that's of order 10 to the 10, it should be able to survive that quenching and keep forming stars until the present day. So we should see some faint galaxies that have late time star formation. From the simulation end, is there theoretical evidence? Does it work out? Here I've basically just thrown up, it's kind of hard to see the 2 sigma scatter, but whatever. Here I've just thrown up a whole lot of different simulations of isolated dwarf galaxies. These are all using different, well, same points, same color points using the same physics, but in general these are all using different physics, different feedback prescriptions. The general takeaway in the last minute I have that I want you to take from this is that maybe they're roughly sampling the upper edge of this 2-decade scatter by eye, which is what allows you to alleviate too big to fail. Again, large galaxies and small halos. But there's nothing sort of scattering below this medium relation, which is what you need in order to match counts. It has a huge caveat that we need a lot more simulations, and they need to be run with identical physics, and there is work ongoing here. Okay, so I think I'm out of time, so I'll just leave my conclusion slide up. Make one quick point. The most important takeaway from this, if you have a large amount of scatter in your simulations, you should not be matching Peter Baruzzi's line because you will overpredict the local group. I'll leave it at that. Thank you.
So it seems like you have a bimodal sort of behavior where you have the high mass galaxies have little scatter and low mass galaxies have a lot of scatter. Is there, you think, a continuum in terms of?
Sure. Yeah. So that's probably a more reasonable model. I didn't present that because, well, it's a little harder to interpret, but this is basically what that looks like, right? You assume something where you fix your scatter to what Peter says at the high mass end, well, high mass for me, and then you allow it to grow as a function of the halo mass. The general takeaway is, so here instead of, the x-axis is wrong here. Here instead of the actual scatter, it's the slope of that scatter. You can sort of read off the equivalent scatter at 10 to the 10 from the top axis. The general, as I said, the qualitative result is the same, that you need things to fall off a lot more steeply as you assume that scatter grows at the faint end. And you find the same results for too big to fail too.
So continuing along the same line, there are reasons to expect that, for example, there's more scatter in subhalos as opposed to scatter in
So that's sort of what I've been thinking about lately, is trying to think about where the scatter might be coming from. One possibility is that maybe your halo mass, your galaxy mass at these scales is fixed by your halo mass at some redshift 6 or something like that. If that's the case, then you would conceivably, I would think, expect less scatter in your subhalo population because they've stopped forming stuff. Well, let me think that through. I need to do that explicitly, actually. There's a lot of taking into account infall times and everything. It's going to be tricky.
More questions? Okay. If not, let's thank formation of star clusters in higher redshift universe. View on the prior cosmological Thank you very much. I actually changed the topic of my talk a little bit to try to expand the scope of my talk. So we'll see how it goes. I was a little too overly ambitious, I guess. So I am a galaxy simulator. I simulate galaxies forming on clusters, on computer clusters. So I'm going to present you sort of how the future looks like in the next decade or so in the galaxy formation community. So just before I go into that, I thought this will be a good chance to sort of reintroduce or introduce myself to the folks here. So this has been my orbit over the past few years. So I actually got my PhD from Stanford, and I was at UC Santa Cruz for about 2 years to work with Joel Primack and Mark Hermoltz. Then I was at Caltech to work with Phil Hawkins, and I just actually moved back to Stanford to do my third postdoc in 4 years already to work with Tom Aba. And if you look at this orbit, there is a strong indication that there must be a massive gravitational body at San Jose. That's where my wife has been working all alone as an engineer in Silicon Valley, and actually Grid's mass, already I spoiled my joke. It's growing in mass, and it actually became a three-body problem. So it's no longer analytically solvable. So that's why I study numerical simulations to predict where my next career path is. You know, it's really important. Enough about me, and actually I'm going to talk about the actual galaxy formation simulation done in with a numerical tools. And 2 points that I want to raise is that the new possibilities aspect, what's to come and what will be possible in the next decade or so, and the challenges, and what are the sort of pathfinder studies to have a sneak preview of what's coming up the next decade. So to simulate galaxies, you need multiple different ingredients. But most important stuff is obviously the star formation and feedback that's happening at like a parsec scale. But it has to be simulated in the context of a larger inner or intergalactic dynamics that's happening at megaparsec scale. So it's a large multi-scale problem that involves a lot of nonlinearity. So it requires a numerical tools. And the community of numerical simulators have benefited a lot from the advancement in computing technologies. For example, if you look at this supercomputing flops, floating point operations per second as a function of time, you can see it has been growing exponentially. So either combining the advancement in massive computing, massively paralleled computing technology, or just the pure advancement in the chip technology, we're going to see advancement. We have been seeing great advancement in terms of the mass resolution in a typical galaxy scale simulation. So here I'm plotting the mass resolution in a typical galaxy simulation in a stellar disk.
And we have come a long way in the days where the individual galaxies were represented by some 30 particles to today where the typical resolution that we're talking about is some thousands of solar masses. So we have come a long way. And assuming that the computing technology will evolve with the drivers like not by astronomy but by biology or energy industry, we can predict that this line will go down to, say, somewhere resolving the individual galaxies with, say, tens of solar masses or even a single solar mass particles. So that's going to happen in the next decade, whether we like it or not. So are we prepared? So I'm going to give you two examples of what's going to happen in the Pathfinder studies to let you have a sneak preview of what's to come. So the first thing that I want to talk about is that stars will shine in galaxy simulations. It's a obvious statement, but it was rarely the case in a typical galaxy simulations. By that I mean the following. Say, if you think about the mass resolution of, say, tens of thousands solar masses or even millions of solar masses, what's happening below that resolution, like the stars are shining and the supernova explodes, those physics are not described in your simulation. It's only the energetics of those individual particles are described only in a so-called sub-resolution recipes. So you dump your supernova energy back into the ISM in some convoluted, like complicated, empirically tuned way, which is not physically, may or may not be physically accurate. So imagine this is the moment where your star particles that represents like thousands, tens of thousands solar masses are formed. And this is the moment where that stars collectively explode. And what's in between has been typically ignored because, if you think about it, the corresponding time step for the millions of solar mass particles are really coarse. So it's resolved, the time step in between those two moments, formation to supernova explosion, was resolved only by, say, a few time steps. But now that we're talking about hundreds solar mass particles or even tens of solar mass particles, which I think is important turning points because tens of solar mass particles will enable us to describe a young massive stars that will explode as a core collapse supernova, which is a major energy source in galaxy scale dynamics. This time step in between will be resolved by couple thousands time steps, which is non-trivial to just let it be ignored. So we're going to have to include other modes of feedbacks, not just the supernova thermal energy, but like the radiations from young stars, like really massive young stars, or protostellar jets, or outflows that has been typically ignored. Yet there are multiple evidences that these early stellar feedbacks before the supernova explosion is really important to describe the proper regulated star formation processes. So here is the sort of the Pathfinder study that I have been working on. So what you're going to see in this movie is a photo heating rate from a star particles, star particles. That doesn't mean individual stars, but actually now means 1,000 solar mass per each particles. And what you're seeing here as a color is a photo heating rate, how quickly the gas gets heated by the radiation from the nearby stars, star particles. And you can see that the overall escape, you can see that where the most brightest stars are located along this galactic spiral arm. So you're obviously looking at the galaxy from the face-on angle. And you can see that the galactic escape fraction, the overall escape fraction, stays at around 1%. So this new modes of stellar feedback allows us to have not only allows us to have a new modes of coupling the stellar energy inputs with the ISM, but also allows us to have a new insight into, say, for example, escape fraction of the stellar photons in a galactic scale, but also in per star particle basis. So, for example, here what I'm plotting is the escape fraction of each star particles. What fraction of the stellar photons from each particles eventually escapes the galactic virial radius. So it will depend upon the morphology, gas morphology around each of those emission sources. So what you are seeing here is this galactic escape, the individual per stellar particle escape fraction in the y-axis as a function of its age. What you're seeing here is that when the stars are actually formed, right now, when stars are formed out of the dense gas clouds, the stellar photons have hard time to escape that dense gas peak because it's like enshrouded with the dense gas. It has really hard time to escape that dense gas cloud, even like at below or at 10 parsec level. But as it ages, the stars, now gravitationally decoupled with the rest of the gas, may have drifted away from the dense gas peaks, or it may have dispersed the dense gas around it. So it's relatively easier for that stellar photons to escape. So we have observed that the escape fraction per stellar particles increases by an order of magnitude as the star particle ages. So this is one example that as soon as we start to include different modes of more sophisticated modes of stellar feedback, we're going to have a different picture, a new insight into how the stars evolve in a galactic context and how galaxies evolve. So that was the first example, and I'm going to skip this slide. I'm running out of time. So the second example that I want to talk about is that the stars will form in clusters. Stars will form in association. It's, again, an obvious statement observationally, but it was rarely done in galaxy simulation. Again, think about the resolution that we're talking about. 10 to the 4, 10 to the 5 solar mass particles to represent your stellar population. And it's hard to use those particles to resolve the dynamics of star clusters, which may be millions of solar masses. So as soon as we get into this regime, then stars will be forming in clusters. So it has been quite challenging to accommodate this need. Or, for example, answer some of the most prominent questions. For example, how the globular clusters might have formed and evolved in time, how it has survived the multiple rotations around the galaxies and then survived the galactic tidal fields, for example. This was never been tackled in galaxy simulations because it's hard to simulate both galaxies and star clusters at this simultaneously. But in this Pathfinder study, you're going to see the black dots that represent star particles, which represents about 1,000 solar masses again. It's done in different codes, Gizmo code by Phil Hopkins. It's one of the sophisticated hydrodynamics code that's being used in galaxy simulations that includes a sophisticated modes of stellar physics. But here, two proto-galaxies are merging and coming to each other, and the gas in between gets compressed and forms a tightly bound star clusters. That actually is surprisingly really tightly bound. This movie is actually centered at the gravitational center of that resulting star cluster, so it stays there, that black collection of dots. And it's surprisingly tightly bound, so it survives the entire period of the simulation that we were able to run, which was about half a gigayear. So this is a resolution. We're talking about mass resolution still well above what we want to have, like tens of solar masses, but it's an interesting study. We're starting to resolve the dynamics of star clusters. So it's something that we want to work on in the next few years. The resolution at the moment is like barely enough to be able to see the relaxation process of those star clusters. So in this mass versus radius plot of those star clusters, you can see that it stays nicely on that dynamical relaxation track. So we're trying to, at the moment, find a way to evolve this galaxy longer in time to a lower redshift. Thank you. So in the next 1 minute or 2 minutes or so, I want to put a last sort of cautionary note to the many optimisms that I talked about. So I told you that the stars will start to shine and stars will form in clusters. So that's great. But what that means is, what that entails is that we'll have less room for the sub-resolution physics that I talked about. Here in this regime, we were describing the physics that's below the resolution with some tunable parameters, like how the stellar and supernova energy couples with the ISM. But we'll have less and less rooms for those physics, those sort of hand-waving descriptions of physics. So at the end, as soon as we have enough resolution, we're going to have probably a more or less identical input physics that's going to be needed in each of the galaxy simulations too. So at the moment, there are like tens of different simulation codes out there, and whenever we see a different results, there are like widely different, sometimes contradicting results, and we just wave our hands, and that's probably because we have a unconstrained, unequal, unidentical physics inputs. So we just move on. We're going to converge at some point, but we may soon be forced to have more or less identical physics. Then we don't want to be surprised by the fact that we now realize that one of the codes were just widely wrong because the code has some errors that has been hidden for the last 20 years because we haven't necessarily done our checks carefully against one another. So before we get surprised by the time when we're forced to include the identical physics, we may want to do a careful comparison before we hit that turning point. So we don't have to wait for another 10 years to have a perfectly constrained input physics. We can already include a common baryonic physics, for example, UV background, how the gas cools. We can pretty much agree on it. And we just include those constrained baryonic physics and see how different galaxy simulation codes pair against one another. So this has been a concern for many of the simulators, and it's great that people share this common concern and start to talk to each other. So we have formed this Agora collaboration. I talked about this last year a little bit. Last year I talked about mostly the dark matter only comparison. It was a success in that no single code was widely wrong. Now, this year we put a lot of effort in including the common baryonic physics. We're making an active sort of comparison to compare the galaxy simulations, including the common baryonic physics. Unfortunately, it's still work in progress. It hasn't gone as fast as I wanted, but stay tuned so we can I can talk about it maybe next year. Thank you very much. Yes.
Galaxy scale simulations. So a lot of evolutionary processes like expansion and core collapse and evaporation are controlled by the rate of two-body relaxation, and that rate is proportional to the mass of the stars or particles inside. So even if you get down to 10 solar masses for your typical
you'll still be overestimating the rate of relaxation by an order of magnitude, and all these processes will speed up.
Yes.
Is there some sort of numerical fix you have for this, or?
That's a good question. I don't have an obvious answer to. I mean, so for those of you who are not familiar with this topic, so to reduce the two-body interaction, I mean, if you just naively allow the gravitational body and body dynamics to progress, two particles that are really close by will form two-body pair, and it'll never get detached from one another. So what you usually do is soften your gravitational force over, say, 32 particles or 64 particles. So that's, I guess, what you're talking about, like by an order of magnitude difference, still with a 10 solar mass resolution. So I don't have an obvious answer how to approach that problem, but it's something that we have to think about. I have to really think about it.
Radiation feedback is important and if not dominant, right? So the question is, how do you treat radiation in particular? Is it possible to is it possible for radiation to propagate a long distance before it interacts?
Sorry,
How is radiation treated in the simulation?
Oh, sorry. So in the Pathfinder study that I shown you, I forgot to mention this, but it was the photon packets from each of the radiation sources were traced with the on-the-fly radiation transport calculation. That's a quite expensive calculation because at any given moment there are like tens of thousands of radiation sources at a given moment. So it's a quite expensive calculation, but it's getting increasingly doable. So.
A couple quick questions. The cluster that you showed, did that have adaptive softening on the side?
Yes, I believe so, yes.
And then my second question was about the escape fraction that you showed. So you showed that like redshift 7, right? I'm guessing you have ionizing background.
Oh, sorry. So the first experiment that I showed you, like the movie, that one was modeled to be like a present day galaxy, whereas I sort of briefly skipped one slide, but that was actually the redshift 7 calculation, in which case I include the UV background. Yeah.
Basically, I'm wondering if you could explore self-consistent reionization without an ionizing background.
That's absolutely possible if you are starting to, trace like millions of radiation sources, which I haven't done yet.
Possibly possible.
Yes, in the next decade or so. I mean, I learned that biologists are aiming to simulate human brains. So that's the main driver for exascale computing or even zetascale computing. So you have to be ambitious. So.
So in your plot of your cluster, you had at some point it went all white. The white stuff.
Sorry.
Yeah, the one after that, slide after that. In the movie.
Oh, in the movie, it's a poor color map that didn't. I mean, I should have. It's low density. Yeah, I mean, I can tell you like 30 secrets about this.
So in the galaxy simulation, we had a few slides before this one. It looked like to me that the knots, maybe one slide before this, here. It looks like the knots are maybe being fed by one cold filament. Like, say, all the red dots kind of have this one cold.
Like something like this?
Yeah,
Is it
so
there?
like each of the sources, it looks like there's kind of like a cold filament feeding into those sources. Is that something that you see in observed galaxies? I mean, this is the topology of this teaching.
Yeah, so this is the projected density. So I guess you're talking about like this kind of filamentary structure. I haven't actually done a rigorous comparison of this simulated galaxy, particular galaxy, against in observation. But this is just one very short time period, which was spanning about like 50 million years or so in the movie. So I don't know. I mean, I have to.
So at that point in the future, when biologists simulate human brain and you've sorted all numerical problems and there's no more physics to play with in galaxy formation, you will want to check whether the galaxies you produce look like real galaxies
Yes.
out there, right? So what kind of data do you envision you would need to do these checks? And if you find that your galaxies don't look like the real ones, what extra observational input should
Well, that's a major question that I don't think I can answer. So in the Agora collaboration that we talked about, I guess I remember I briefly talked about this last year as well, but we have a pipeline to compare our simulated galaxy against observations. So that will be the judge to like figure out which code is correct or more close to reality or not. I mean, if we happen to need that kind of judge. So we have a pipeline to convert our simulated data into a observable, like simulated spectrum or simulated images in any telescope filters, like literally any telescope filters. Yeah, I mean, that should be a community effort, which I mean, obviously it's not being enough answer for your question. So.
On that note, let's thank you. So I suppose the flush.
Yeah, so lunch will be in here, but feel free to wander back. Be back here by 2.
clip it on someone. Yeah.
Okay, I think we still got a couple minutes, and I think this is not actually muted.
It's
so
not muted.
Let's
It's definitely
turn this pointer. No, I had a. Did I walk away with the pointer? Probably. Yes, there it is. Thank you. So I was going to talk to you today about, I've given you a brief outline, a little bit first about clusters. I know all of you don't work on them, but I'd like to persuade all of you to work on them and to have all of the Chandra time put into them, right? Good idea. But let me give you a little bit of history, and then I'll basically the main part of the talk is about two things. The most massive clusters, how they're forming, and the clusters I'll be showing you are the HST frontier fields clusters, and then some of the nice work on AGN feedback. And here the primary example I'll use is M87 in Virgo. And finally then at the end, some information about what we might be doing in the future, quite a bit in the future. Okay. So how was the X-ray mission from clusters first formed? Well, there were initial reports of X-ray emission from Virgo, from M87, but it was always a question of, is it from the AGN? What's it from? So the first real evidence that there was extended X-ray emission, trying to find the pointer, came from Uhuru, which was a scanning, instrument, and it basically showed that this emission from Perseus was extended. It wasn't a point source, and sort of on the sky, it was something big like this. So it was really unclear what the nature was. People had argued that maybe it's not extended gas, maybe it's point sources, or maybe it's something. But then from Ariel 5, several years later, it was found that this is what spectra looked like in those days, right? Okay, so this is energy and counts here, and here you have this bump here around 6 keV. Well, that was iron emission, and it was really this that suggested that this was a 6 keV plasma that had iron in it. And this led quickly to one thing I'll be discussing quite a bit about later, which is the cooling flow problem in clusters. Okay, so how do we find clusters? Well, traditionally, the earliest ones were found by looking at for clusterings of galaxies. And Zwicky did this, and Abel did this, and it's been done most recently on the Sloan data. It's been done by X-ray surveys, the imaging ones, by Einstein, Isabella Joya, and her collaborators on ROSAT, by Boehringer, Rosati, Buchanan, Ebeling. A lot of people used the ROSAT all-sky data to do that. And now more recently it's been done with XMM and Chandra, and here are a couple of the recent references. So when you're looking in the X-rays, of course you're seeing the hot gas, and this is where most of the baryons in clusters are. When you're looking in Planck, you're also seeing the hot gas, and this is an image of the contours here are from the Planck, and they're on a big ROSAT image. So you can also find lots of clusters through SZ surveys. Planck has found them, the SPT project, as well as ATT, find new clusters. Not so much yet, but starting in the future, clusters will be found by where their dark matter is, because this is the dominant mass in clusters. And they can be found through lensing. HST and ground observations do that now. This is a magnification map of one of the frontier clusters for redshift 2. But then Euclid and W first AFTA will be very effective at finding those in the future. So let me give those of you who don't work on clusters a little bit more about their overall properties. Basically, starting with elliptical galaxies, you see hot gas in these systems. And this is a Chandra image of a galaxy. And as you go then to groups, they're often more extended. They're brighter. They're somewhat hotter. And here the gas is about equal to the stellar mass. In the galaxies, the gas is only a couple % of the stellar mass. In clusters, the gas mass really dominates over the stellar mass by about a factors of 5. And clusters can get to be very hot and very luminous. So the clusters are really the most massive collapse-bound systems in the universe. So I wanted to talk to you now about the frontier fields clusters. And there are a lot of people who have been involved with this project. And one of those I'd particularly like to mention is Steve Murray, who's put a lot of his HRC GTO time into this. This was really a project that he really loved. And in fact, the last conversation I had with him was when he put 100 kiloseconds into one of the clusters, so it'll bring it up to where it will be possible. But there is a really large team of people here, and who cover all wavelengths who've worked on these. So let me tell you a bit about these clusters, starting with the one whose picture is up here. So here's what we'd really like to do. We've gone after very deep Chandra observations to complement the very deep HST images, and we've also gotten, with Reinhard van Wieren as the PI, very deep radio observations. What HST wanted to do was to use these as cosmic telescopes to really be able to get a glimpse of what the James Webb telescope would be able to see at the high redshifts, at redshifts, 6 to 10, what the galaxies there might look like. What we've been more interested in doing is looking at these very massive clusters to understand what's going on with the cluster mergers. Our observations are deep enough that we'll be able to map the dark matter halos down to, for a cluster, what is a pretty low mass, 10 to the 13th solar masses. We'll be able to look for offsets between the dark matter and the baryons, the gas, or the galaxies. We'll be able to identify, and I'll show you a couple of merger shocks. And for the radio, to be able to start to understand the particle acceleration that you need to produce these radio halos and relics. To be able to look at the really faint radio population, and finally to be able to observe the effects of the mergers on the galaxies and the clusters. Okay? It's a long list. It's a big project. So here's the observing status. When HST started this project, there were 4 clusters that had been picked out. So these 4 have been completed now as far as the Chandra observations of them. This one was actually done and studied by Matt Owers before it became a frontier cluster. And these require more Chandra or more XMM time. Okay, so let me start with the most massive of the frontier fields clusters, and it's at a redshift of about 0.5. It's max 0717. Its mass exceeds 10 to the 15th solar masses. And this is the Chandra image in blue here. And you can see it's a very messy looking cluster on top of the deep HST image. And it's a very complicated system. This image makes it look a little less complicated. But this is sort of to illustrate how clusters grow. They grow through the infall of matter along filaments, and you can see a weak filament here. There's a group here that's probably also infalling, another group up here, and these major mergers, which are happening here. So in MAX 0717, we basically see sort of all the ways that a cluster can grow. Previously on this cluster, it had been studied mostly in the optical and also some in a much shorter X-ray observations. It was known to be very luminous, very hot. This is an overall temperature. And again, this very massive. So it was picked out then as being a quadruple merger with pretty massive subclusters. And that's this A, B, C, D that you're seeing here labeled on this optical image. And there were hints before of shock-heated regions. We can see those pretty clearly now. So let me show you what other wavelengths, the radio data in particular. So this observation from the GMRT shows a big radio halo here. And what you see here in red is a radio relic. and the size is the length of this, almost a megaparsec long. There's another radio source falling here, and somehow it seems like you always have a foreground, no matter what you're looking at. So there's a nice radio source here, but this is a foreground galaxy. So this halo, as well as the relic, sort of really implies there's a whole population of cosmic rays and magnetic fields, throughout the cluster. So these relics are really accelerated when you are really particles that are accelerated when you have these massive mergers coming together, and you'll see where that lies on the X-ray in the next one. So this is the most luminous extended radio source when you add the halo and the relic together that's known. So these are really, it takes a lot of energy to make these, and these are where there's a lot of exciting stuff going on. So now those things that are in pink are going to show up on the X-ray image. Okay, so here they are. Here's the relic, this thing that looks like either a flamingo or a rubber chicken. I'm not sure. Here's that foreground galaxy. Here's another tailed radio source, again, probably falling in along that filament that's feeding it here. So this region here between this merger that's happening, we're measuring with Chandra a temperature of about 20 keV. So it's been very much shock heated by the merger, since the overall temperature is more like 10 keV. And that's where it's reaccelerating the radio particles to make this relic. Okay. So these clusters, this idea of using clusters as cosmic telescopes, well, they're really not just for galaxies. That's what HST was doing. They really work for AGN. And with Reinhardt's very deep radio observations, this is a map of about, I think it's 51 or so radio sources that are in the field here. And these were again taken with the JVLA. 7 of these have magnification factors greater than 2, and a couple have magnification greater than 5. Based on their radio luminosities, probably most of them are star-forming galaxies with 10 to 50 solar masses a year. From mostly the photo-Zs, we can sort out which ones of these are in the cluster and which ones are behind. And Reinhardt's actually has measured the first radio number density and compared that for the high redshifts compared to numbers that are known locally, and found out that there's actually an increase here. We are reaching with these very deep radio observations using these clusters as lenses, we're reaching the SKA detection threshold. So the same way that HST, with the clusters, you're getting a peek of what James Webb is going to see, we're getting a peek at what the SKA will be finding. So for these clusters, there are a number of them, and this talk is not as long to cover in detail all of them. So I tried to kind of pick out maybe one sort of thing that was interesting to tell you about each of these clusters. So this is one of the next ones. And in pink you're seeing the radio and the X-rays in blue, and they're always on the Hubble deep images. So this is MAX 0416. Again, very massive, because that's why they were picked to be great cosmic lenses. And Georgiana has a paper that's just come out in the AppJ on this. So what she's found is that this is probably a pre-merger cluster. Previously, it was classed as actively merging, and there were 2 pieces from the X-ray and then 2 other smaller subclusters that had been found from the lensing. And now, at least one of those dark subclusters, it may be a filament that's really in projection. We see no X-ray emission from either of those smaller subclusters. But one thing that we'll be doing, and it was done on this cluster already, is a comparison of the baryonic, the gas, and the galaxies where they're located, and the dark matter. You've all seen the pretty pictures of the bullet cluster, where you see those separated, and it gives you limits on on what kind of dark matter you might have. Well, when Georgiana looked at this, she found that there was very good agreement with the peak of the X-ray emission for the two subclusters and the brightest cluster galaxies. So there's a peak here, and there's a peak here. But there had been a previous study that came out more recently, and they'd actually found a significant offset, this paper by Harvey, Massey, and others. But unfortunately, they found that offset because they took this blue galaxy. Those who know about clusters know usually in clusters, especially the brightest cluster galaxy, is a red galaxy. It's not a blue star-forming galaxy. But they took this blue galaxy as being the center of that cluster and found an offset from the X-ray gas. So that wasn't so good. So anyway, she doesn't find that, so it's a more normal result. In this cluster, and I only have one image on this, there are picked out about 4 subclusters that seem to be merging, and it has a really quite faint radio halo for its mass, and that's interesting that it may be either a very steep spectrum radio sources, which are unusual, or it may be, you may be seeing the birth of the radio halo. And Georgiana's paper, I think, has now been submitted, but is not yet out on this one.
Do you know if that rectangular appearance is just due to chip boundaries? Or is that
No, it's not chip boundaries. It's really what it looks like. Yeah. These clusters aren't so big. Yeah.
This is a field with a lens supernova, right? In Reynolds observations, are there any radio point sources associated with that galaxy?
I don't know with that galaxy for sure. Where's Reinhardt? Reinhardt, do you know?
It's this cluster.
Yeah.
It's that spiral, it's that lens.
Yeah, but I have not. We don't know yet if the supernova is there.
Okay. This is the cluster that Matt Owers looked at. Before it was a frontier fields cluster. And this is, so here's the X-ray, here's the optical. It's a very messy looking cluster. Again, it's very luminous and it's very hot. It has 2 cores that have probably passed through each other here. And here you see the BCGs left from those. They're pretty well destroyed. In this bright region here of the X-ray, there really aren't many galaxies left. They've passed with the cores to here. There's also a northern interloper subcluster that is probably headed on its way out. So it's really a quite massive one. One of the most interesting things about this one is what's happening to some of the galaxies in this cluster. Matt found 4 of these jellyfish galaxies that have like these tentacles on them, and they're marked in green where they are here. You can see one's a pretty bright X-ray source, and the others are probably not much emission from them. And you see these as the gas gets stripped out in these merging clusters. I think Ming Sun found the first jellyfish galaxy in another merging cluster, and now there are more than 100 at least in other clusters. Harold Eveling has a nice recent sample, and Poggianti also has a large sample of about 70 clusters where she's looked for jellyfish. So there are 2 other frontier clusters that have now been approved for HST observations. And in the X-rays, this is a Bell 370, and this is an existing Chandra observation that Mark Bautz analyzed. You can see it's very elongated north-south. It has a couple, they're hard to see here, one's here and one's here, I think, of these sub-millimeter galaxies that are detected. And this one we've proposed for deeper XMM observations, since it doesn't have nearly the structure that Chandra does. And the other one is this cluster called S1063, and it was also one of the clash clusters. It's probably the most relaxed of the frontier clusters. It doesn't look nearly as messy in the existing observations. And as I told you at the beginning, this one, Steve put in 100 kiloseconds of his GTO time, so we'll have good deep observations of that. So in the shorter second part of this talk, I wanted to move on from mergers to what's happening in the clusters that generally don't have major mergers going on in them. These mostly looking relaxed clusters that have cool cores, their surface brightness peaks toward the centers. And if you do temperature maps of them, this is a set that Alexei did for Chandra and a set that Gabriel Pratt did for XMM. They have these very cool cores at the center. And the question for many, many years was, what happens to this cooling gas? I mean, it's cooling. What's going to stop it from cooling? Well, we now know that what stops it most of the time from cooling is that there are supermassive black holes in the centers of these massive galaxies, and outbursts from those through bubbles and through shocks reheat this cooling gas and stop it from cooling, and then it cools again, and this cycle continues. You see, I've shown us a set of these going from the Virgo cluster here up through Perseus. And you can see the scales and how the energies are changing, up to one of the most massive ones, MSO 735, where it has huge, huge bubbles here that produce a lot of energy. So there's very, very little emission coming from the AGN itself. They're radiatively faint, but they're mechanically very powerful to be able to drive the types of bubbles and shocks that you see. Here are a couple review papers if you want to know more. So I'm going to concentrate now just on the Virgo cluster, on M87. This is the nice picture from ROSAT. It's a huge scale here, right? This is 2 degrees here, right? 2 degrees is a half a megaparsec. And here in the core, you see the brightest emission on M87, which is here. And there are another couple of galaxies here, M86 and M84. But M87 is clearly the dominant galaxy. The brightest galaxy is actually NGC 4472 here. You can see it's much fainter in X-rays than M87. And M87 is the one that hosts a supermassive black hole and a jet. And it has a relatively small cooling flow compared to a cluster like the Perseus or the Phoenix cluster, but it's nearby and can be studied in great detail. So Bill's led all of the work on M87, and what you see in the X-rays, I have to get ready to push another button over here. What you see in the X-rays is a bright central region, and then these two arms that extend out. This one is very filamentary, and this one is not so filamentary. And here from the XMM observations, you see these arms are really cool. This is a temperature map. And when you look in the radio, you see that this arm here, which looks so straight and filamentary, is actually all twisted in the radio. And on the other side, you see an arm coming out and then a beautiful bubble, classic bubble at the end of it. And this YouTube simulation that Bill found, I think we can make it play. Here we go. The sound is so faint. Okay. Anyway, you see, as it goes up, you get quite a loud lot of noise and a lovely smoke ring here. And that torus that you see is very much seen from the side, the torus that you see here in the radio. Okay. So what do we learn from the X-rays from here? Oops. Oh, I'm sorry. Yeah. Okay, so here's the picture again with the arms here. Okay. And this is in the soft. Remember, these arms are really cool from XMM. So this is 0.5 to 1 keV. These are very cool. If you look at it in a harder band, 3.5 to 7.5 keV, you might not even think it's the same object. You don't see the arms at all. Instead, you're basically seeing what the pressure looks like. And the pressure is showing you that there's this shock that has a radius of about 13 kiloparsecs. Okay? And here are the stars. They're just there. They have no control what's happening to them. This stuff is just going on, and they're watching. As you know, there's a large central black hole at the center. It has a famous jet. It's this supermassive black hole that drives the jet and the shocks and inflates all of these little bubbles that you see here and makes this shock. Okay. So we know from looking at the core, this region here, that there's no really hot gas just outside this region. So whatever this outburst is doing, it's a pretty long duration outburst, and at least the initial shock is pretty modest. We're not seeing really hot gas that's been heated, as you might expect if there had been a really major shock that had happened here. So what Bill and Eugene Chorotsov and others have done is they took a whole series of models to try to explain what parameters you would need to get a shock that looked like this. And they took different durations for how long the AGN is on, ranging from 1/10, 100,000 years, up to 6.2 million years. And they matched this to the data, and this shows you the temperature profile, and it's really these jumps that are important, and basically the emissivity, the density profile, and it's again these jumps that matter, and these are the two different energy ranges here. And the best match to the data gives you an outburst energy of about 5 × 10⁵ ergs, pretty major, but more exciting, it gives you how long the AGN is on as about 2 million years. Okay, so we know this outburst started about 10 or 11 million years ago, but the AGN was probably only on for about 2 million. Couldn't have been less than 1 million years, because then it would have put in a lot of energy at the beginning, and we'd see hot gas around that central area, and we don't. And it's probably not more than about 4 million years, so pretty short by comparison. Okay. Okay. So we can also look at how these sort of summarize. That's the age, how the energy gets carried away. The bubbles themselves, all those little bubbles you saw, they carry away most of the energy, about 65%. The shocked gas has about 10%. So 75–80% of the energy that comes out from the outburst is available to reheat the gas. Some just gets carried away by a weak wave. And again, the outburst lasted about 2 million years. And this is plenty of energy to balance the cooling of the gas. So now we know that that AGN are really important. They really tell you a lot about what's going on in terms of the feedback to the galaxy evolution and the growth of the supermassive black hole. So I have 2 more things I wanted to cover. And the first is, since most of you are mostly postdocs, some of you have come from more grown-up or less grown-up areas. But I wanted to pass along some advice that both Bill and I and everybody who worked with Ricardo probably got from him. And that was to look at the data. Really, really look at the data. And I could give you a lot of examples for interesting things that we've looked at and found in the data. I wanted to give you one example. Bill was getting a long time ago, probably 2003. Bill was getting a set of lectures ready for some island off the coast of either, I don't know, Italy or France, right? He was about to go away for a while. I'd gone to the grocery store because there were kids at home. We needed food. And Bill decided he needed to get a nicer image for his talk that he was going to give than just the ROSAT image of M87. So he looked in the Chandra archive. And obviously you know what he found. He found this. He found arms and bubbles galore in this. Well, the PI of the observation was looking for low-mass X-ray binaries and emission from globular clusters. They didn't pay any attention to this other stuff. They were probably annoyed by it. Anyway, pay attention to the data. I wanted now just to talk at the end a little bit about the future. But first to remind you how far we've come in such a relatively short time. So the first imaging solar X-ray telescopes were these 3-inch diameter ones here. The pictures are shown. And they're about the same size diameter as Galileo's 1610 telescope. Well, it took about 400 years to go from his 1610 telescope to HST, which is 100 million times more sensitive. We went from these 3-inch X-ray telescopes to Chandra in about 40 years, and again reached this, huge increase in sensitivity. And it's really great. At 16, Chandra's still doing great. So what's next? Well, you all know that Athena has been approved by ESA as a mission for the 2020s. And now NASA is looking at future missions, one of which is under study is the X-ray Surveyor, also for the begin in the 2020s. This is the current team of institutions involved in that. It would have a 3-meter aperture with Chandra resolution. This would be 30 times the effective area of Chandra with very good imaging capabilities and a good big 20 arc-minute diameter field of view. And of course, the most up-to-date science instruments, microcalorimeter, a large CMOS imager, and gratings. And that would be a huge increase over Chandra, especially with the gratings. So for the kinds of things I've talked about, what might you see? Well, you'll be able to look at, a quasar at a redshift of 6. This is when it's still in its radiative phase. So you're going to see a lot of bright emission from the quasar. But there's probably a corona of hot gas around it, either from the group that it's in, and you'll be able to measure, that corona, and measure the cooling time of that corona. For low redshift, here's M87 again. It has knots in its jets. You'll be able to get wonderful spectroscopy of the jet and the gas, as well as the gas that's around these. So there'll really be, huge increases in sensitivity and what you can look at overall redshifts. So just in summary, I hope I've been able to show you that there are really incredibly dynamic processes going on in clusters of galaxies. I showed you the AGN and how the reheating of the cooling gas occurs in the centers of these clusters. I showed you the frontier clusters and what we're learning about how clusters grow and reheat them. But, to do this and to understand really the physical processes, we need the X-ray, we need the multi-wavelength observations, and we need the simulations. So thanks very much. And remember, look at the data. Thanks.
Any questions?
Everything is fine? You asked questions while I was talking? Ramesh.
So, Christine, you said one of those clusters earlier in your talk is a quadruple merger.
Yeah.
Does that thing happen in simulations?
Yeah, it does, but I mean, it happened when, but these, you have to, I mean, if you do, like, I go sometimes and look and try to talk to people, like, about the Illustris simulations. Those are done for a pretty small volume of space, and these are really rare. These are the rarest, most massive clusters in the universe. So you need to simulate larger volumes to see clusters this massive in simulations. That's really the problem. You see mergers, but they tend to be of much smaller systems. More volume.
Okay.
Or you got to use real data.
No, but I think you should post this as a challenge now.
Oh, okay.
Name one of these guys with 4 that are still distinct and visible.
Yeah, yeah.
In
yeah.
big cluster.
Yeah. Okay.
Other questions? Well, I have one. We've learned a lot about feedback and about AGN power and its effect on clusters and galaxies, thanks to radio emission. But, you know, like being a guy that looks at quasars, that's only 10% of quasars. So what do we know about, you know, the power that comes from supermassive black holes in the radio quiet case, and how do we know it?
Well, in a very basic sense, if you have, you know, galaxies and they're to keep those elliptical galaxies, their stellar populations, we call it red and dead. Mm-hmm. You can't have gas cooling and forming new blue stars, right? So at some level, there has to be feedback going on in all of the elliptical galaxies, okay? Mm-hmm. And there are many of the galaxies that, you know, often you see something faint from the nucleus, but there are many of these elliptical galaxies that have a lot of emission around them in X-rays, and they don't have radio emission. Often there'll be something just from the core, just from the nucleus, but not always, you know, radio lobes and jets and things.
Right. Right. Yeah. Okay.
Okay.
One last chance. Okay, so Christine has also been volunteered to chair the next session.
Oh, you can go on to the next here. I will give you the microphone. Good. Thank you. And then I will go look up and see what the name of your title is.
Should I get to a program?
There's one right here, and I had one as well with titles and things on it.
By the way, where's Philip? Philip? Oh, could you stand up for a second? We want to thank Philip for the cover image on the abstract handbook, and I'm singling him out because we neglected to put a caption in there, but it's his 3D MHD simulation of a supernova.
Right, actually I have a movie of that tomorrow.
And we're going to see a movie tomorrow. So stick around. There's no popcorn, but it's going to be really good.
Okay. Use your microphone so I can shout. Okay. It's my pleasure to introduce Rebecca Canning. Rebecca is from Stanford, and the title of her talk is still The Evolution of Early Type Galaxies, an X-ray Perspective. There you go. I'll give you a 5-minute warning. Thank you.
Okay, hi. I'm a first-year fellow here. I'm going to talk about X-rays, looking at the evolution of early type galaxies with X-rays. So first I'd like to spend the first half of the talk kind of saying why is an X-ray perspective of early type galaxies interesting. For the second half of the talk, I'm going to tell you about some recent results we have in the interplay of cold and hot gas in massive elliptical galaxies. So we know that the dark matter structure provides a framework for the evolution of matter, but we also know that that's not the complete story. So there's a lot of baryonic physics that goes into the evolution of galaxies. And here's just a cartoon from a review paper by Silke Mumma, where they're looking at the galaxy luminosity function. And the red line indicates what happens if the stellar mass simply follows the halo mass with no no baryonic effects, no feedback. And the blue curve indicates what we get from observations. So we can see that there are discrepancies with the Fourier. This is telling us that baryonic physics is important. And at the high mass end, we have these red and dead giant ellipticals that Christine was talking about earlier. And we think that the discrepancy in the number density here is driven through AGM feedback processes, which prevent our galaxies growing really large. So they prevent this cooling flow onto the galaxies, which would make them very large galaxies. So this is just an image here of a red and dead giant elliptical galaxy. And it's very easy when you see it next to a nice star-forming spiral galaxy why these things are called red and dead. But in the 1980s, actually, it was discovered by the Einstein satellite that these red and dead elliptical galaxies have actually a lot of gas. So here is the X-ray view of both of those systems. So in the X-ray, these systems are very much alive. You can see that the X-ray emission is from point sources. It's from the AGN stellar point sources as well, and also from hot gas. And in giant elliptical galaxies, most of the X-ray emission is coming from hot gas. And this hot gas carries with it an imprint of the baryonic physics. So you can see in this image, I hope you can see here some cavities in the X-ray gas. And these are cavities that have been driven by radio mode AGM feedback in these systems, blown these bubbles of relativistic particles, which have risen buoyantly into the hot gas, and they've pushed aside the X-ray emission, causing these cavities. But if we're going to talk about evolution, we'd like to look, we can't just sit and wait for these sorts of systems to evolve. We need to look at many of these systems and look at them in statistical sense. So one of the early and very important observations on the X-rays coming from elliptical galaxies was the relation between X-ray luminosity and optical observables, such as, so here on the bottom we have the K-band luminosity, so it's a proxy for stellar mass. I've got the gas X-ray luminosity on the y-axis. And the thing I wanted you mostly to draw your attention to actually isn't coming out on the image, but there's a grayed region here, so you're going to have to believe me on that one. It's about this size. And that's the current, from literature results, that tells you the current Chandra scatter and limits in these observables. So there is a relation, but the relation has over 4 orders of magnitude of scatter. Okay, so, but putting that aside, these sorts of relations have 3 key features that can tell us things about feedback models. So the first is the bright end slope. So that's dominated by the mass of the galaxy. It's dominated by AGM feedback processes. There's the faint end slope of these relations. That's dominated by global winds from supernovae feedback. And then there's a critical luminosity. So this occurs at the mass at which the supernovae winds dominate over the AGN and gravitational processes. So in this plot, using some models for the energy input from the supernovae, the energy required to unbind the gas, the critical luminosity would be there. So here's a very similar plot. So on the bottom, it's velocity dispersion rather than K-band luminosity, but still a proxy for stellar mass. Against the X-ray luminosity, this is gas luminosity again in galaxies. And this is from a paper of Choi et al. 2014, and it's actually, the data points on here are all points from simulations. So they used their simulation, they just put in 3 different prescriptions for AGM feedback. So first, no AGM feedback, those are the black points. The second prescription was a thermal AGM feedback, so just adding heat to the gas, just put in heat. And what that does is it rises the temperature of the gas, prevents that gas from cooling, so it prevents the formation of these big galaxies, but the gas is at very high temperature and it increases the X-ray luminosity. And then there's momentum AGM feedback. So this drives the gas out of the galaxy. And as it does so, it reduces the density, it reduces the luminosity. So both these prescriptions in blue and red actually can recover the optical observables that people test these simulations against. They recover the galaxy luminosity function in the optical, they recover M-sigma relations and things. But if you look in the X-ray, they differ by 3 orders of magnitude here in what they would predict as X-ray observables. And what this paper found, and a number of other papers too, is that X-ray observables are actually very sensitive to the sorts of prescriptions that you can put into these models. So far I think X-ray observables have been underexploited for this sort of, for providing anchor points for these sorts of models. Now I told you there's a huge scatter. This is actually, there to there is the level of the scatter at that mass, so you're going to have to believe me again since you can't see the contours. But this scatter is going to be from observational effects. It's going to be from environmental effects, so the density of environment galaxies are in. It's also a reflection of the energy budget of the hot ISM. And that energy budget depends on the host mass. It depends on heating and cooling prescriptions. So it depends on the supernovae feedback, AGM feedback, also the metallicity of the gas. So that means it depends on the star formation history of the galaxy. It depends on the galaxy structure and kinematics, so whether a halo is flattened or whether it's got significant angular momentum. What we'd like to do, what I'm going to try and do over the fellowship, is to try and quantify better how these processes contribute to the scatter in these plots. And the idea is to try and provide a low redshift anchor point for testing feedback prescriptions in simulations and things, using X-ray multi-wavelength observables. Now we're doing, we have about 300 galaxies, which amounts to a few thousand Chandra obsides from which to do this work, but we're doing a blind analysis, so I can't show you any of these results. I don't know the results. Hopefully next year I can show you the results. So I'm going to talk about something I can show you the results of, and that's the interplay of cold and hot gas in massive elliptical galaxies. So this is a small sample of 8 nearby red and dead giant elliptical galaxies, which we went and got Herschel data for. And we traced the C2 line. So the C2 line is from gas at about 100 Kelvin. All these galaxies are nearby, and all the galaxies are very similar. They have similar stellar masses, they have similar X-ray gas masses, they have similar black hole masses, even. But, and they have the same star formation rates as well. But 6 of 8 of the systems show extended ionized gas, 2 of them don't. And what we find with our Herschel results is that the same 6 of 8 in which we found the ionized gas, which is shown here as contours, so these are contours of H alpha emission, are seen in cold gas. And so the cold gas is, intensity is what you're seeing in the colors. And the cold gas morphology and kinematics, so in cases where it's dubious whether the morphology is actually tracing each other, we have the kinematics, and the kinematics trace each other. The morphology and kinematics are similar to the ionized gas, and this ratio is relatively constant between each galaxy and also along these filaments in galaxies. So these phases of gas know about each other. But what about the hot phase? So what we found with the hot gas properties, so these are looking at Chandra images of these systems, was that in our cold gas poor galaxies, they have very relaxed X-ray morphologies, and the X-ray density peaks on top of the AGN emission. In our cold gas rich systems, they have a very disturbed X-ray morphology. The gas peaks are less peaky, and they tend to peak off the AGN. And actually, it's not just in morphology that they're different. They're different in the thermodynamic properties of these systems. So what you're seeing here is entropy profiles of the elliptical galaxies. So this is entropy in the hot gas against radius. Our cold gas rich systems are shown in red, and our cold gas poor systems are shown in black. These data points are uncertain. So I would trust everything beyond about a kiloparsec. I'm not sure we can say really what's going on in here except in 1 or 2 systems. But outside of a kiloparsec, there's a systematic difference in the X-ray properties of these systems with the cold gas properties of these systems. And we can look at this in another way, and we can look at the field stability parameter in these systems. So this is the ratio of conductive heating in the hot gas to the radiative cooling rate in the hot gas. This here is just using Spitzer conductivity. So if the conductive heating is greater than radiative cooling, then the field stability parameter will be greater than 1. And if cooling is dominating over heating, then the parameter will be less than 1. So in all our coal gas rich systems, we find that the field stability parameter is less than 1. So this is telling us there's really a nice link here between the coal gas and the hot gas. And it's provides some quite nice evidence that that the coal gas is there because it's cooling unstably from the hot ICM in those 6 of 8 systems. But their star formation rates are the same. These systems with the coal gas that are coal gas rich aren't just forming stars. So how is this gas coupled in 2 ways, not forming stars? Well, one way to couple them would be through AGM feedback. Now, all of these giant elliptical galaxies have radio mode AGM feedback, which is active. So we see the radio lobes. That's in purple in this system, with the blue behind is the X-ray. Here, the radio emission is actually confined to the center. That's the radio emission. This is optical emission, and then blue is the X-ray. But rather surprisingly, we found that the cavity power, so this is derived from the X-ray observations of cavities being pushed aside by these radio lobes, of systems in which we find no coal gas, is larger. So these are larger jet powers than in systems in which we do see plenty of coal gas, which is rather counterintuitive. We would have expected a correlation like this because more coal-dense gas you might have thought would provide more fuel for the AGN. Unfortunately, we found exactly the opposite. So there are 2 scenarios we thought. So maybe the AGN is very strongly coupled to the hot gas. Perhaps it's even feeding from the hot gas. So in which case you have this relaxed X-ray gas. So it's very dense. It has a short cooling time. Now it could remain stable if heating can balance the radiative cooling. But if it's feeding from the hot gas and that food source is disturbed, offset from the AGN, then the AGN loses its fuel source, the jets will shut off, and the gas will be able to cool. But this means that eventually, if this is occurring, then eventually when the system relaxes, the jets should switch back on. We should see very nice correlations between morphology and jet powers if we have larger sample sizes. In the second system, perhaps the AGN is coupled to the coal gas. So in this case, you have a system that's become morphologically disturbed, and that tends to aid cooling from the hot atmospheres. So the AGN has more coal-dense fuel that goes down to the center. It gets these strong jets, and the jets then clear out the coal gas, which is why in the systems with the strong jets we don't see the coal gas. They deposit their energy further from the black hole, which would then mean the gas would be able to cool again. But if this is true, then we should see intermediate states if we have larger sample sizes. So we'd like to go get larger sample sizes. We only have 8. There were only 2 that were coal gas poor. So we're working on that. This was Herschel no longer exists, but Sophia can do these sorts of observations. So this is Sophia, and this must be the most fun telescope to go observing on. And actually, we came back just last week from our last set of observation. Thank you. We've got initially 6 new systems, so we want to make sure that we can calibrate these systems well and stuff before we go and get a very large sample. We have 40, a parent sample of about 40 in the radio, but we're only going after 6 so far in the C2. So we can hopefully use these observations to try and work out, does the coal gas cool from the X-ray gas? Is the rate at which the gas is cooling affected by the dynamics of the hot halo? How is the AGM fed? Is it fed from hot gas? Is it fed from coal gas? And also, at what mass does the radio mode feedback cycle break? Because as we go down in masses, we have our potential for hosting an X-ray halo becomes less and less. So if we can trace these sorts of things to lower masses, somewhere this feedback cycle should break if hot gas is really important in this cycle. Okay, so just in summary, X-ray observations of the gaseous halos hold information about their evolution. And this is information that I'm hoping to mine in the next few years. Massive galaxies can host cold gas, but they don't tend to host star formation. And that this cold gas likely originates from the hot gas in these systems. Hot gas may be important in feeding the AGN, but it seems like it's very important to the feedback cycle. So this tells us that if we can look at these systems and go down the mass range, we might find some interesting new physics. Thank you.
Questions for Becky?
I have actually two comments. So first of all, when you show the LX versus LK from the whole silicon paper, that LX is not LX gas, that's LX photon.
Yeah, so that was
So
the Rosat observations.
It's going to be even larger if you plug LX gas.
Yeah.
Because a lot of low gas poor galaxies have LX much lower.
Yeah.
That's right. And second, so and it may be better instead of using the LX, LK, using LX versus temperature of the gas. That gives you much better correlation. And the second comment is when you show the two types of galaxies, the giant galaxies, one with the cold gas, one without cold gas. What we have found is if you plug the LX luminous temperature of the gas plug, then one with the cold gas has a much higher luminosity for a given temperature. They also have a similar LK. So similar LK, similar temperature, but much higher
X-ray luminosity.
Hot gas luminosity. So one possibility. Also, those are mostly the one in the center of small groups of small groups like 50, 44, 46, 36, and 58, 46, and something like that. 58, 13. Those are all in the small center of the small group. So one possibility is instead of AGN feedback, just dark matter distribution may be different in those two groups. So one with more dark matter or in the different distribution of dark matter could hold the gas better. So the density of the gas is higher. That's why the entropy is different.
Yeah.
That the higher density will make better cooling, higher cooling rate. So that may be the reason why you see the second point, right? The cold gas coming from the hot gas, but why has a higher density?
Yeah. So actually the systems that we've that are in the plot with the entropy, the two sets of entropy profiles, in both sets of those, there's central group galaxies, or they're possibly in a group but towards the outskirts of Virgo or something, and they have very similar X-ray luminosities because those particular galaxies were picked specifically for that. So yeah. Okay.
So if the cold gas potentially originates from the hot gas, then no matter what its origin, if it was driven out of the galaxies by supernovae or if it was a mix of other processes, the cold gas should have similar elemental abundances to the hot gas if it derives from the hot gas. Of course, the temperature being different, if you looked at iron, you might have to look at, I don't know if the iron L lines or the iron K lines, if the gas is hot enough for the hot gas. But is there a chance to get enough photons to look at the lines and actually try to see if the gas has a similar...
There is with the X-ray surveyor.
Yeah. So I would... in Chandra... In the Chandra archives, it's nowhere near that the sorts of sample sizes for which we could get a single LX, a simple TX, and be able to form those relations. But we could probably do it with much smaller, maybe 30 or 40. Yeah. So, but this sort of thing would be amazing for Surveyor because this may provide a low redshift anchor point, but with Surveyor we could push to higher redshifts, look at the like luminosity functions of LX and stuff. Well, of gas, even of the gas luminosity, as you go to slightly higher redshifts, not hugely higher redshifts, but slightly higher, provide, I think, really nice constraints. And looking at how the metallicity of those halos changes over redshift would be awesome.
No more questions? Let's thank Becky again.
Excellent.
Our next speaker is Karen Yang from the University of Maryland. And the title is The Interplay Among Cooling, AGN Feedback, and Anisotropic Conduction in the Cool Cores of Galaxy Clusters. One of my favorite topics.
Thank you. So my name is Karen, and I'm from University of Maryland. And today I'm going to talk to you about a recent project I've been working on with Chris Reynolds. And it's about interplay among cooling, AGN feedback, and anisotropic thermal conduction in cool core clusters. So this is in a big context of AGN feedback in clusters, as has been mentioned in the previous two talks. So just to briefly recap, so we know that for some massive clusters, actually the central cooling time is very short. So we expect to see a massive cooling flow toward the center and produce a lot of coal gas and star formation at the center of the clusters. But we actually don't observe it, which means that there must be some heating mechanisms that's stopping the cooling flows. So one of the most promising mechanism is AGN feedback, because we see that almost all cool core clusters host these large X-ray cavity systems at the center, and they're filled with radio emitting plasma, meaning that these bubbles are inflated by the supermassive black hole jets. And also the cavity power estimate from these cavity systems are enormous, and it's enough to balance the radiative cooling. So we think that it's the AGN feedback that's counteracting the radiative losses in these cool core clusters. However, one question that has been long studied but still not well understood is the roles of thermal conduction. So basically, the thermal conduction has been proposed as one of the heating mechanisms because it can channel heat from the cluster outskirts to the cooler centers. However, the ICM is magnetized, so we expect the thermal conduction to be anisotropic because of the small gyro radii of the electrons. So actually, if you have anisotropic thermal conduction in the condition of the cool core, then actually it will induce the so-called heat flux-driven buoyancy instability, or the HBI, which will actually reorient the magnetic field lines in the azimuthal directions and thus shut off heat conduction and potentially worsen the cooling flow problem. So the main question we want to study for this project is that whether it's good or bad to have thermal conduction in cool core clusters. So more specifically, we want to look at these following questions. First of all, in these previous HBI simulations, actually they've neglected the importance of magnetic field strength. So basically, they use a very high beta. And we know that in clusters, actually, the plasma beta is around 100. So we want to know what is the saturation property of the HBI in this realistic cluster magnetic field strength. And the second question is that in these simulations, it's also letting the HBI to develop in a quiescent ICM. But we know that the ICM is very dynamic. It's filled with AGN jets and bubbles. So actually, we want to know whether the turbulence driven by the AGN jets could randomize the field lines and thus could overcome the field line wrapping effect of the HBI. And lastly, we want to know what is the relative importance of conductive heating compared to the direct AGN heating. In particular, we want to see whether there will be a very special case where the AGN can heat in two channels, one by directly transforming the kinetic energy to thermal energy, and also by opening up the field line so that actually it can promote conductive heating. So basically what we do for this project is to run 3D MHD simulations, including anisotropic thermal conduction. And so we have two sets of simulations, one without AGN feedback to study the HBI property and dependence on the magnetic field strength, and the other set of simulations where we turn on AGN feedback and to study the second and third question. Okay, so here's just to show you a typical HBI simulation without AGN feedback. And here's a temperature map overplotted with the magnetic field directions. And for these clusters, we initialized the temperature profile based on the observed Perseus cluster, which has a cooling radius of 100 kiloparsec. And the initial magnetic field is assumed to be tangled with a coherence length of 100 kiloparsec. And we assume full Spitzer conductivity along the field lines just to explore the maximal effect of the thermal conduction. And as you can see, actually, without AGN feedback and because of the fact that conduction is shut off by the HBI, the core actually collapsed around 0.3 billion years. Okay, so we can quantify the topology of the magnetic field by looking at the evolution of this theta B defined by the angle between the magnetic field lines to the radial direction. So the larger theta B is, that means the field is more azimuthal and the HBI is more significant. And in the beginning, the field is tangled, so the theta B corresponds to a Spitzer fraction of around 1/3. And as you can see, for this dashed line, where for the typical HBI simulation with very large beta, actually the theta B just grows with time due to the effect of the HBI. However, when we used a more realistic beta value of 100, which is shown in the dashed solid line here, you can see that the HBI is much suppressed. We can better understand this result by looking at the stability criteria for the HBI. This equation basically represents the competition between a destabilizing temperature gradient and a stabilizing magnetic tension. So as you can see, the smaller beta is, or the larger field strength you have, it's more likely for the HBI to be stable. And the K here is the wave number of the initial perturbations. So this equation also implies that actually, for a system where all the other quantities are known, there exists a critical wavelength below which the HBI should be stable because magnetic tension is enough to resist the growth of the HBI. And if we plug in the number for the Perseus cluster, actually this critical wavelength is quite big. It's comparable to the size of the core radii. So that means that actually a significant portion of the HBI modes should be stable. And that explains why we see a suppression here. This equation also implies that actually if you start with a perturbation that tangles on very small scale compared to the critical length here, then you shouldn't see any HBI at all. So we indeed confirm that using a simulation with a magnetic field coherence length of 10 kiloparsec, and that's plotted in the dotted line here. As you can see, the HBI didn't grow at all, and also the magnetic field is even extended in the radial direction. That's because the magnetic field lines are dragged in by the cooling flows after 0.3 billion years. Okay, so now we want to see whether, in the cases where HBI is still allowed to grow, we want to see whether the AGN-driven turbulence can randomize the field lines. So here is one of our simulations, including AGN feedback. And in here, I'm showing you the density evolution, and the black dots are the cold gas forming out of the hot medium due to local thermal instability. And in these models, we assume cold gas accretion, in which the jet power is directly linked to the amount of cold gas in the vicinity of the black holes. Okay, so here are typical snapshots of the turbulent velocity and the magnetic field strength and directions in the simulations. And as you can see, indeed, the magnetic field lines can be randomized by AGN-driven turbulence. However, the effects of the AGN primarily just along the jet axis. And again, we can look at the evolution of the theta B parameter. And here, as before, if we only average the theta B within the whole core region, then actually we don't see much difference between the simulation with or without AGN feedback. However, if we average the theta B only within a cone that's 30 degrees away from the jet axis, then actually we find that the HBI is indeed suppressed for the simulation, including AGN feedback. And actually, the theta B fluctuate around a value that corresponds to a 1/3 Spitzer value. Okay, and the bottom panel here shows the instantaneous jet power. And you can see that for the AGN simulation, actually the dips in the theta B or the enhanced Spitzer fraction happens whenever you have a large AGN outburst. And that's because whenever you have a large outburst, there will be some magnetic field lines that stretch in the wakes of the bubbles. Okay, so now we have a magnetic field topology that's mediated by AGN feedback and thermal conduction. Now we want to ask the question, what is the relative amount of conductive heating compared to AGN heating? So here I'm plotting the conductive heating rate within the cool core in the dotted line here, and compare that with the radiative energy losses in the dashed line here, and also the average jet power is shown in the red curve. And as you can see, after some time, the cluster has reached a quasi-equilibrium state, and at that point, actually, conductive heating rate only contributes to roughly 10% of the radiative losses. And you can also see that the conductive heating rate actually decreases with time, and that's due to the action of HBI, and also because that whenever you have efficient conductive heating, it will raise up the core temperature, reduce the temperature gradient, and so that it will suppress the subsequent heat fluxes from cluster outskirts. And a somewhat disappointing result from this figure is that actually we don't see any events such that the conductive heating rate just simply boosts because of enhanced Spitzer fraction enabled by AGN outbursts, but instead, because of the compensating effect of enhanced Spitzer fraction and reduced temperature gradient, we get a pretty constant conductive heating rate throughout the cluster evolution. So in the long-term evolution, actually the HBI and reduced temperature gradient is a more important factor in determining the overall cluster evolution than the temperature, than the temporary fluctuations caused by AGN feedback. Okay, and here I just want to compare the conductive simulation with a normal, typical AGN feedback simulation, and you can see that there's basically not much difference between these two because the conductive heating only contributes to 10% of the radiative losses. However, we know that thermal conductivity is a strong function of gas temperature, so we expect conductive heating to be more important in more massive clusters. So here I'm showing you a simulation run with a cluster with twice of the mass of the Perseus. And here's the same plot again. As you can see, in this system, actually, it's quite interesting. So the conductive heating rate is around the same as the average jet power, and they both contribute to around half of the radiative losses. And by comparing the conductive simulation with the AGN-only simulation, we see dramatic difference in the pattern of AGN activity in these two systems. More specifically, we found that because of the conductive heating contributing to half of the radiative losses, actually the AGN don't need to input so much energy to counteract radiative cooling, so that actually the average jet power is suppressed. Also, the duty cycle is also suppressed. And recall that in the cold feedback model, the jet power is proportional to the amount of cold gas in the system. So actually, in the conductive simulation, we also expect suppressed cold gas formation when conduction is important. Okay, so lastly, I just want to show you a typical snapshots of the cold gas distribution. And we found that actually our simulation reproduced the diverse morphology of the cold gas seen in cold core clusters. And in these simulations, we actually found that the AGN uplifting and also the random gas motions in the ICM is the main mechanisms of forming these diverse morphologies, including the filaments in the Perseus cluster or the long tail in the Abiel 1795 system. Okay, so in summary, in general, we find that the conduction actually does more good than harm in the cold core clusters, because we found that actually the H-band should be completely or significantly suppressed because of magnetic tension and also by the turbulence driven by the AGN jets. And also the conductive heating can contribute up to 50% of the radiative losses in the very hottest clusters. And it's possible to find the observable signatures of thermal conduction in these very hottest systems. Okay, thank you very much.
Questions for Karen? Grant? So that's really nice. Thanks. So so your buoyant bubbles stretch field lines in their wakes.
Yeah.
So how long do the field lines remain stretched after the bubble buoyantly rises and moves on?
Right. So yeah. So basically, just comparable to the buoyant.
Okay.
Buoyant
So they disappear immediately.
Yeah.
So what's the net effect on conductivity? Is it enhanced or suppressed there?
So in the wakes is enhanced. Yeah, because the temperature gradient also goes in the radial direction. Yeah, but as you can see, the effect of the AGN is temporary. So yeah.
So the turbulence is very resolution dependent.
Yeah.
So I don't know. Did you do any like resolution studies to see if these trends converged or?
Right. So we actually done twice the resolution compared to this one, and the overall qualitative result is unchanged. Right, but I agree with you that actually the detail of like turbulent power spectrum or something that will depend on the resolution. Yeah.
John?
Hey, Karen, what off of her question, what was the resolution of the simulation you showed us?
So the peak resolution is 2 kiloparsec. Yeah. Mm-hmm.
And just a curiosity, so you're showing like the black dots,
Mm-hmm.
the cold gas. Are you like dropping
Right.
gas into like
Yes.
massive particles?
Right.
Following them?
Mm-hmm. Yeah. So for this particular study, we're focusing on the hot phase.
Right.
So that's why we used a drop-off for the cold gas. Yeah.
I should say thank you for doing this with the correct magnetic field strength. That's something that's been just sort of left hanging.
Yeah. Yeah. Mm-hmm. Yeah.
So do you have isotropic conduction in these simulations? And do you think that anisotropic conduction would affect your results in any way?
So these simulations are done in the anisotropic way, in the sense that the thermal conduction are only along magnetic field lines where the perpendicular is basically zero. And so the main result for our simulation is that actually the result should be quite similar to assuming an isotropic thermal conduction with a spacer value of 1/3 because of the turbulence that's within the cold core.
Last question, Grant? Right, so going on John's question, your cold gas here is still just really hot gas, slightly cooler hot gas that you put into a black box sink. So what's the temperature at which it becomes, you put it into this, your black dot? Is it 1,000,000 degrees?
So the black dots are the cold gas that's condensed out of the hot phase, and we removed it once it dropped below 5 × 10⁵ Kelvin. Yeah.
Let's thank Karen again. And the last talk in this session is by Timothy Linden from The Ohio State University.
Thank you.
Games. Yes,
Yeah.
you are.
You have to be very careful
and
with
I grew
that.
up in Dayton, so yeah. What's the source of the galactic center gamma ray excess?
Perfect. Is there a clicker? Okay. Thanks for having me. It's really great to give, I guess, what is going to be my last Einstein talk here at the symposium. So I'm going to talk about diffuse emission models in the galactic center gamma ray excess. I guess I switched the title. So first, how do you make diffuse gamma rays in the galaxy? Right? You start off, we think, with supernova, which give us most of the non-thermal cosmic ray power in the galaxy. They produce about 10 to the 51 ergs in a supernova explosion. About 10% of that goes into relativistic protons and about 2% into relativistic electrons. Those cosmic rays then propagate through the tangled magnetic fields of the galaxy. They move off turbulence, they get convected, advected, all sorts of crazy things. You can solve this numerically with some sort of cosmic ray propagation code. Eventually they stop because they hit something. That something is usually gas. If you're talking about cosmic ray protons, if it's electrons, you could do Bremsstrahlung gas, or you could hit, say, starlight and inverse Compton that starlight up to gamma ray energies. And when you do something like that, you produce some gamma ray map, which then, comes into our telescope, Fermi, or some other ACT, and we observe it, right? So what are the sources of diffuse gamma ray emission, or gamma ray emission in general, in our galaxy? Well, they're the point sources themselves, the supernova remnants, the pulsars, the things that are accelerating the high energy particles. Then there are hadronic interactions. This is normally the dominant mechanism for astrophysical protons. They hit another gas molecule. This produces a pi zero. That pi zero decays to 2 gamma rays. It's about 90% of diffuse gamma ray emission. There's Bremsstrahlung. So if electrons are hitting the same gas, they slow down. They produce gamma rays at the GeV energies. And you have inverse Compton scattering if they scatter starlight, right? And what's important to note is that there are order of magnitude uncertainties basically everywhere in this problem. How much energy, there's some uncertainty of a factor of few in how much energy goes into protons from supernova. The propagation is unknown by orders of magnitude and is probably very different in different regions of the galaxy. We have some models of gas in the interstellar radiation field, but those are plagued by tracers. And then eventually we kind of do know what happens when 2 protons hit each other, and so we have some models for that. Right? And the only way to constrain those is you compare with diffuse gamma ray observations, or you do local measurements of the cosmic ray primaries to secondaries that happen to make it to Earth. Right. So one thing that you might worry about is where do you actually inject these cosmic rays in the galaxy if you want to make diffuse gamma ray emission. So the cosmic rays in the galaxy are thought to trace the historic supernova rate. So not only the supernova that are going off right now, but those protons travel for some 10 to the 8 years or something like that. So you need to know where all the supernova happened over the last 100 million years or maybe more. So we need some sort of tracer for that. You could use, say, the observed supernova remnants. But then there are observational difficulties in finding supernova remnants that are far away or ones that are very old. You could look at the pulsars. Those are the compact objects that often come out of the supernova themselves. So you could trace those around the galaxy and attempt to use those to determine where the supernova actually went off. Or you could use OB stars, right? Those are the things that are about to go supernova in the future, so they might tell you where other supernovae are right about now. And those tracers are, due to low number statistics and some other problems, very coarse measurements of where all of the supernovae have gone off in our galaxy. And they've always been fit by these analytical prescriptions that have a cosmic ray source injection that peaks at about 4 or 5 kiloparsecs away from the galactic center and falls off as you get closer to the solar position and falls off very sharply as you go towards the center of the galaxy. Now that's good. There are lots and lots of supernova around 4 kiloparsecs from the galactic center along the plane. It's bad that it's falling towards 0 at the center. And also that these studies are axisymmetric. Of course, I don't know what's happening really on the far side of the galaxy, so I'm just assuming it's the same as the local part. And it's bad because it's not tracing a lot of things that we know exist in our galaxy that should correlate with where supernova are. For instance, we know there are spiral arms in our galaxy, right? We see them in all sorts of images, and then we make fake representations of them if you were, outside the plane of the galaxy. Supernova should be much more prevalent in the spiral arms because stars are much more prevalent in the spiral arms. But our models don't say anything about that. Well, in the galactic center, we also know there should be lots and lots of cosmic ray injection because we know there are supernova. The reason we know there are supernovas, there's a supernova remnant there, and there's a supernova remnant there, and a supernova remnant there, and another 5 or 6 in this image somewhere else. Right? And on top of that, Chandra observes 9,000 point sources in the inner degree. Around here, VLA finds bright non-thermal emission structures. There's lots and lots of cosmic ray acceleration that should go in there, and it's not in our models. Right? So what you're probably asking yourself right now is, when is this guy going to shut up so I can go eat food? But what I'm going to pretend you're asking yourself is, why are people using such poor models for cosmic ray injection when we have observational indicators that should be better? And the first reason, like I said, is just statistics. Right? It's very hard to know to take 50 models and build something that's not axisymmetric, that has a bunch of symmetry or something like that in your problem when you don't have lots and lots of sources to count from. The second reason is the theoretical motivation for building these sort of models historically, which has basically been you build cosmic ray propagation models because you want to know the ratio of cosmic ray primaries to secondaries at the solar position. You want to see what's actually coming into your instrument at Earth in terms of cosmic ray protons, in terms of the ratio of boron to carbon atoms or the positron fraction. And all of those depend really on what's happening over the galaxy at large. It doesn't depend on that small-scale structure. Cosmic ray protons, for instance, can propagate across the entire galaxy without losing appreciable energy, and most of them just leave the galaxy at all. All the structure gets washed out in local measurements. But that's not true for gamma ray emission, right? So there could be something very different when we're talking about trying to model diffuse gamma ray emission as opposed to trying to model diffuse cosmic rays at the solar position. So we want some sort of new tracer that is well motivated theoretically, and also we want to see if that tracer, develops a better fit to the gamma ray data. We have tons of it now. So our solution was to add an additional cosmic ray injection morphology that traces the molecular gas density. That's observationally resilient. We have lots and lots of tracers for the molecular gas density all over the galaxy. You can use CO, you can use CS, you can use all sorts of things and get, observations of all the molecular clouds. And it's theoretically motivated because molecular gas is the seed of star formation. And so the Kennicutt-Schmidt law tells you where there's molecular gas, there's star formation. And if there's star formation and there's some universal like saltpeter initial mass function, then that tells you where the supernova went off. So, you have this really nice model. And specifically, we adopt something here where we source a cosmic ray injection component that is 0 if the H2 density is below some given value, and then traces the H2 density for larger values, right? And so what does that look like in our models of cosmic ray injection? So here again is you've jumped outside the plane of the galaxy and you're looking down in X and Y. Here's what an old model looked like. This is where the fraction of cosmic rays tracing H2 is 0. We call that FH2. And so this is just cosmic ray injection tracing the supernova remnant distribution. And you see a big hole in the center. And you see no spiral arm structure. Everything's axisymmetric. Now you add in a model where you have 15% of the cosmic rays are injected tracing H2. 85% of cosmic rays are tracing still the supernova remnants. And you see already you've added a bunch of structure. There are now spiral arms. There's this bright galactic bulge in the center with a galactic bar structure that you see with a lot of cosmic ray injection. So it's something very different. And it's not only something different when the cosmic rays are injected, it's something very different in the steady state cosmic ray density that's observed or that is hitting gas somewhere in your model. So here are, as you take FH2, the very light colors are FH2 is 0, and then you just slowly turn the knob and crank up the fraction of cosmic ray injection tracing H2 up to 30% or so. And here's what happens to cosmic ray protons, the steady state distribution of them. At an energy of 5 GeV, it's about the same for all energies for cosmic ray protons because they don't lose much energy. For cosmic ray electrons, which do lose energy as they propagate through the galaxy, then it does change. It has an energy dependence, but you see this huge spike at the center. The other thing you should notice is out here at 8 kiloparsecs is the solar position, which is where, cosmic ray measurements can directly happen, and all the models are identical. So like I said, all the small-scale structure gets washed out by the time you get to the local solar position. And does this actually improve our fit to the data? So it does quite a bit. So this is as a fraction of H2, just turning this knob. This is the delta chi squared, and I'm not telling you the region of interest, but it's a broad 80 degree by 8 degree, 16 degree patch of the sky, which I'm calling, I think, let's see, inner here. Local is everything over a latitude of 8 degrees, so it's basically what's happening near the solar position. And outer, the fit actually gets worse, and the reason for that is mostly because our tracers broke down, because people hadn't looked in a lot of regions of the sky for H2, and the CO to H2 tracer is really bad far from the galactic center. But overall, our fit gets much better to the gamma ray data by something times 10 to the 4 in chi squared, and we prefer something where FH2 is 0.2 or 0.25. So that's great. Now, what does this do? And I see that a slide has been omitted at this point. What does this do to the galactic center excess? Because I know everybody has seen my previous talks, and they're like, when is he going to get to that? Because it always happens. So all previous diffuse models, and this is what the previous slide was going to say, all previous diffuse models have found that the galactic center excess is pretty resilient to changing different propagation parameters. So here is this 2 GeV excess that's centered around the center of our galaxy. It extends to about 10 degrees or so. It's bright. It's about 10% of the total gamma ray signal from that inner 10 degree area. And when you change all the propagation parameters, you get this kind of yellow shaded thing. It affects low energy emission. This becomes statistically limited. But, the bump itself has been a very resilient feature when you change cosmic ray propagation parameters. the slides just got switched out of order. Now you can see what I was talking about. So here's the 10% residual in all of these maps from 500 MeV up to 50 GeV or so. And we'll see what the next slide's going to be. Oh, the next slide's going to be the one I wanted it to be. So here's all the different models again from all the different papers, and this is the radial profile of the emission, and it's been about the same for every group's analysis, and it's been a consistent thing that extends for a long region. And you'll note there's been lots and lots of papers that have argued this, and that gives you some credence that people are doing something correctly, but they've almost all used those same background models that haven't injected new cosmic rays at the center. They've basically all used models where there was a huge production of cosmic rays right in the center in this region that we're analyzing. The one exception to some extent is Calore, who tried lots and lots of different diffuse models, but they never tried to change the cosmic ray injection. So here's what happens to the GeV excess when you change the cosmic ray injection. And you start adding a fraction of cosmic ray injection that traces H2. So you'll see the excess starts off really bright if none of the cosmic rays trace the H2 injection. There's a hole in diffuse emission near the center. And as you crank that up, the normalization of the excess component goes down and down and down and drops by about a factor of 3 by the time you get to the best fit global value, where it's about 25% of the cosmic ray injection tracing H2. What happens to the morphology of this excess? So here as you go out in degree, here's a normalized thing where this is, say, something that the NFW profile is alpha to the -1, so the injection intensity is alpha to the -2. And this is kind of what things used to look like down here. But as you crank up the fraction of gas that traces H2, it gets very flat. And so what you're seeing is just kind of some amorphous blob near the center that doesn't have a lot of structure in it. So one problem, or one caveat, which is what I've done here is I've taken the global best fit value of the H2, which I fit over the full sky. I basically did a sidebands analysis, and I forced that to be the fit at the galactic center. Now let's say I focus my attention only on the galactic center, and I don't use that as a prior. So I ask just what's the best fraction of H2, and what's the best fraction for my excess that actually fits the data the best. As I narrow my region and go smaller and smaller and smaller, in this fit I used a 15 by 15 box around the galactic center, then what I find is that the best fit value of FH2 goes from about 0.25 in the galactic center itself to about 0.1. And then if I go onto this plot, the best fit NFW excess at 0.1 is this third line down here. It drops by about a factor of 1.6 or so, but it doesn't drop near as drastically as it dropped when I forced FH2 to be 0.25 from my sidebands analysis. So there's a little ambiguity here and a little bit of, do you force your best fit on the full sky and then evaluate that from the sidebands and use it as a prior on the galactic center, or do you let everything be, equal and just let everything float and determine what your actual best fit to the data is? So that's an upcoming paper. We're going to look at this in a lot more detail and look at different regions of the sky and how the excess behaves. But to conclude, models of diffuse gamma ray emission have been long used very unphysical morphologies for cosmic ray injection. And they weren't unphysical when we were looking for the average cosmic ray spectrum that was observed at Earth, but they are fairly unphysical in examining the diffuse gamma ray emission over the full sky. And so we suggested a new tracer that's physically well motivated and does appear to improve by a wide margin the fits to the diffuse gamma ray sky. And previously, it was thought that no changes in the cosmic ray diffusion parameters were actually going to be degenerate with the gamma ray excess. People had tried to turn all the knobs, but this tracer seems to be. So a further analysis is necessary in order to resolve that degeneracy, and the preliminary evidence is intriguing. It does appear that as you increase the cosmic ray injection near the galactic center, that the normalization of the excess goes down. So I'll leave there. Thanks.
Questions for Timothy?
So in the CMD, my understanding is that the star formation is actually very inefficient. So you have a lot of gas sitting there, and you don't have enough star formation that you would expect from a Kennecott type scaling. So did you take that into account with?
No, it's not taken into account right now. And that could be, for instance, the fraction of gas tracing H2 goes down in the galactic center. That could be a reason that that's actually an expected phenomenon. And I think one thing to mention is that we're always adding these things in as tracers, but it doesn't necessarily mean that it's motivated by a Kennecott-Schmidt relation, but that doesn't necessarily mean that supernova go off At the end of the day, we're just using a tool. We're not actually, we don't know that supernovae are forced through the Kennico-Schmidt mechanism. But
Decrease your gamma ray excess production, though, because if you have less stars with the same amount of gas, you have less supernova, therefore you have less.
yeah, no, it definitely does. I think it would motivate a change in the fraction that traces H2 as you go towards the center. Of course, I guess the way to say that they're all tracers is then there's a fraction that traces supernova. So if the supernova fraction, say, even underproduces the Kennico-Schmidt relation expectation, which it seems to, then the thing that's too heavy or too high in the galactic center would want to, stay high. I'm not explaining this well. I'm using two different tracers. If one is subdominant, the other one has to be overproducing the excess in the center in order to get the actual result out that fits the Kennico-Schmidt law. But that's a good question.
There might have been a starburst in the galactic center a few million years ago, and that would have produced a lot of cosmic rays.
Yeah.
But now the present day H2 may not actually be, say, the H2 regions that produced that starburst a few million years ago. So it might be the case it's like a time lag thing.
Right. That was our theoretical motivation for moving some fraction to trace H2. And the reason is that, dense molecular clouds last about 20, 30 mega years in most of our ROI. Supernova also take, 5 to 30 mega years from star formation in order to actually go off. And so, some fraction of the youngest cosmic ray acceleration would be tracing the H2 gas density observed today directly. And some fraction would be tracing more historical markers. So we used supernova remnant because they can, trace some of the oldest supernova activity. But yeah, that's the motivation.
Question for the balcony, Doug.
So I thought our friends and colleagues, Lee et al., had just about convinced us that there was a population of point sources in the inner galaxy causing the excess.
I think that's also a possibility.
Is there a way their analysis could be fooled into seeing that, given what you're saying?
So given the change in cosmic ray injection, I think, cosmic ray injection gets pretty smoothed out before it produces gamma rays. So if everything's very point-like, and let's say the point-like thing is a realistic observation, there's no problems there, then that would be a problem. One thing is also that, in all those models for diffuse emission, the H2 gas that was used as a target is fairly diffuse, axisymmetric, doesn't have a lot of fine-grained structure. Where we know, again, in the galactic center, there's lots of molecular clouds that are dense. There's lots of fine-grained structure in the target densities. So if there's lots and lots of more targets that look point-like compared to, say, a few tenths of a degree angular resolution for Fermi, then you could potentially be faking point sources in their analysis, which is really low significance point sources, 1 or 2 sigma apiece. The numbers of those could actually be tracing errors in the diffuse modeling from the gas density. So we're working with them on a follow-up study where we take these kind of, I'm not going to go back and find the slide, much more refined gas models of the galactic center region that have a lot more point-to-point variation than old gas models that were used, and seeing how much of the point-like structure that soaks up.
There are no more questions. Let's thank Bimbe again. And we'll start again for
Yeah, that's a good idea. Oh wait, we already loaded it, right?
Maybe.
Yes.
He always does. Oh no, it's right there.
Okay, that looks good. All right, good. Looks good. Looks good. Yeah. Awesome. Just leave it on that so that. All right, cool.
Thank you. And the second person.
Yeah. I need. Hi. Oh, you emailed yours, didn't you?
Yeah, possibly twice. Did you get it?
I saw it once at least.
Yeah, the internet wasn't that great. I couldn't tell if it was sent or not.
Hi.
Can I upload my...
Yeah, do you have it? Do you have it on a thumb drive yet, or?
Yes.
Oh, okay, yeah, we can upload it. You're today, right?
Yep.
In session 4.
I think it's the next one.
Oh, right, yeah, there you are. Gonna test it.
Okay, yeah, that's session 5. 4 sessions per day. Yeah.
Okay, that works.
So good?
Yep.
Okay. Every day we start from the beginning.
Yeah, I mean, tomorrow's session 1, and today's session 5. Let's see what I got up here. Cover.
So it's in the file PPT.
This one?
Yeah. And there should be a symposium.
Just the PDF?
Yeah.
Okay.
Can I take a look at it?
Yeah, definitely. Let me get it loaded on. We'll check this.
I'm not saying you shouldn't have done it. You obviously should have done
Yeah.
There is just one slide that I would like to take a look at.
Okay, let's put it in. Yeah.
Okay, no, I
Is
just
this
wanted
good?
to see the colors.
Okay. The colors might not look exactly like that on the screen. The color balance is not
It
like
doesn't matter.
perfect.
I just wanted to check because with another PDF reader it appeared just gray.
Oh, I
So,
see. I see.
yeah.
Okay, cool.
Thanks.
Yeah. American, you gonna take off?
Yeah, before this stuff starts.
That's okay. Get out of here. Go then. Get out.
Dan Castro is here.
Who dat? Oh, yeah, that's right. Where is he? Oh, I see him. Have they made an offer on you? Give me that.
I don't know.
No.
Okay. That's one cheese for crackers.
cosmic rays.
I'm going to ask about cosmic rays, how they interact with the
Yeah.
if they do.
They do. They get wrapped up in magnetic fields. Interplanetary magnetic fields. But like, if she talks about modulation or like changing the size of the atmosphere, I'm not sure what that does to the cosmic rays. And it should be, if it's cosmic rays, it should be like smaller. You get more cosmic rays.
So she doesn't answer that outside.
No, I think it is much more complicated because it changes the energy spectrum. But I don't know. I mean, it's really hard to like when you said now we're going to write a paper on this, we're going to bring in someone else who writes bring it up. So yeah, that's where if the ionosphere is changing, then there's some consequences. Report back.
It's going to be something like that.
So this might not, it's supposed to be muted, but it might not be, so just don't say anything.
No, it's not muted.
So they're all loaded in here and everything, all these talks?
Yes, except for the last one, but we have to.
So please take your seat. So the first talk of the session is Constraining Supermassive Black Hole Binary Dynamics Using Pulsar Timing Data, and it's Justin Ellis.
Well, thanks for having me. This is my second Einstein Fellow talk. And last year I talked about, is this loud? It seems loud to me. Last year I talked about when we might hope to detect gravitational waves with pulsar timing arrays. And I said 5 or so years, so we're still consistent with that. We haven't detected anything yet. So this talk is basically an overview of a paper that essentially myself and a large number of the nanograph collaboration have been working on pretty much since last year at this time. So if you want to know more information than what I talk about today, there's this talk here. Hopefully it'll be out on AppJ soon. Okay, so just a quick overview of what I'm going to do. I'm going to try to give some background to this because this is fairly different from what most people are talking about here. So the first thing is sort of the big picture overview of gravitational waves and supermassive black hole binaries and the sources that we're looking to detect with pulsar timing arrays. Then I'm going to go over a little bit about sort of the current predictions, the current state of where we think the background level might be, and then I'm going to go over a little bit of sort of environmental effects that you have to have something to get these black holes close enough that gravitational waves can take over. So what are these effects? And then I'm going to go over some of the results from the analysis on the most recent nanograv data set. And then in the very end, I'm going to go over the beginning of trying to make some sort of inference about astrophysics from this non-detection. Okay, so the first thing is the obligatory pulsar timing slide. So I think everyone knows what the pulsar is. In this case, we're using millisecond pulsar. So this is a pp dot diagram. So this is it's the log of the period derivative, and this is the period. So we're using these millisecond pulsars, millisecond periods, but they're also extremely stable. So the spin down rate is something like 10 to the minus 20 seconds per second. And so basically the main idea is that you have this pulsar, you can see this radio jet, you measure the intensity with your telescope, and you essentially measure the exact time of arrival of when that pulse reaches the Earth. And then what you do is you're essentially just taking this measured time of arrival minus the model. The model takes into account everything we can think of from the pulsar to the Earth, including gravitational waves. And so we try to model all of this simultaneously. And we use an array of pulsars to try to detect gravitational waves. I don't actually have a slide on this, but you can't really detect gravitational waves with just one pulsar. This is why in our array we have about 37 pulsars now. And just to give you an idea, sort of I think this is probably messier data than maybe, actually people are astronomers in here, so they deal with messy data. But we deal with this pretty messy data, and this is actually cleaned significantly. The data, looks much worse than this in general. So it's a big data analysis problem like Rutger talked about last year, and he's going to talk a bit about today as well. Okay, so just to give you an idea of what we expect, the kind of sources we expect. So we have this idea, and when I say we, I mean essentially the entire astrophysics community, that the large-scale structures we see today, the galaxies we see today, are basically built up from major and minor mergers in the past. And we see, some observational evidence of this. And then we also have, in the centers of these galaxies, there are supermassive black holes. You can't really read the axes on these, but these are sort of these two famous M sigma and M bulge relations. So this is how the mass of the galaxy or the velocity dispersion of the galaxy is related to the mass of the black hole in the center. So we have these galaxies merging. We have some idea of how the properties of the galaxies relate to black holes in the center. So essentially that's meaning the galaxies are merging, also means these black holes are merging, producing gravitational waves, and you can get this spectrum of gravitational waves, in this case, or at least in the case we're looking at, from supermassive black hole binary mergers. And so this is sort of the whole landscape of gravitational waves. Really it goes down further if you want to talk about CMB type measurements. So pulsar timing is sitting around here in this nanosecond or nanohertz regime. So you might be more used to LIGO. LIGO's sitting up here in the kilohertz regime, and you have ELISA or something of the sort in the millihertz regime. And the way that you can think about this for at least half of the talk is the way that we're going to characterize this background is with the simple power law. Everything in astronomy is a power law. All right, so this is just saying that the gravitational wave strains, just how much it stretches and compresses space-time, it's just this power law. So this dimensionless amplitude is usually the parameter that we're going to want to set limits on, and the spectral index is usually fixed, depending on the kind of source we're looking for. So if you have supermassive black hole binaries, there's some prescribed alpha, which in this case is minus 2/3. So basically, in the most simplest type search we're doing, we're just trying to constrain this amplitude, so the strength of the background. But there's another part of this story. For gravitational waves to take over, there has to be some other physical mechanism to get them from basically parsec separations down to millisecond parsec separations where the gravitational waves can take over. If you only had gravitational waves, nothing would ever merge, It would take way longer than the age of the universe. So the main things that we're gonna look at a bit in this is stellar scattering and circumbinary disk interaction. So stellar scattering is just where you have basically stars from the galaxies colliding. There's lots of slingshot effects, and the system's losing energy due to scattering off these stars, and it drives the system to small orbital separations. Or you can have this circumbinary disk interaction, where you have this disk, and there's interactions with the gas on the supermassive black holes, and again, it's taking energy away from the system, and you're driving it to merger faster that way. And both of these at larger orbital separations, which I'll show in a second, are way stronger than gravitational waves when you're in a large orbit. So the end result of both of these is this so-called hardened binary. Right? So at this point, you have these things that drive it to small orbital separations, and then you just have gravitational waves taking over at the last stages of the merger. So sort of a byproduct of these environmental effects that have to drive the binary to these orbital separations is that they will most likely basically cause the binaries to come into the frequency band that we're sensitive to, cause them to have some eccentricity. Right? You have these stars scattering. It can cause the black holes to be eccentric. Also, if you have these torques pulling on it from gases, you can have an eccentric binary. So this is sort of just showing that, if you have these two different cases in some of these simulations, you usually end up with, decent eccentricities. But again, there's a pretty big uncertainty on all of these things. So this is just something that we expect. We expect stellar hardening and gas dynamics to cause eccentricities, but it's fairly hard to predict, how big or small that eccentricity is. But usually we expect something probably other than circular. And I'll mention, this is a big caveat in the analysis we do. I'll mention this a bit later. Okay, so this gets to the sort of search results of this analysis. And this equation is not really important. This basically just says that when we do this search, what we're looking for is this sort of characteristic correlation between pulsars at different angular separations. So this is, to us, it's famous. It's called this Hellings and Downs curve. It's just basically how this is the cross correlation of the residuals for different pulsars versus the angular separation. And there's a characteristic signature that we're looking for in there. And basically all this is saying is that we do this cross correlation basically tuned to look for this kind of analysis. And essentially this is just showing sort of a non-detection. This is essentially the upper limit, which is this red curve right here, and these blue points are basically the cross correlation values as a function of angular separation of the pulsars on the sky. So basically this is just a way of saying, we haven't detected anything, and we're basically dominated by a few pulsars in our array. So like I said, we have 37 pulsars, but unfortunately, we can time some way better than others. So in this case, we're dominated by a few pulsars, at smaller orbital or angular separations. So that's sort of just a detail, but you might hear things like, oh, we need more pulsars, which is true. We do have a lot of pulsars right now, but they're not, they're varying degrees of how well we can time them. Okay. Okay, so I call these the classic results, and I call these classic because essentially up until this year, every gravitational wave paper in pulsar timing arrays did something like this. They assumed this power law that I talked about in the beginning. They did some sort of analysis, and they put an upper limit on the amplitude of the power law. So essentially, this is just showing basically a perfect example of Bayesian statistics. So it's good to look at these two cases, because I'm going to mention these later. So these are essentially the PDF. So this is the probability distribution that we infer from the data set, which is the blue here. And the green are two different priors. Okay, so these priors are basically predictions for this dimensionless strain amplitude for two different models. And I'm going to call them the McWilliams and the Sassana model. These are the authors of these papers. I don't have enough time to get into the details of these models too much, but essentially the McWilliams model predicts an amplitude that's about 4 times bigger than the Sassana model. And so basically what we're seeing here is that our data is essentially updating the prior in both cases, right? So we're starting to say things, essentially under this power law model, we can rule out almost all of this model, and we're starting to say something fairly interesting about this model. And statistically, if you want to check the consistency between this model and the data and this model and the data, you get something like this model is 20% consistent with the data, and this is something like 1% consistent with the data. And this here is sort of just putting these limits on a sort of a landscape. So instead of just thinking of it as one number, instead of just thinking of it as a slice through this, what we really have is this full spectrum. So we have the strain versus frequency. And this black line just shows the upper limit we have, and these shaded areas are the predictions. And basically, the fact that these are not power laws at low frequencies is what we're really trying to investigate. And this is the new thing about this work. So, as we had with many other talks, you can't see the little shaded region there, but it's not too important. So now we're going to move beyond this assumption of a power law, which might sound simple, but basically up until now, the data hasn't been sensitive enough to really have any need to do this. So basically, this is what we're trying to get. This is the strain squared. This is how you get it. This is integral, essentially, over the merger rate times some sort of frequency evolution. Right? So you have some merger rate, frequency evolution, and then this is sort of just the amplitude of the individual gravitational wave sources. So this is how you build up this background. And there are sort of two separate ingredients that come into this. First is this sort of high frequency piece. And this is essentially controlled by this merger rate. This is just, how many galaxies are merging, what's the mass of black holes in those galaxies, how strong is the signal in the gravitational wave dominated regime. And this depends on these kind of things, the merger rate and the M sigma relation. Down here, which is much more interesting, also much less unknown, is this is where you might have these environmental effects. At low frequencies, means big orbital separations, you might start to see these environmental effects. So these are the things like stellar hardening, circumbinary disk interaction, and eccentricity. And so this comes into the frequency evolution piece. So these things are almost separable, and that's how we're going to move forward. And so I just wanted to quick mention this point right here. So this is basically preliminary analysis of trying to say something astrophysically about the population of black holes, but in the case of a non-detection. So what we're going to do is we're essentially going to use this prior that I talked about in the last one, essentially to anchor this piece, right? So it's anchoring this piece that's related to the merger rate. And then we're basically going to free ourselves and not make any assumptions about this piece right here. We're going to allow for some turnover, but we're not going to make any assumptions about what the source of this turnover is. But the main thing is we're going to sort of take these one at a time. So we're going to look at just stellar hardening, just circumbinary disk, and just orbital eccentricity. And so first, this is just the generic case. This is what we get for these two different models. This is the one that has the large amplitude prior, and this is the one that has the slightly smaller prior. And what you're seeing here is this characteristic strain, so the strength of the background as a function of frequency, and the color map is basically a PDF. So this is a 2D PDF. Basically, so what this is showing is that if you do happen to have this model with the larger amplitude, then you have pretty strong evidence that there's a turnover in your spectrum. If you have this model with a smaller amplitude, there's some evidence, but a little bit less. So if you use the Bayesian statistics, the Bayes factor for this is 22 to 1, and this is 2 to 1. So just quickly in the end, there's a couple slides here, but essentially they're all doing the same thing, just for different sources. So what we do is we take essentially this spectrum, we do some simulations, and we map that to a certain physical parameter of interest. So in our case, when we're looking at stellar hardening, the parameter of interest is the stellar density of the galaxies that are merging. And so what we try to do is we say, all right, the spectrum has some turnover. What stellar density would give us that turnover? And then we can basically make a posterior of that. And so what you see here is that in this case, for the more optimistic model, you basically need stellar densities of 10 to the 4 solar masses per cubic parsec. This is extremely huge. We'd expect something more like 10. Yeah, time is up. So I'll just quickly say that in all of these cases, for the more optimistic model, we're really starting to have some doubts about this model. You need pretty extreme situations. You need pretty high eccentricity, something above 0.7, or you need really dense stellar systems in which these black holes are merging. So really, this is the first time that anybody's done this kind of analysis with gravitational or non-detection of gravitational waves with PTAs. There are a lot of caveats, like I said. We take this one at a time, but this is really the beginning of being able to do astrophysics with pulsar timing, with even the non-detection of gravitational waves. And just quickly, I know I'm over time, just quickly, so this is all with a non-detection. We have to assume something about the strength of the background here. But in the case of a detection, we essentially have this. So right now we have to make these assumptions, and then we infer something later. But if we have a detection, we basically know this, and then we can really have more strength in inferring the astrophysics later. And I'll just leave up the conclusions.
I have a question about the eccentricity solution to this. So,
Well.
definitely in some numerical and analytic papers, it's argued that if you have binary hardening in a rotating stellar crust, and binary orbit is retrograde with respect to that, that will pump up its eccentricity. But it's hard to imagine why more than 50% would be in those retrograde configurations. Is there a different mechanism to get you to high eccentricities?
I know that's one of them. I think basically when you look at n-body simulations, the predictions for what the eccentricity is when you're coming into the pulsar timing band can essentially covers this entire range. So I think it's fairly, it's fairly unknown. But yeah, the major point is that if these models are correct, then this has to happen in some way. Otherwise, we need to go back to the drawing board and look more into the merger rates and things like that. Well.
No questions? Yes.
It's a very similar question. So I'm just trying to figure out what you actually see here. So you have the pulsars, and then you have tons of merges spreading through the universe, right?
Mm-hmm.
Do you then see an average spectrum of all these at the same time, or are you dominated by few close by, or is it a mix?
Well, technically we're not seeing anything, right? Because these are all upper limits. But what we're modeling is a background that we're not dominated by single sources. Basically, it's an isotropic bath of. Yeah, it's basically this isotropic bath of radiation that just has a certain quadrupole signature from the gravitational waves, and that's why you're looking at the correlations. Yeah, so most of the population models for this, especially at low frequencies that we're sensitive to, definitely predict a background, and it's fairly unlikely to see a single source at these low frequencies. You might see a single source that stands out above at higher frequencies, but our sensitivity, we're much more sensitive at low frequencies.
Other questions? So I would just ask you, is there an instrument coming along, or do you have instrumental capability that's going to increase, or whatever that you might find new and better pulsars and improve the timings of the ones you've got? Is there a breakthrough coming?
Well, there's there's good and bad news. The good news is that we are, even with the existing telescopes, so all this is from Green Bank and Arecibo, and you can sort of see right here that the uncertainties are much smaller than they are here. That's because we had essentially a hardware upgrade. Still using the same telescopes, but it's a hardware upgrade. We're observing the frequencies over a much wider radio bandwidth, and there's ideas of getting an even larger bandwidth. So you're basically getting the entire signal across a huge radio frequency range, a couple of gigahertz. The bad news is that there's a lot of pressure right now to essentially shut down Arecibo. I just got an email today that there's pressure for this, and Green Bank isn't looking that great. So if those are the main workhorses for this collaboration, if they're out, that's fairly bad news. There are still telescopes in Europe. There's the Parkes telescope in Australia. There's Meerkat coming up. There's potentially the Square Kilometer Array coming up. So that these, when those things happen, those will be really good for pulsar timing, but it's still pretty far off. So, in the pulsar community, we're really trying to say, look, we're doing cool science, way more than just this. So we really need to keep Arecibo and Green Bank around.
Okay, so your talk is an ad of sorts.
Yeah.
Okay, thank you very much.
Sure.
The next talk is identifying the remnants of neutron star mergers. 1.5 falling.
Here. Thank you. Oh, okay. All right. So my name's Wenfei Fong. I'm at the University of Arizona in Tucson, where I just looked up the weather. It's currently 73 degrees and sunny, and it'll probably stay that way until the very end of March. So if you're looking for a place to visit, spend Christmas, New Year's, whatever. Actually, it did snow for like 5 minutes on New Year's last year, but it's a good place to visit. Okay, so the question that I've been thinking about the past couple of months is what's left after two neutron stars merge? And to understand this question, I've been using radio observations taken with the VLA, pictured here, the Very Large Array in New Mexico. It's actually a really, really nice place to visit. It's really surreal to see these huge antennas kind of in the middle of nowhere in New Mexico. And I'll just warn you that this is very in-prep work, and I figured this was a good forum to share it since there's a lot of high-energy-minded people here, and so I welcome your feedback on this. All right, so what's left after two neutron stars merge? So the idea is that you have two massive stars in a binary. They're gravitationally bound together, they undergo stellar evolution, and they leave behind two neutron stars. Two neutron stars that are still in a binary, and eventually they give off gravitational wave radiation, and they merge and give off a burst of gravitational waves. And so these merging neutron stars are the premier systems for gravitational waves that Advanced LIGO is currently looking for. So Advanced LIGO came online just last month, so its first run should run until December. But it's currently looking for these neutron star mergers, and also the neutron star merging systems are also the progenitors of short duration gamma ray bursts. So understanding their underlying physics is really important for a broad range of fields. All right, so these two neutron stars merge together and produce a hypermassive neutron star remnant. And this hypermassive neutron star is necessarily spinning very rapidly due to the angular momentum of the binary, and also may acquire very large magnetic fields. So the idea is that there's initially a weak field that gets amplified by shear instabilities or some other mechanism at the merger interface, and so may acquire very large magnetic fields, and in this way we might call it a magnetar. So this hypermassive neutron star is stable as long as rotational, so it's supported by rotational support and also thermal pressure, but it's also balanced by gravitational collapse. So eventually, the standard picture is that gravitational collapse within 100 milliseconds or so eventually wins out and collapses to a black hole, shown by this black hole right here, with a transient accretion disk. And that transient accretion disk powers a relativistic blast and collimated outflow that we see as a short gamma ray burst. Okay, so this is a standard picture. Now, the interesting thing is that we know that there are magnetars, two solar mass magnetars, that are actually stable to collapse that exist in our galaxy. So I think we know two currently. And so there seems to be, the stability of this magnetar is highly dependent on the equation of state of this high density matter, as well as the actual mass of this hypermassive neutron star. And so my question is, how long is this stage? Is there a scenario in which there's a short GRB, but potentially there's a long-lived, and by long-lived I mean a few seconds or less, magnetar that can be imprinted on observations of short GRBs. And this would be very interesting for GRB physics because there's a great debate as to what power short GRBs. Is there an actual magnetar remnant? And that could also inform studies of the equation of state for neutron stars. Okay, so I've tried to look at observational signatures of GRBs and seen if there's any signatures of a long-lived magnetar in these. So indeed, there are kind of two mysteries in short GRBs that people have invoked to the magnetar, long-lived magnetar scenario. And one is this so-called extended emission of short gamma ray bursts. So this is the picture. This is a gamma ray count rate light curve. So this count rate versus time. This prompt spike is a typical short GRB. You can see it's very clean, less than 2 seconds long. It's very fast. And then this particular burst has a very long extended tail in the hard X-ray. So this is about 10 to 1,000 kilo electron volts or so. And this is about 10% of the energy of the actual initial spike. So it's really non-trivial. And about 10 to 15% of short GRBs have this extended emission. Hasn't been able to be easily explained. People have invoked the magnetar scenario, saying maybe it's a relativistic wind from the actual magnetar that's powering this extended emission. And interestingly, these extended emission bursts don't seem to differ in any other properties. Their environments are all the same as normal short gamma ray bursts. Their locations in their galaxies are the same, etc. All right, another mystery that people have been invoked to the long-lived magnetar scenario is X-ray plateaus. So in the, as Justin said, everything in astronomy is a power law. So when the short GRB interacts with the interstellar medium, it produces synchrotron radiation and decays as a power law. And so this is an example of a short GRB X-ray afterglow. So this is luminosity versus time. And typically you should see this initial emission just decay as a power law, but instead we see this pretty long plateau out to about 1,000 seconds, and then it decays as a power law. And so some people have thought that maybe these X-ray plateaus seen in these short GRB light curves might also be powered by a long-lived magnetar. This is just a zoo of them. This is a zoo of light curves with plateaus, so there's just more than one. And for reference, these are example light curves with no plateaus. You can see they're just very simple power laws. Okay, so obviously these signatures are not exactly ideal because they're confounded with the actual afterglow emission itself. You can say that maybe there's a plateau, but could be other activity going on, and the plateau needs to be bright to stay above the actual afterglow emission. So there's been kind of a need for a clearer signal to find evidence of long-lived magnetars. So this was put out by Nakar and Piran in 2011, and the idea is that maybe a long-lived magnetar can actually power a radio transient. And the idea is that you have two neutron stars, they merge, they form this hypermassive neutron star remnant, and this magnetar has a very large rotational energy. So given a period of about 1 millisecond, that means an rotational energy of about 10 to the 52 erg. So it's this enormous reservoir of energy that's not present in just a prompt collapse to a black hole. And so this energy, when coupled to the surrounding medium, effectively can actually produce a shock that emits synchrotron radiation in an isotropic sense, and the shock propagates outward at a constant velocity given a constant density medium, which we think neutron star mergers explode in. And so they propagate out at a constant velocity until a time when the shock sweeps up enough matter comparable to the energy that was dumped in. So at that time, the shock decelerates, and this deceleration time is proportional to the rotational energy, the density, n, and the velocity of the shock. Okay, so we can make our best guesses about some of these parameters, and as always, if we have a model with a lot of parameters, we fix a bunch and then fit for the last one. Okay, so in this case, I'm assuming a energy of 10 to the 52 erg, which is a reasonable energy for one of these magnetars, and a mildly relativistic velocity of 0.8, the speed of light, just to show you what the light curves look like. So this is luminosity versus time, and these are light curves for varying density. So between, this is 10 to the minus 4 down here, up to 1. And you can see that the light curve rises until this deceleration time when the velocity of the shock slows down, and then you can see that for a density of about 1 particle per centimeter cubed, the deceleration time is about 1 year. So these are pretty long-lived radio transients. I forgot to mention that modeling of this from the original people, Nakar and Piran, and also Brian Metzger, show that the peak is in the synchrotron, the synchrotron peak is in the radio band. Okay, so as you go to lower and lower density models, you can see that the deceleration time increases. That makes sense that it takes a longer amount of time in a low density environment to sweep up enough material to decelerate. And this scenario is not unlike a supernova shock, except in a supernova shock, you're exploding in a massive star wind environment, whereas here you're exploding in a constant density environment. So that's the basic picture. So I tried to use radio observations to actually explore this, and just to give context, existing radio observations of following GRBs are too early in general. So as I said, the deceleration time is about years, and so we have a really long time for this to actually reach the peak of its light curve. Okay, so this is a compilation that I published earlier this year of all of the existing radio observations following short GRBs. This is flux versus time, and there are 4 afterglows out of about 70 that were followed up. 4 afterglow detections here in these colors, and then a whole host of upper limits. So each of these triangles represents an upper limit. Thanks. And so you can see that the latest observations of these short GRBs are only about 200 days. So we wouldn't be sensitive to a long-lived magnetar remnant if that model that I presented is correct. All right, so I convinced the VLA TAC magically to give me time to test this magnetar model. In fact, I wrote this proposal when I was moving from Boston to Arizona for my Einstein fellowship. So TAC sometimes surprised me. I've spent far longer on some proposals that haven't gotten accepted. So, okay, so I chose 9 events with a previous signature of a magnetar. So either an extended emission or an X-ray plateau. And they also had to have a redshift so we could compute the luminosity. Okay, and so I looked at the data, and I wrote the abstract before actually reducing all of the data. And so these are all the radio images, and the yellow circles are the positions of the GRBs. And so we're looking for some sort of source in each of these images. The images were taken at 5.8 gigahertz, which is the band with the most sensitive band of the VLA. And just for reference, a radio source should look like that. And so you can see I looked at the data and took Christine's advice and didn't find anything. So sometimes it's kind of sad to be an observer, but not every day. Okay, I don't regret it. Okay, so, but the VLA is very, very sensitive and powerful, so we can use the upper limits, take a positive spin, and try to say what can the upper limits tell us, what constraints can they place on this magnetar model. All right, so this is just one example. This is a burst that happened in 2013. These are the model light curves, the varying densities. This is the density constraints we can place from the actual afterglow. So this is an independent constraint. And then if you put our limit from our recent radio observations, you can see it lies right here and constrains the density to about 0.08 particle per centimeter cubed. So really, really low density environments. And in this case, it also is not in conflict with the afterglow constraint. You can see that in this particular case, perhaps a density taken at 8 to 10 years, or observation taken at 8 to 10 years after the burst will be much more constraining. So look forward to that. All right, this is another example where this was a burst in 2008, and these again are the model light curves. They're much, much brighter because this burst is at quite a low redshift. And again, these are the densities. And so this particular burst from the afterglow had an upper limit on the density of about 0.05 particle per centimeter cubed, so that's the light curve. And then the constraint placed from our limit was 0.002 particle per centimeter cubed. So that means that if a magnetar were to exist with these parameters, they would have to explode in a very low density environment. Okay, so this is the whole zoo of light curves, and you don't have to memorize this, but just to show you that each kind of burst has its own unique story, and especially the ones with afterglow constraints. None of the magnetar upper limits actually violate those. Okay, and so just putting everything on the same plot and converting it to luminosity. This is luminosity versus time. Again, these models, and these are all of our upper limits. So you can see we're really pushing down to very low luminosities, sometimes 10 to the 38 erg per second for this. And so that means that if a magnetar were to exist, it'd have to explode in an extremely low density environment. And in the interest of advanced LIGO, so advanced LIGO will be discovering dozens of neutron star mergers soon within a volume of 200 megaparsec. And so this is so if we are able to identify the electromagnetic counterpart of an advanced LIGO source at 200 megaparsec, and then repoint a few years later with a radio telescope, this is the type of limit we would be able to place on the luminosity of a magnetar. So really, really low, about below 10 to the 37 erg per second. So it's kind of a very promising, hopefully, test of whether long-lived magnetars actually exist. Right now, I've had just the cosmological sample to work with at redshifts about 0.2 to 1, but when we actually have neutron star mergers in our neighborhood to work with, we'll really be able to test this scenario. Okay, so just a summary. So I've shown you this model that perhaps neutron star mergers can create this radio transient. I ruled out long-lived magnetars for densities greater than about 0.01 to 0.1 particle per centimeter cubed. Again, this is very in prep, so I plan to explore additional parameters, like I just fixed the energy and the velocity, but by changing those, how can that affect the constraints? And then just considering future observations in the area of advanced LIGO. So thanks.
If you had an X-ray polarimeter that you could just point instantly as soon as you trigger an event, would you be able to tell anything about this model by watching, or do you have any idea about that?
That's a good question. Like immediately after the merger, maybe. So yeah, like the extended emission that I showed is thought to be from a relativistic wind or something from this magnetar. So maybe, or you might even be able to see kind of the actual collapse of the black hole. So that would be my best guess for kind of the signatures that you might be able to see. But that would definitely be useful.
Is there any difference between the radio emission from magnetar and radio emission from ejecta that you would have? Can you differentiate between the two?
Oh, from the actual afterglow?
From matter ejected by the...
Oh, matter ejected. No, actually, so the original Nakar Puron model actually came from ejecta from the... this was actually modeled from actual ejecta. And so the mechanism is similar. Yeah, you'll produce synchrotron emission. Yeah, so it might be difficult based on the kind of, if we were able to get a really well-sampled light curve, we might be able to differentiate between the magnetar and scenario and just ejecta. You might need an accompanying wavelength. Yeah, that's a good point.
So post-coalescence, you do expect the magnetar, immediately post-coalescence, to be in this cloud of ejected debris, explosion debris, right? Which would be high density, presumably.
Yeah. Wait, so after for when the magnetar collapses, yeah.
It has a lot of junk around the
Yeah.
explosion site,
Yes.
right?
Yeah.
Can you get a really, really short-lived radio burst then because you have very high density?
Maybe, although I think so a lot of the matter goes in, either gets ejected if it exceeds the escape velocity of the merger, or it goes into this kind of transient accretion disk, a lot of which goes into the GRB. Yeah. So I'm not sure about in the radio what would happen. Yeah. Yeah. Yeah, it's not an extraordinary amount.
My question was, how important is absorption in radio frequencies in that model and in that time?
Yeah, so we assumed that in this scenario, I assumed that we're above the self-absorption frequency. If we were below the self-absorption frequency, the magnetar models would predict much lower fluxes. Yeah. Yeah. Although we assume that by kind of year timescales, that the self-absorption frequency would have already passed through the radio band, and so we don't expect to be self-absorbed at that point, just because the timescales are so long. But that's true. Yep.
So if you were to look at it with some bigger dishes, would it help? How much?
Yeah, I mean so ALMA, for instance, operates, unfortunately, for this project at kind of higher frequencies, and the spectral slope is disfavorable to higher frequencies. So if we had something like ALMA for in the north and at the correct frequencies, that would be helpful. Yeah. But
Other questions?
yeah, that would be very different. So that would be much like a supernova shock. I don't exactly know how exactly the light curves would change, but so the initial kind of power law light curve would be time varying, actually. So it wouldn't just be a constant velocity, just because your number density is decreasing. So I think your transient, the radio transient wouldn't brighten as quickly, if I'm thinking about it correctly. But yeah, that would definitely affect things. We think most neutron star mergers, by the time they merge and explode, are kind of in the middle of nowhere, or at least in the ISM. And so we don't expect them to have a massive wind environment, but and at present we don't have the type of data to constrain that.
Thank you. Thank you very much. Good to see you back.
Oh, thank you.
So the next talk is quite a long title here. Unleashing the Electromagnetic Beast. Simulations of disk-induced field line opening and accreting millisecond pulsar magnetospheres.
Yeah, my title is too long and overly dramatic. I'm sorry about that.
No, it's good. We needed it, so.
All right. Okay, 2 talks left. We're almost there. Just dig deep and we can get through this together. If anyone needs to take an emergency nap, I won't be offended. All right. Okay, so it's good to start local. You are here. This is the Earth's magnetosphere, so it's the region of plasma surrounding the Earth that's dominated by the Earth's magnetic field. It's extended into this kind of tail geometry by the solar wind coming in from the left-hand side of the screen here. And something that's actually in some ways somewhat similar is the magnetosphere of a pulsar. In this case, there is no additional object. This thing is just purely isolated. And this open magnetic geometry is determined entirely by the rotation of the star. So this point here is the light cylinder. So if you were co-rotating with the star at this point, you would be moving at the speed of light. Therefore, you can't co-rotate with the star out beyond here. That's why all these field lines are being forced to open. The color is toroidal magnetic field. So you have magnetic stresses being applied by these open field lines onto the star, and that extracts energy and angular momentum for the star, and it flows out in this pulsar wind. So this is strong magnetic fields, low plasma density, energy comes out of the star. So the question is, what happens if we stick an accretion disk in here? Something that may or may not have its own magnetic field and has high plasma density. Is it going to do anything interesting and anything observable? So why are we interested in this? So there's a few different things. One is torques have been in accreting neutron stars that you see via X-rays. You can measure these torques, which cause the star to spin up and spin down. So this is actually the very first ever detected X-ray pulsar. And even in this first detection paper, they reported torques that were changing on very short timescales, hour timescales, showing the star spinning up at different rates, different torques being applied to the star. And one question is, what's doing this and why is this happening? The other thing is, if you look at the distribution of very rapidly rotating pulsars, millisecond pulsars, you see that there's a cutoff in what would otherwise look like a uniform spin distribution. So this is stellar spin frequency, star, 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 and then nothing. So the question is, why are there no stars out here? We know that we can detect them. There's no reason that we shouldn't be able to detect stars out here. So what sets this upper limit to the spin distribution of the stars? And then finally, jets. Everyone likes jets. This is SIR-X1. So this is a neutron star that's powering a very relativistic outflow. Lorentz factor of gamma about 15. Powerful 10 to the 36 erg per second jet. Is what powers this kind of jet similar to what powers the jets coming out of black holes? Is it something completely different? It's not really known too well at the moment. All right. So going back almost to the first slide, the question then arises of what does the magnetospheric geometry look like when you have a accretion disk around the star? So there's two main possibilities. One is mostly closed, going back to the 70s. You see field lines that go in from the star into the disk, and they couple the star to the disk in a sort of quasi-steady state. The other option is that the field lines are mostly open, so that if the disk is a very good conductor, they won't be able to slip through the disk. The field lines won't be able to slip through the disk, which is required in this picture, and therefore they'll be excluded from the disk, and they will be in this kind of open configuration here. And this will determine, what torques are applied by the disk to the star, and what if you want to produce a jet from the star, what that jet would look like and how powerful it will be determined by things like this. Okay, so one interesting possibility that's been discussed for a long time is the possibility of opening field lines that otherwise would be closed from the disk. So those field lines that would intersect the disk coming out of the star here, because you have a mismatched angular velocity between the stellar surface and the disk, you build up toroidal magnetic field that builds up pressure and basically pushes the field lines open. And that was discussed here. And then this is kind of a steady state simulation showing this happening with a realistic Keplerian disk and stellar rotation. So basically, you cause these field lines to inflate outwards and then eventually go out to infinity. And you get these open field lines that can channel energy and angular momentum out of the star. Okay, so this is a simulation that I'm going to show that comes from my force-free code, Fedra. It's a pseudospectral code that simulates force-free electrodynamics. So force-free electrodynamics is MHD with the magnetic field strength turned all the way up. So you can basically say it's good for those situations where you can say that I can ignore the rest mass density of the plasma, like in a pulsar magnetosphere. So what we have here is this is the light cylinder. This purple thing is the outline of the disk. So in this case, there's no MHD in the disk. The disk is just imposed. So it has a constant magnetic diffusivity. It has a constant, an imposed angular velocity profile, so it's purely Keplerian. And in this case, I'll talk about cases where you have accretion velocity, but in this case, the radial velocity in the disk is set to 0. So here is the co-rotation point. So at this point, the disk Keplerian velocity is equal to the stellar rotation velocity. And I think that's all the important radii. So the color is going to be toroidal magnetic field, and the black lines are poloidal field lines. So you set everything rotating. This is just a potential dipole. You set everything rotating, and we see what happens. Okay, so you just like in the thing I showed before, you build up toroidal magnetic field, which increases the magnetic pressure, opens these field lines. You form a current sheet along here, which reconnects. You get this sort of tearing plasmoid-dominated reconnection, which outflows. So you have this kind of Y geometry here. So these field lines are subject to magnetic diffusion out through the disk because of the way that they're being caused to bend by this powerful pulsar wind coming out of the center here. And we let it go, and it keeps basically getting pushed out. So in the case where the accretion velocity into the disk is smaller than the slippage speed out through here, you actually just push all of this stuff out, and you relax to this nice, very simple steady state where all of this stuff is basically radial. And you got a little bit of interesting stuff going on in here where the field lines couple to the disk inside the co-rotation radius. All right, so opening of field lines, current sheets, everything's eventually settling down to something nice and simple that we can model with some simple analytic model and hopefully apply to some data. So this is the torques. N is always torque for that movie I just showed. So this red line is the spin-up torque, causing the part of the torque, those field lines that want to cause the star to increase the spin frequency. Black is spin-down torque. So this is coming off the open field lines mostly. This is coming off those field lines that are coupling to the star inside co-rotation, so these ones here. So you see that you basically are coming to some sort of steady state eventually. Okay, so I also did this with radial velocity, something a little bit more realistic, a disk model that was more realistic. And I found that the amount of open flux, for example, or the spin-down torque on the star was very, very similar in cases where the disk is pretty thin. So that's what I'm going to be mostly interested in here. So I think we can go forward with the kind of simplified model. So this is the final steady state for what I showed. So what you, and this is the case where you have the same thing, but where the disk doesn't go into the co-rotation radius. So it's basically the same thing, apart from you don't have this more interesting region, and you have less field lines that are opened here. So the interesting thing here is that what this basically looks like is like the isolated pulsar I showed on the first slide, right? So you have all these open field lines, and if your disk conductivity is large, you have less, as you increase your disk conductivity, you have less and less field lines coupling to the disk in here. And basically, your entire thing is going to be dominated by these open field lines here. And you know how the spin-down power of a just isolated pulsar like this depends on the amount of open flux. So this is spin-down power is related to the omega, spin frequency of the star, times the torque. And it all just scales quadratically with the amount of open flux. So now if you have a simple model for what the open flux does in the case that you have an accretion disk, you can then come up with a similarly simple model for how the spin-down power or the torque on the star varies in the same situation. Okay, so we wanted to come up with something like that. And the simplest thing that you could possibly do is say, well, if you had just a pure dipole, like in the initial conditions of the simulation, you know what the flux looks like. It just increases, it decreases like 1 over r as you go away from the star. So we'll just say that if the disk would open all of the flux that would otherwise intersect the disk from the dipole field, it should just go like light cylinder divided by magnetospheric radius times the open flux you would have in the isolated case without the disk. So magnetospheric radius is just the inner disk edge here. So this is going to be our model for the amount of open flux. Okay. So using that simple model, you just get this black dashed line here, and this is some of the simulation results for increasing magnetic conductivity in the accretion disk. And you can see that although it's not perfect, it does seem to mostly give you kind of order of magnitude pretty similar results to this pretty simple model, and it agrees better and better as you increase the conductivity in the disk. So this is the amount of open flux. And then if you think that the torque should just scale like the square of that, you look at the spin-down torque applied in the simulations to the star, and similarly you see that it mostly scales pretty nicely with the simple model that I showed before. Okay, so with the model in hand for the spin-down torque, you can then put it together with the other parts of the problem to say what the torque should be like in different parts of the evolution of the star. So the idea is that you have amount of open flux scales with light cylinder divided by inner disk radius. Putting in the zeta parameter, this is just some kind of efficiency factor. So zeta goes to 1, this thing gets maximally efficient and optimistic. And you can put it together with the other parts. So when the magnetospheric radius is inside co-rotation, you have both the enhanced spin down and you have a spin up torque just coming from the matter that's accreting onto the star. So this is transmitted via the magnetic field, of course, but you can estimate the amount of torque just by mass accretion rate times specific angular momentum at the inner disk edge, just root GMRM. So if your disk ends between co-rotation and light cylinder, you just have the enhanced spin down from this pulsar wind, and if your disk is outside the light cylinder, it's just the isolated case. You don't get any change. Okay, so then you can, these are all the sort of standard models that have been published in the literature over the years, and this is what I've been talking about here. For a particular star at varying accretion rate, and you can see if you sort of look at this carefully that for some of the conditions you get significantly lower spin up at high accretion rate because you have a lot more spin down coming from all these open field lines. In this case, so Cassie is a parameter that determines, that basically relates your disk inner radius to the simplest spherical estimate of what the inner disk radius should be. So this is the alpha inner radius. So this gives you some, you basically parameterize all your ignorance about how the disk truncates into this Cassie parameter. Okay. All right. So the other interesting thing that I wanted to talk about was jet power. So of course, if you have all these open field lines, if they're somehow collimated by something like a disk wind outside the star, this could be basically collimated into a relativistic jet. So if you want to use the same estimates as before for estimating what the power of this jet would be, you plug in some numbers, you actually get a pretty high jet power, which is easily powerful enough for stars that are kind of 300, 500 hertz with about 10 to the 8 Gauss field at the stellar surface. They're powerful enough to power things like SIR-X1 or SCO-X1, some of these powerful radio jets coming out of atoll-like neutron stars. Okay, so in terms of torques on the star, there have been some interesting systems. These two here, I won't spell out their telephone numbers, where there have been no detectable spin-up, even when you have these very strong accretion episodes where you see large X-ray luminosity. You should be able to measure a large spin-up if the mass accretion rate is related in the expected way to the X-ray luminosity, but instead, when you actually look at the timing solutions, you actually can't see any detectable spin-up. And one possibility for this is that the reason you don't see spin-up is because at the same time you get a very large increase in your spin-down. And if you use the model I showed earlier and plug in some fairly reasonable estimates for what these different parameters should be, the effect is large enough to basically cancel out the increased spin-up during the accretion episode. There have been two other sources where you see also you get timing solutions during accretion episodes, and you don't need any enhanced or anomalous or additional spin-down in these systems. So obviously, if this is the answer for these, it doesn't happen in every single system. Okay. Another thing that can happen is that this spin down from these open field lines can be strong enough to actually put the star into spin equilibrium, so that the spin up coming from the accreting matter is completely balanced by the spin down on the open field lines. And you can, you just basically equate these two things, rearrange it all, and you get equilibrium spin frequencies depending on a whole bunch of things. The interesting thing is that it looks like for, these kind of combinations being roughly unity, it looks sort of like the maximum cutoff spin frequency that I showed in the initial slide. A couple of, good few hundred hertz, but less than a kilohertz. And then another bizarre thing about this is because the model is so simple and geometric that if you have spin equilibrium and it's given by the equation I showed before, this very simple relationship holds with the magnetospheric radius divided by the light cylinder is just given by this simple combination of the parameters. And if this holds, and we know that if you see something as an accreting millisecond pulsar, you see channeled accretion, that the magnetospheric radius must be outside the stellar radius. And that then gives you a maximum spin frequency for these magnetically channeled accreting millisecond pulsars. And you can look at it and see that, well, if this is about a half, which is most simulations have been showing, and you have some large efficiency factor, say 0.8, it gives you roughly the ballpark of the cutoff spin frequency that I had showed before. Like, it's usually taken to be about 700 hertz. Okay. And that's the end of the time. So that's my summary. Okay. Okay.
Because if it's very low, then the turbulence would be suppressed, and field line mixing would then be suppressed. And so you would naturally get these more open field lines. Whereas if the Reynolds number is higher, you get more reconnection events.
Yeah, so the idea is that the magnetic Reynolds number should be very high in the corona, like the magnetosphere above the disk, but it can be a lot lower in the disk. So you should have you should be able to see the separation between the two.
But in your simulations, it's lower than it would be in reality, for sure.
Probably. I was thinking of it mostly in terms of conduct. Well, I mean, the simple kind of conditions I've been putting in, I don't think you're not driving it in the right way to get turbulence, right? If this was three-dimensional and you have kind of vortical things in the disk, then you may get more turbulence. But you would expect a lot of reconnection. I think we're definitely in the regime where, I mean, you see this kind of plasmoid-dominated kind of reconnection. But there's nothing other, when the current sheet goes away, there's nothing there that would reconnect. You need to form the current sheet, then it reconnects, and you form it again.
What's the time scale at which you reach the equilibrium spin?
So in this, oh, you mean in the kind of the simple model applied to data and stuff like that? That's a good question. I've mostly been thinking of this in terms of like a steady state. That'll determine a lot on what the mass accretion rate onto the star actually is, because you expect that to kind of go up and down a lot over time, and you probably don't expect you to ever actually hit true equilibrium. It's going to be this kind of effective. Yeah, there might be. I should think about that. Yeah.
Are you asking about the time it takes for the spin of the star to change and go to equilibrium, or the time it takes for the magnetic flux to leave?
I think the first one.
Yeah, to alter the spin of the star to match or whatever m dot and field you have set up.
Any questions? If not, let's thank the speaker. So the last talk today is by Rector Van Ostrom, and it's solving pulsars from scratch.
Excellent. Good. 2 years ago, I came here for the first time, and I said that within a year I would have fully analyzed the international pulsar timing array data sets. That didn't happen yet. It's a big problem with collaborations that there are delays and putting out data sets and stuff like that. But in order to make up for my promise, these are preliminary results from the IPTA data sets in black, which combines these individual pulsar timing arrays. And you can see that the line is below the level for all of the others, which is approximately what you would expect. This upper limit here is somewhat disappointing because individual PTAs have already updated their data sets, which are basically more constraining than this, which is why there's a lack of enthusiasm to analyze these IPTA data sets. Anyway, so I won't be talking about that because it's not interesting. I want to talk about a little side project I've been doing this year, solving pulsars from scratch. As Justin already explained earlier, we want to time pulsars very accurately. We do that by comparing the measured time of arrivals from pulsars with the expected time of arrivals. These are our timing residuals, our basic data, which will be affected by gravitational waves. If gravitational waves are present, then they will shift our timing residuals a little bit, and that will be visible in a correlated signal across pulsars. If you see angular separation here, cross power between different pulsars, this is a hugely visible signal of a stochastic gravitational wave background in our data. Our actual signal will never look anything like this. This is very idealized, but this is the type of stuff we would be looking for. So in order to get this, we need a lot of pulsars. And when I say a lot, I mean we don't have enough yet. So we continue to look for new pulsars, and the more the better. So especially in the era where the SKA comes online, we'll be seeing many more pulsars that we currently can't see due to lack of sensitivity, and we need to incorporate these in our timing arrays. The problem is that once we find a new pulsar, we need to come up with a way to accurately describe these pulsars in terms of their relative motion. We need to have a so-called timing model. When we observe these pulsars to a level of 100 nanosecond timing accuracy, that means that you need to have an accurate description of the pulsar's trajectory relative to the Earth to about a couple of dozen meters. So that means you need to know the orbit extremely accurately. You need to know its position extremely accurately and all that. But we can't solve for the orbit very accurately until we can analyze these timing residuals. But we can't get the timing residuals unless we have the timing model. So there's this bootstrapping problem. And this is a significant problem because of the following. Let's say that we have a very simple 28 millisecond pulsar, which is in a binary. Most millisecond pulsars are actually in a binary. And due to the binary motion of the pulsar and its companion, there's going to be this extra binary delay simply due to the fact that the pulsar is rotating its companion. And we want to know what this signal is going to look like when you look at the timing residuals. Well, there's going to be this thing called phase wrapping. If this millisecond pulsar is 28 millisecond rotational frequency, then this is what you're going to see in the timing residuals. You don't see anything. And that's because you don't know which pulse is which. And this is the basic problem when you first observe a pulsar. You can't distinguish pulses from each other. So in order to get a coherent solution, you need to somehow bootstrap the system. Let me show you how that is currently done. And this is why solving pulsars is considered an art. This is an initial data set. We have basic idea of what the parameters are. We've already been observing this pulsar in the discovery phase, and we did a couple of follow-up observations. We know approximately what its period is. We know its position, and we plug it in tempo 2. This software package has been written less than 10 years ago, and in their infinite wisdom, these people decided to make a PG plot interface, which is which is awesome. So this is state-of-the-art pulsar timing, all right? So let's see what is typically done. We're going to select these observations right here, and we're going to zoom in, and we see that. Okay, this somewhat looks, like there's a straight line in here. Let's see if we can add a couple of phase wraps, reorder reassign the pulse numbers, and bloop, you get this sort of straight line. That looks promising. Let's see if we can fit something to that. And then you get this following plot, and you see this little somewhat arclet over there. Let's zoom in, and let's fit a couple of more parameters. Let's do that again. We zoom in, and then you see something like that, and you fit more parameters. So basically what you do is you start fitting a straight line, then you start adding more timing model parameters until you get something reasonable. Okay, let's look at that. We are now at this position. Maybe we can fit a couple more parameters. And boom, your timing solution explodes. And this is very frustrating. We fitted for some parameters that were not constrained by the data just yet, by this number of data points, and you have to start all over because there's no undo button. Also, this is very, very frustrating. And especially this blowing up of the timing solution. If you just place a prior on your timing model parameters, you can prevent that from happening.
Sorry, is this particular pulse have a companion?
Actually, this one does not. This is a lot more difficult if you have a companion. Unfortunately, I won't be able to talk about that, but that's something I've been including in here as well in my work. Anyway, if you finally solve the pulse, or you see something nice with a fairly consistent chi-squared, we should, reduce chi-squared of 10 or maybe a couple of dozen is not too uncommon because, it's astronomy we're doing here. But you typically have a couple of microsecond timing accuracy instead of something of the order of milliseconds here. So my first approach to this problem, I wanted to I like to do fun new data analysis things, and I wanted to look at this. So my original approach was to include an undo button and write this interface in a little bit more modern environment. So yeah, I had these ideas of what I wanted to include. The real kicker was to include an actual IPython console in here so that you could do some actual science while you were doing this graphical interface thing. But that's still an interface. It's not the actual science. The whole problem I had with solving pulsars is that it's considered an art. And I don't think that any of our science is supposed to be an art. Something should be just well-defined, and we need to be able to do it. So let's see. I wrote this. I started to play around with the problem, and I came up with this thing, which I'm calling algorithmic pulsar timing. The idea is that if you have a binary model like this, and you zoom in, then at some point, if you somewhat know what the binary model is, then you should be able to make a prediction of until when you actually know what a timing solution is doing. You should know when you're going to start to phase wrap around. And I was able to phrase this in terms of what you can call a coherence length, where I was describing the timing model as a so-called Gaussian process. So basically, you assume that you know the timing model parameters to a certain accuracy, and you can use that to project into the future how well you know how well you can predict basically what the timing model is doing. So if you do that, you take a par file. This is our language in which we describe the timing model, just timing model parameter with the value and the uncertainty with which you know the value. And if you put that into a timing package and you start extrapolating, then initially, if you just only use the prior, you get these red lines here. Basically, I sampled the prior, which have some broad distribution. I randomly sample from it. I plot what the timing model is, and that gives you a reasonable idea of what the uncertainties are of your model. These yellow points here are the data. I haven't fit any data at this point. So let's see what happens to our timing model when we update it with the information of one observation. Then you get that. All your red points now obviously go through the observation with, if there's a large error bar, then there's a larger spread there, which you update your timing model, and then we see whether we can make good predictions of which data points to include. I plotted the pulse period here in green, so that's basically where we start to phase wrap, and we can see very, very clearly that we can include a couple more data points. Remember, I don't have to select which parameters to include in my model because I've used the prior, so I always fit for everything. So I include a couple more points here. I keep doing this, and I start to build up my timing solution. There's some extra stuff that sometimes happens. Sometimes you change the receiver at the telescope, or there's some other stuff happening, so you can have a phase jump. You can all include those type of parameters, just like we usually do in our real data sets. You can model that just the same. It's not necessarily an art. This description always works. So the idea is that basically this fitting procedure, it's almost instantaneous when you let the computer do it. So even if you don't have enough data at some point, you can still search over these phase wraps algorithmically and much faster than a human can do it. A human maybe in a minute can click on refit a couple of times and make a decision. A computer can do this maybe 1,000 times in a second. So you can really explore larger parameter spaces this way. This potentially has great advantages. The nice thing, I think, also, what this kind of approach offers is that it allows us in advance to produce an observing schedule, which tells you how to more efficiently use your telescope. Right now, we discover a pulsar, we observe it as much as we can, which is very expensive, especially if you use a telescope like the SKA, and now we can drastically reduce the observational time and basically do this algorithmically, so no more grad students solving pulsars. So yeah, that's basically this idea that I had. It's all still very preliminary, but I also already have some initial software online that does this stuff. Yeah, and I don't know if anyone has any other ideas, but I'm still very much working on these type of interfaces. And yeah, if anyone knows something better than Qt and IPython merging stuff and all that, then I'm very open to suggestions. Anyway, thank you.
Questions for Rutger?
So I did not see anything about Fourier transform or something like that. Like it just looks like you have one parent here, you have another parent here, so that this segment in some way. In the first thing you think is to look in the 3D space. Maybe I misunderstand something, but why are you first working in real space?
It's slightly different. So what we're talking about here are radio pulsars, and when you've discovered a radio pulsar, then you already know with which period to fold the data. All that pulsar searching and doing Fourier transforms and all that, that's when you're trying to discover a pulsar. We found a pulsar, we know its period, we know when to fold, and we can make time of arrival data somewhat accurately. You don't need to know the pulse profile, you just use a Gaussian profile in order to time it, but that's already done. That's something that's been done before. Now it's the problem to use these initial TOAs to get a proper timing solution, so you can redo the folding of the data. So that's one step prior to this.
I just wanted to say something, because I feel like if you don't know about this, nobody's going to believe anything I said in the previous talk. Yeah, so this will work on with any set of TOAs, but its main thing is like right the first time you're getting the solution. It's hard to find this timing solution the first time. You got to do all this crap like partnership. But for the data that I've presented, this is data over 10 years, and it's been checked and rechecked a million times, and right. So you can trust that.
Yeah. No, you only have to do this once. Once we've done this and we have an initial data set, we know the actual pulse number of every observation. You can just not look at this pulsar for 2 years. Look at it again. And because this timing model is so good, we know exactly which pulse number belongs to that observation. We don't even have to guess anymore. We actually know it. So once you solve this problem, it's a solved problem. And we can just extrapolate it to years into the future.
But you do need multiple observations within the coherence limit, right? Sorry.
Yes. Yeah. And otherwise it's an exponentially increasing problem where you have to try multiple pulse numbers. Yeah.
Okay.
That's hard to answer because honestly, I haven't tested it that well. It definitely wouldn't work if our model is not correct, like in a triple system or something like that. But I would estimate that this, if a grad student can solve it, this thing would be able to solve it. Let's keep it at that.
It's as good as a grad student.
Yeah, which is good in a way.
Do you ever have to worry about things like glitches or anything?
Oh, that would be a problem, I suppose. But yeah, that's right. That's right. Well, ordinary pulsars, they would be usually not in binary. Some of them will be, but most of them won't be. And then it's not that hard of a problem.
And I also had a question about the distribution of the pulsars. Are they mostly like focused towards the galactic center, or are you trying to specifically, look at a very?
I'm not doing any observations. That's
in general, do you know how they're distributed?
Well, yeah, they're mostly towards the galactic center, but yeah, it doesn't matter for this kind of stuff.
More questions? Okay, well, thank you. So, Paul, do you have anything?
Awesome day, very interesting. Thanks to everybody. So we should be at the restaurant for dinner sometime between 6:15 and 6:30. Hopefully more towards the early time. That's nearly an hour. If you want to take a walk and try to wake up or whatever, you can stay here and work on your laptop if you want to. So again, it's at the Sheraton. So let's just raise your hand if you are familiar with the territory around here. So if you're friends with those people, then you're in good shape. So we'll see you at dinner. And then tomorrow morning we reconvene 9 a.m.
Well, do you anything?
Yeah.